Hello and welcome to the first annual virtual student workshop taking place as part of the 2020 CEDAR virtual meeting. My name is Matthew Graw. I'm from the University of Illinois at Urbana-Champaign. I'm joined by Komal Kumari from Clemson University, and we are the CSSC student representatives this year. If you're a first-time attendee, congratulations. By attending the CEDAR workshop, you are gaining exposure to the forefront of research in our community, and this is a significant achievement for you and your academic career. If you're a returning participant, welcome back. So I'm going to quickly share my screen so that you can see what we have to share today. So Komal and I would like to go over a couple things before we begin the first speaker. So we're going to talk a little bit about the participation statistics for today. We would like to introduce the CEDAR Science Slack. We want to talk a little bit about the CEDAR Student newsletter. We'll talk a little bit about how we're handling questions and answers for today. Komal will then talk a bit about the theme and schedule for today, and then we'll wrap up the intro with some comments about the CEDAR mailing list, the selection of the next student rep, and the feedback form that we would like to send out at the end of the workshop today. So we have a few viewer recommendations. To ensure an uninterrupted viewing experience, we ask that you try to limit other usage of your internet connection. If you do end up experiencing buffering issues or quality issues, try to pause large downloads, halt other streaming services. Things like Netflix and Hulu will eat up your internet bandwidth. We also, if you can, try to use a wired internet connection, and if you can't, try to place your laptop near your router or switch. So we're happy to welcome participants from all over the globe today. So on the left, the countries in red are countries that have registered participants for today. And I believe that we have participants from almost every continent. We have around 230 total participants. 61% of those are students, 22% of those are early career, 9% are mid-career, and 6% are senior, and 2% are non-science careers. So as I mentioned before, we'd like to spend a few minutes here and talk a bit about the newly created CEDAR Science Slack workspace. We created this to serve the CEDAR Science community during the virtual workshop, but also we created it to act as a resource for sustained interaction at all times. So if you are a workshop session convener or a other community leader, we strongly encourage you to join and utilize this workspace and create channels for your sub-communities. We also invite students to play a leadership role in making this a beneficial resource for the entire community. So if you look at the top right of the slide here, you'll see a QR code. If you use your phone to scan that code, it will directly send you an invite to the Slack. And if you can't do that, you can always email Komal or me using the email addresses shown at the top of this slide. So Q&A today will be done using something called Slido. To access Slido, you go to slido.com on your computer or mobile device. When you get to that, you'll see a little text box for an event code. You type in CEDAR 2020, all caps, no spaces. It should be shown at the bottom of the stream. When you get inside of our event, you'll see a prompt for you to type a question, or you will see the other questions that have already been asked, and you can upvote them if you like them. And the way this will work is that we're going to do our best to allow around 5 minutes of Q&A at the end of each talk, and we will sort those questions by the most popular, the most upvoted questions, and we will go down the line and ask them until there are either none remaining or the speaker's time slot expires. We'd also like to thank Aiden Monter for helping with question moderation today. So at this point, I'm going to pass off control to Komal, who will talk a little bit about the newsletter and some other things. Komal?
Thank you, Matthew. Good morning, everyone. Good morning, CEDAR attendees. I'm Komal Kumari. I'm currently talking from Clemson University in the United States. Thank you, everyone, for joining, irrespective of your time zone difference. As Matthew already pointed out, irrespective of which continent you're residing in, you would be able to interact and communicate with other CEDAR attendees through CEDAR Slack workspace. So I again urge the audience to invite yourself and join the workspace. We are also, Matthew and I are also starting a new initiative this year, which is CEDAR Student newsletter. This is to communicate how students benefit from CEDAR. So this would be something created and written by students and for students. So we will be creating summaries of each of the talk today, which would be written by student volunteers. And for that, we give special thanks to our student volunteers who came on board from all around the globe to help us with this initiative. We have Deepthi Agri from Indian Institute of Technology, Indore from India. We have Edith Makatola from University of Oulu, Finland. We have Megan Leme from Boston University, United States. We have Robert Irvine from University of Illinois, Urbana-Champaign. We have Aidan Monteiro from Case Western Reserve University from United States. So we please expect this newsletter to be released sometime in July. And I urge the audience, especially students, to please print it out, this newsletter, once it's published, and put it at the notice board in your universities or institutions. It would be a great help in terms of raising the awareness towards what we do as scientists in our community. So going back to today, we have 8 wonderful talks today, and those talks basically lie within this broad theme, which is mapping out the future directions of space physics and aeronomy. In morning, no, speakers will be talking about the future directions in terms of effects on geospace, environment of solar variability, and meteorological driving of the IT system. Um, and we'll be listening about what we know, what we don't for particular research areas in our community. We'll be also listening about the future directions for those areas. In afternoon, the speakers will be talking about the future directions in terms of modeling and data science. And we'll also be listening about identifying emerging research topics, new data, new opportunities. Um, so as I said before, we have 8 wonderful talks today, and we have great list of speakers from all over the United States. As Matthew already pointed out, that we have, after each talk, we have 5 minutes of Q&A sessions. And audience will be basically, the audience will be able to ask questions to the speakers via Slido. So please, I urge the audience to make yourself familiar with the Slido. And also, one thing I would like to point out, if you're listening to the talk in your computer or on your screen, you will need to have Slido on a different screen. So please be prepared and ask questions to our speakers. We will try to ask the most popular questions to the speakers, and the questions which would not be answered today, we will be sending out those rest of the questions to the speaker, and we'll be publishing the answers in the newsletter later. So with that, we realized that we had a long day. We have a long day. We also have we have 3 breaks. We have a brief lunch break, and we have 2 little 10 to 15 minutes break. So I hope you all have a great and eventful day today. Um, Next, Matthew. Yes. Other relevant information, especially for the CEDAR attendees who are attending first time CEDAR. If you're not subscribed to the CEDAR mailing list, please do so by using this QR code. It's a great way to know about job opportunities, new mission, new data, conference updates. So if you're not subscribed to the mailing list, please do so by today. Um, Another important announcement is Matthew is outgoing CEDAR student representative. He has successfully completed his 2 years of student representative term. And he has done a wonderful job. We urge from our audience, if any of you is interested to become an incoming CEDAR student representative, please nominate yourself or your friend. um, you will be basically the incoming CEDAR student representative will be helping me to organize the CEDAR student workshop next year. So if you are interested, if any of you are interested in taking the student leadership role, please reach out to Matthew or myself via email, or you can also reach out to us via Slack workspace. I know it's much easier for me to talk with a professor via or any CEDAR attendees via Slack workspace. So I urge the audience again to use the CEDAR Slack workspace. At the end, we will be sending student feedback. We'll be sending feedback form for the student workshop. I urge the audience to please fill this out. Please be candid and let us know what you think about the future directions of space physics and aeronomy. And please let us know what you want us to include for next year's CEDAR student workshop. It will be very helpful for us to plan the future CEDAR workshop. So with that, thank you again for your attendance from all around the globe. We also encourage you to inspect the full workshop schedule and attend individual sessions. So please use this QR code or this link uh, to look into the individual sessions from Tuesday onwards. There are many interesting individual sessions that may spark your interest, may spark your some ideas. So I again urge the audience to explore the CEDAR schedule. So with that, I am going to transfer to the stage to Professor Dolores Knapp. Dr. Dolores Knapp is a research professor at University of Colorado Boulder and at its Space Weather Technology Education and Research Center, and a senior research associate at the U.S. National Center for Atmospheric Research High Altitude Observatory. She's also the current chair of the CEDAR Science Steering Committee. Dr. Knapp earned her PhD at the University of California, Los Angeles. So with that, Dr. Nip, whenever you are ready.
All right. Thank you, Komal and Matthew. I'm sending greetings from the beautiful Front Range of the Rockies, the University of Colorado Boulder. So on behalf of the CEDAR Science Steering Committee, whom you will get to see pictures of tomorrow morning in the town hall, I would like to welcome you to this exciting and what I think are game-changing ways of doing business. So the virtual student workshop, just to give you a sense, I have attended workshops, many of the student workshops for almost 30 years, so you can do the math and realize that I was probably attending back in the late 80s. That was before there was regular email, laptops, and cell phones. So our communication modes were pretty different, and I am amazed at what Matthew and Komal have managed to put together to bring us into a next step forward for this meeting. But I'll take you back to 1987 when my advisor told me I was going to go to the first CEDAR meeting, and I go, well, what's that? I didn't understand the acronyms, and you may not either. So here it is. It's the coupling, energetics, and dynamics of atmospheric regions. And I asked my advisor what that meant, and he said, oh, it means aeronomy. And of course, I didn't know what that meant either. So he told me it was the meteorology of where the atmosphere meets space. And I went away relatively happy with that because I was a meteorology major and I thought, well, that makes some sense. I've spent the remaining 30 plus years trying to figure out all of the, or many of the aspects of CEDAR. So I wanted to put this diagram, I love diagrams, on this slide to give you maybe a better sense of the physical domain of CEDAR. We are still very much in the spheres of Earth's atmosphere, but these spheres are strongly interacting with the heliosphere and the magnetosphere. So we get in our domain energy from above and below, and it's a very exciting and somewhat complex science. Hence, we've been going for 30 plus years. Our science domain is squarely in the middle of Earth science and solar studies. We do a lot with particles and plasma, and we make some just really interesting types of measurements, which I'll bring back up in a moment. But before I do that, let me just point out to you again that your student reps are the ones that are really bringing us into the next decade and the next way of doing business. So I wanted to put these pictures up so that you could see them. You might recognize that this is an earlier picture of Matthew. He did not overnight grow a beard. So, but I just wanted to call out how much work they have done and urge you, if you are enjoying this and are motivated to be one of the next student reps, please let them know, because we will be considering who to bring on as a student rep in an upcoming meeting in about a week. Okay, you're going to be seeing a sea of words navigating almost an ocean of ideas. I tried to grab these words from a project I did just a few weeks ago to create what is my contribution to this student meeting, which is a resource list of about 40 textbooks and texts that are relevant to CEDAR science and CEDAR studies. I can assure you nothing like this existed in 1987, and maybe sadly not even until recently. So I thought it's really important that you have something beyond the journal articles that your professors might be sending to you that gives you kind of a solid, here's where I can go and look things up list of documents. And it covers this range of CEDAR related activities, which you can just see here. And I will tell you now that there is a document on our wiki webpage, along with a little video that I made that is your guide to a CEDAR cross-disciplinary bookshelf that covers these topics. We go starting at the bottom from the mid-atmosphere. These books will guide you through tides and waves, chemistry, ionosphere, all the way out into the space environment and space weather. And I also tried to put on here some additional references associated with statistics and applications, data science, measurements that are relevant. So I put the QR code here and also dropped in the link. You can go to that at any time, and you can feel free to email me and tell me if you think that I've missed something or something needs to be added. 2 items about the meeting. As we said, this is a grand experiment driven largely by the COVID virus, but I think we will overcome this. At the moment, we have to be social distance, so we're going to have this grand experiment where we have, I think it's just it's 230 students now. I suspect that other students will ultimately join in or at least read the material, so I'll be optimistic and say that we're providing free access for nearly 30 students. This is very generously supported by the National Science Foundation, who helped us pivot to make this a virtual meeting, and the CEDAR Steering Committee. That said, we're engaging with a virtual mix of cultures across a lot of time zones and boundaries and different social norms, dealing with many levels of expertise. I know that the student reps have done their very best to make this a welcoming and engaging channel and providing you a Slack channel to interact with and enhance with others. There could always be an opportunity for some kind of inappropriate behavior, intended, unintended, intended. So I want to urge you to go to the Code of Conduct on our virtual meeting page and read through that and see our general expectations for behavior of all meeting participants. And if you feel that something inappropriate has happened, I hope not, but if it does happen during this virtual meeting, there are contacts that you can send an email to report any kind of unacceptable or unwelcome behavior. So to my last slide, I really invite you to participate broadly. You've already seen the outline for today and know that there's going to be Slido Q&A and Slack channel. This will be archived on YouTube, as will tomorrow's town hall meeting, where there will be more attendees and speakers giving outlooks about the future and vitality of the CEDAR science. And then really do dig in with the workshops that go after that, Tuesday through Friday. There are Grand Challenge workshops, emerging idea workshops, 23 of these. We even have a workshop on the last day to try and engage with some of the social challenges related to workforce vitality, including diversity, equity, and inclusion. I recommend you check that out and participate. Lots of pre-recorded presentations that you can view at any time. So I will be turning this back over to Matthew with just this urge to you, invitation to learn, communicate, share, enjoy, and tell us how we're doing with supporting this virtual meeting. So thank you.
Thanks, Dolores. So we're going to go ahead and get started. So our first speaker today is Dr. Stephen Kapler. He is an assistant professor of physics and astronomy at Clemson University. Dr. Kapler earned his PhD in physics from the University of Iowa in 2013. He was a postdoctoral fellow at SRI International from 2013 to 2015, and later as a research engineer from 2015 to 2017. In 2018, Dr. Kapler joined the faculty at Clemson University. Dr. Kapler's research interests are in magnetosphere, ionosphere-thermosphere coupling at high latitudes, auroral electrodynamics, and bottom-side ionospheric physics. Dr. Kapler is an experimentalist who uses incoherent scatter and high-frequency radar techniques and sounding rocket measurements to probe the ionosphere-thermosphere system. He is the PI of the NASA Ion Neutral Coupling During Active Aurora, INCAA, sounding rocket mission. Dr. Kapler is going to speak to us today about high latitude and polar processes. So whenever you're ready, Dr. Kapler, you can take control of the live stream and give your presentation.
All right, thank you very much, Matthew. So I'm Dr. Stephen Kapler. I'm calling and talking to you from Clemson, South Carolina. So today I'm going to talk about high latitude and polar processes, and this sort of picture here is a good diagram of, you're going to see this picture probably a lot today, of the various processes that happen around the globe that we study in the CEDAR community. High latitude and polar processes is, let's see here. High latitude and polar processes, this is the big topic. So I'm going to give a disclaimer, but briefly in terms of an outline, we're going to talk about basic principles and phenomena, how this basically turned into a talk about MI coupling, and I'll motivate that in a few slides. And then I'd like to shift gears a little bit and talk about big questions for CEDAR 2020, particularly at high latitudes in the polar ionosphere-thermosphere, and also some future outlooks and directions based on sort of my perspective on the community. So just a quick disclaimer regarding this talk. So first of all, your views on a topic or what perspective you're going to have is dictated strongly by the techniques that you use. So I am an experimentalist, an observational person, a hardware person, and less so a modeler and theory person. So if you were getting this talk from a modeler or a theory person, you might see sort of a different perspective on the topic. That being said, I think I've tried to highlight some of the basic physics that we see, and at the very least talk about some of the phenomena and terminology that we see at the high latitudes and how they're coupled and interplay with each other. The second thing is that my background is actually more in plasma physics. University of Iowa is an excellent school in plasma physics, and a little bit less so in neutral atmospheric dynamics. So the focus is going to be a little bit more on plasma physics. With some of my colleagues in some of the later talks today, hopefully going to be filling in a lot of the gaps that perhaps I have. There's going to be more breadth than depth in this talk. And last but not least, there's a lot of really basic physics that have been outlined in a number of previous student tutorial talks, particularly this one, Geospace Electrodynamics by Roger Barney, Astrid Mott, and Jeffrey Forbes. And so I would encourage you to look at those talks if you're really curious about some of the basic plasma physics. Okay, so let me start off with some really basic concepts. So what we have here, let me talk a little bit about what do we mean by the ionosphere-thermosphere. So let's take a real basic step here. So when we talk about this region from about 50 kilometers up to about 1,000 kilometers, we're talking about the upper layers of the Earth's atmosphere. And those layers are composed of basically two overlapping populations of particles that switch back and forth between being neutral, which is the thermosphere, and then you also have this very, very weakly ionized layer called the ionosphere, or the plasma part, which is the ionosphere. Traditionally, these layers have been divided up into the D, E, and F layer, where the E layer, I believe, was the first one that was actually discovered back in the turn of the 19th century, with Heaviside at least theorized it, and then Bright and Tuve were the first to actually reflect radio waves off of this. So the reason why we even know the ionosphere exists is because of radio experiments that happened quite a while ago. But this is actually a very, very weakly ionized plasma. So the E region is primarily composed of molecular ions. As you go to higher and higher altitudes, especially in the F region, you start talking about atomic ions. So you can see that these are primarily atomic species, with O+ being your dominant atomic ion. And then you have the electrons, since plasmas are quasi-neutral. So the electrons and ion populations basically equal each other. The thermosphere, you can see, is significantly more dense, orders of magnitude more dense than the ionized component. So the plasma is actually very, very weakly ionized, but its impact on radio wave propagation in particular is one of the reasons why it's so significant and why we see it. Anyways, this is kind of an introductory slide to kind of get us all onto the same page when we talk about the ionosphere and thermosphere. So what I'd like to do now is provide just a little bit of motivation about high latitude processes. So first of all, why do we study these regions to begin with? And there's a couple of reasons why, but the most significant is that the magnetic flux tubes from the Earth's magnetic field couple deep within the magnetotail, and some regions couple directly within the solar wind. So these magnetic fields, the Earth's field is kind of a dipolar field, and what happens is these flux tubes actually converge in towards the pole. So that's one of the reasons why this is a more interesting region to study. And so to illustrate that, I have this diagram here. So this is sort of a standard diagram showing the Earth right here. And then we have the solar wind, which is coming in. We call this region by the sun here the day side. And then this is the night side. So you can envision sunlight is illuminating this side of the Earth. And what we have here are these different regions that are connected by these magnetic flux tubes. So the region of interest here are these purple regions, where you can see that you have some of these sort of dipolar field lines. They sort of form a bullet shape, but these dipolar field lines here are the closed flux tubes, magnetic flux tubes. But then you also have these open flux tubes which converge into the pole. And these are carried and moved by the, so these are the Earth's magnetic field, which are actually connecting with the interplanetary magnetic field, which is basically moving through by virtue of the solar wind. So you have the day side over here, and then of course, like I say, the night side. You also get reconnection, which happens over here, and this is a term that we use and means something very specific, which closes these magnetic flux tubes. So in terms of what we're interested in, we can take this Earth's magnetic field, this sort of dipolar field, and we can divide up into a couple of different regions. So starting from the equator here, we call this region the equatorial ionosphere, and it corresponds to basically at the geomagnetic equator. And these are generally closed flux tubes. As we go to higher and higher latitudes, we start to get into the subaurora zone at sort of mid-latitudes, or going from these low latitudes up to mid-latitudes. You get into the auroral zone, and the auroral zone corresponds to the last closed flux tube. And then as you get into the polar cap, you start getting into these open field lines, which are connected more directly with the magnetos, with the solar wind, and also into different regions of the magnetosphere. So one of the other regions that's fairly interesting to talk about is on the day side. You have this region here, which is called the cusp. And this is where you have a convergence of magnetic flux tubes into the polar region that happens primarily on the day side. And the reason why this is important is because this allows for a basically direct coupling of the solar wind and the plasma on the solar wind right into the high latitude ionosphere. So it's a very specific region of the high latitude ionosphere that people have studied. And very, very recently, to kind of make a connection to some recent activities, there's been a recent sounding rocket campaign out of Norway that has been primarily designed to study the cusp. It's corresponded to 12 rockets over 9 missions that have investigated a variety of different mechanisms and different scientific questions associated with this particular region of converging magnetic flux tubes. And so I'd encourage you, especially if you're not familiar with this, to watch this. There's a video on this website down here that's actually quite good. Okay, so connecting So the reason why, as I mentioned, there's these different flux tubes that couple to the solar wind, but these flux tubes also couple into different regions of the magnetosphere. So the magnetosphere is basically a region of plasma that's basically confined within the Earth's magnetic field. And there's a bunch of different regions that we talk about as plasma physicists and space scientists that correspond to both different magnetic field characteristics and also the characteristics of the particles as well. So in particular for the auroral zone, we're really interested in the plasma sheet. So these are extended regions. This is the tail region that gets extended out, and we're interested in the plasma sheet populations, which form the source population that precipitate into the auroral zone. You also have, for example, the cusp region, which connects to different regions within the magnetosphere and also directly to the solar wind. And then you also have the polar cap, which connects within different regions of the magnetosphere as well. Now, just to point out as well, there's a bunch of different regions. For example, you have the plasmasphere, the radiation belt. You have the different regions within the tail, the neutral sheet. And all these different regions have their own fields of study and are important in their own right. And currently right now, there's actually a series of seminars that are being presented on a weekly basis. And this is the website. These are online seminars that are actually exploring a lot of these different regions within the magnetosphere. And I would encourage you to potentially look into these as well for more information about basic magnetospheric physics. So in terms of what we're interested in the high latitudes, we're really interested in this extended tail region on the night side, and then also this cusp region and day side as well, and the auroral precipitation that forms. So, so I've given at least one reason why we study is that basically we have a tightly coupled system where the plasma can be driving processes that we're seeing. So magnetospheric processes are driving ionospheric processes. And so what we need to really understand is we need to understand some of these magnetospheric processes, and we need to understand the coupling between the magnetosphere to the ionosphere to understand how the ionosphere and thermosphere is driven by the magnetosphere. So another way to phrase this is sort of ignorance of the magnetospheric ionosphere coupling is sort of ignorance of the high latitude ionosphere-thermosphere system. We need to understand both to really understand the driving that's happening. For the remainder of this talk, I'm going to specifically focus primarily on the electrodynamic and plasma coupling. And again, I'll leave it to my colleagues to talk a little bit more about the interesting neutral dynamics that's also happening at the same time, which is driving the region as well. So I'd like to take a little bit of a step back in time, and we're going to go back to 1964 here, so about 50 some years ago. And 1964 was actually a fairly important year, so important that a TV show I like, American Experience, made an episode about it. And what's over here is Muhammad Ali and the Beatles, of course, right at kind of the rising edge. Obviously, two huge cultural icons in the 20th century. So what I want to talk about now is that around 1964, there were actually two significant papers that actually came out, one of which I kind of want to add in because it's a term that you sometimes hear, and that's field-aligned irregularities in the ionosphere. And then the other paper was this model of auroral electrodynamics, and we're going to talk about that for the remainder of the talk. But I wanted to at least highlight this paper that was by Farley. Here's a picture of Don Farley. He was a professor at Cornell. And he actually does have a contribution to our story as well, because he was one of the first to mathematically describe some of the electric field mapping, which is a common assumption that we use to map magnetospheric electric fields down into the top of the ionosphere. But he was also the father of a technique called incoherent scatter radar, which is arguably the most powerful ground-based technique for probing the ionosphere. But one of his early contributions as well was the study of field-aligned irregularities, which are a common backscatter source that are used by a number of radars, both at mid and low latitudes and at high latitudes. So let's dive in and talk a little bit about this model of auroral electrojets by Bostrom, who's a Swede from Sweden. And so this is the basic picture that Bostrom had come up with. If you look in his paper, this is basically what you'll find. There were sort of two cases he devised for magnetosphere-ionosphere coupling. You have the magnetosphere out here where you have a large electric field, and you could have these line currents that flow in, and you have a large sort of electrojet which forms, which is indicated here, and polarization charges with these pluses and minuses, and the current flowing out. The other case you could have are these sheet currents which end up forming, where you have an upward field-aligned current, downward field-aligned currents, and then you have these closure currents where IH corresponds to a Hall current, and then a Pedersen current which forms. So these pictures were theorized way back in the very early days of space physics back in the 1960s. And what I want to do is actually discuss some of these configurations in more detail, and then make the connection to how, kind of where we are right now and where we're going. So this diagram, this basic picture here is sort of evolved into a more standardized diagram here. This diagram is a sort of a reprint of originally, it was in a Baum-Johann paper from 1983. And also he has a plasma physics textbook. And so the basic idea is that you have magnetospheric currents, plasma, and electric fields, and you have ionospheric currents, conductivity, and electric fields, which are all connected in the ionosphere through Ohm's law. And they're within this neutral atmosphere that we have, the thermosphere in the background. And you have these agents, as I call them, of magnetosphere-ionosphere coupling. You have field-aligned currents, particle precipitation, and then also electric field mapping. And as I mentioned with the electric field mapping, this was one of Farley's first contributions, actually, was describing the mathematics for how you could have fields that could map in different regions in space. So the magnetosphere is coupled to the ionosphere through some of these agents. Also, you can have that the ionosphere in and of itself can also produce certain agents which couple back into the magnetosphere. In particular, one of the most important ones currently that people are studying is ion outflow, and the impact that ion outflow has within the magnetosphere. So I'd like to go ahead and talk about a few of these individually. And what I'm going to do is I'm going to talk about the electric fields, the particle precipitation, and the currents individually, and then I'll kind of come back to the overall picture. So let's talk about the electric fields first. And so the convective electric field is basically the idea that the solar wind, so there's an important concept in plasma physics that we talk about, which is the concept of things being frozen in or frozen in flux. And the idea is that if you have a tube of magnetic flux that has is associated with the plasma, if you move that plasma, you're going to move the magnetic field line along with it. And if you move the magnetic field line, you move the plasma. Okay, so this is the basic idea, and it's well understood that this is a good concept, a well understood concept in MI coupling. So the idea is that the solar wind is actually dragging these magnetic flux tubes. And so what ends up happening is these flux tubes get dragged over the pole to the back side, from the day side to the night side. So you can see this progression here of numbers 1, 2, 3, 4, 1, 2, 3, 4, as the flux tube is getting dragged by the solar wind. As it comes to the night side, you have this situation where the wind continues to pull out and stretch and stretch and stretch. And eventually you get a point at which the flux tubes come together and do something called reconnect. And this reconnection happens right here. And so once the tube reconnects, it becomes a closed flux tube, and like a rubber band, races back in to sort of a dipolar configuration shown as figure 8. And so this flux tube then now moves back to the front, back to the day side. And so you end up having this convection pattern which forms, where you have this typical velocity of the ions moving throughout the day as a result of this convection pattern. And so what happens is this convection pattern sets up these electric fields, or the electric fields set up the convection pattern, and you get these electric fields which get set up along with this, what they call two-cell convection pattern, which gets formed. Now, another phrase for this is sometimes called the Dungy cycle, the Dungy cycle two-cell convection, but this is sort of the dominant convection pattern that you have, where you have the dusk side, and then you have the dawn side, and you end up having this convection which ends up happening throughout the day as a result of magneto's reconnection, and also the solar wind driving the system. I will just add, by the way, too, that this is primarily the picture that we see, or sort of the classic picture you see for BZ South, which means the interplanetary magnetic field is pointed towards the geographic south. Okay, so, but it turns out that actually the picture is much more complicated than simple two-cell convection. So for BZ South, so what I'm showing here are magnetic local time plots of this two-cell convection pattern. Okay, these are actually in kilovolts, so this is actually voltage potentials, but you can envision that you would end up having the two-cell convection rotating around these cells here. So you can see, and what's shown here is the clock angle, as they call it, of the interplanetary magnetic field. So this is purely southward, purely northward, eastward, and westward. And what you end up having is for generally southward BZ, you get this two-cell convection pattern, which forms as shown by these cells here. But if you go to northward convection, the situation becomes a lot more complicated, and you start getting sort of a fragmenting of the convection pattern, which appears, where you can actually have multiple cells that appear. Additionally, the IMF-BY actually has an impact on this as well, and can shape sort of the dawn side cells and the dusk sides, or the dusk side and the dawn side cells that you end up seeing, based on the orientation of IMF-BY. So some of this is written about, and this comes from the Weimer model, and this was in a paper by Pfaff from 2012. But the upshot of all this is that the convection pattern changes a lot depending on the solar wind conditions, and so it's actually variable. It's not just sort of this simple picture that we originally see. So what I'd like to do now is move on to particle precipitation and how that impacts high latitude ionosphere-thermosphere systems. So very quickly, returning back to this picture, you also notice here we have the polar cap in green and the auroral belt, so the auroral zone and the polar cap. And so what we're talking about now for particle precipitation is primarily in the auroral zone. So these are two different types of aurora. This is something I'm studied a lot as a grad student and currently study. But basically, aurora that we see, so this green and red and blue lights and other type of color that you see are composed of basically two types, or there's basically two types of auroral configurations. There's discrete and diffuse. Discrete aurora is generally caused by electrons that precipitate they're accelerated by parallel electric fields, so parallel to the mean magnetic field at very, very high altitudes, well above the ionosphere. These auroras that we see are generally 1 to 10 keV electrons. Okay, so that's kiloelectron volt electrons. And they tend to be the more structured version of the aurora that we see. So you see sheets, arcs, rays, all that kind of stuff. Other names that are referred to them in the literature, other features of the aurora that are referred to them in literature are such as inverted V. Let's talk about black aurora, alphanic aurora, flickering aurora. And then you also have diffuse aurora. So this is more like glow that you see in sort of towards the north. So for example, I grew up in Wisconsin. If you live in Wisconsin, sometimes if you look towards the north on some nights, you'll see just a glow. That's an example of diffuse aurora. So there's very little or no structure. In this case, you end up having more direct precipitation, which is caused by wave-particle interactions, which is a certain type of plasma phenomena that is very actively studied. Typically, the precipitation is more energetic, so 10 to 100 keV, and sometimes even greater than 100 keV electrons. And we talk about this as rain, pulsating aurora. That's a common example, or proton aurora. Now, the reason why all this matters, is because when you have this precipitation, what's shown here are different energies of electrons precipitating. This is taken from a paper by Semeter and Kalamabadi from 2005. You get this deposition at lower and lower altitudes from this auroral precipitation. And what this does is it changes your conductivity. So the conductivity is directly related to the electron density, which can get significantly enhanced during discrete auroral events. Now, so to show you kind of an example here, by the way, too, this is actually kind of where we are right now in terms of understanding discrete auroral physics, is that there was a satellite from the late 1990s called FAST, which sort of really studied discrete auroral arc electrodynamics. So what's shown here is an all-sky image showing discrete auroral arcs. And what you can see as some of the features associated with these discrete auroral arcs is you have downward precipitating electrons. That's indicated by these bumps here, which you can see are clearly correlated with the bright spots. So white here corresponds to bright aurora, dark corresponds to, no aurora or the dark regions. And you can see that clearly correlated here, we have precipitating electrons. If we were to actually measure the electron spectra of that precipitation, which is what's measured here, this is plotted with respect to energy and time, you start to see these features here. And these right here are an example of what are called inverted V's. Okay, and so inverted V's, they look more like upside down U's, but when they were originally observing these back in the 70s, they looked more like V's. And then the other important aspect here is that these downward precipitating electrons correspond to upward field-aligned current regions. So there's a large scale upward field-aligned current associated with these downward precipitating electrons. Now, this is the only time I'm going to mention this with respect back to some work I'm doing in particular or have done, but I have in my doctoral thesis, the second chapter presents, in my opinion, a fairly decent review of discrete auroral arc physics up to about 2013. And very recently, there was an article that was published by Carlson in 2020. Here's the link, which also is kind of an update on this sort of the picture past since fast. Okay, so this corresponds to some of the harder precipitation we see, but we can also have soft particle precipitation. And this soft particle precipitation generally tends to occur in the polar cap and also in the cusp region. And just as an example of this, so this is an example from Zhao et al., which shows a polar cap, an air glow patch. So what this is red line emission, which is corresponding to the F region of the ionosphere. And you can see that this region of the air glow patch corresponds to these generally weaker, so 100 to 1 keV electrons. Here you can see that they peak at about between 10 eV and 100 EV. And you can see that there's this air glow patch. And you can also see that this air glow patch is enhanced within the F region of the ionosphere. So it looks like it peaks at about 375 kilometers here relative to the background. So soft particle precipitation that we see generally tends to enhance the F region electron density, while harder electron precipitation that we see tends to enhance the E region electron density. And here's another example here too for the cusp and also the night side, showing some of this soft particle precipitation and the effect that it has on the enhanced, or it has on the electron density, temperature, also the Joule heating rates, and also the density enhancement. So one of the features that's seen in the cusp and in the polar, or particularly in the cusp, are neutral upwellings of neutral particles. And Joule heating caused by, or soft particle precipitation is thought to be one of the mechanisms that can help to enhance this process that we see, which is another reason why folks want to study the cusp, for example. So you can see that this is 200 EV and 400 EV electrons. So now I'd like to move a little bit into the current systems. So talking about magnetospheric current, field-aligned currents, and then also a little bit about ionospheric currents. So in terms of field-aligned currents, magnetometers were flown on in the very early days on satellites. And there was a very important paper by Ajimwa and Patemra from the 1970s, and this is a figure you see a lot, which shows the large-scale field-aligned current patterns. These are currents that are parallel to the local geomagnetic field. And you can see that there are upward and downward field-aligned current pairs. And what they typically define these as are the poleward currents are called the region 1 currents, which actually flips depending on whatever magnetic local time you're at. So this is a figure as though you're looking down towards the Earth. So depending on what magnetic local time you're at, you might have upward or downward field-aligned currents for region 1 currents. And then you have the region 2 currents, which are your equatorward currents. Now, this is kind of a large scale picture that was taken over a number of statistics of flying satellites over the high latitudes, but you also have this more localized picture associated with discrete aurora, and as I've just described as well, but this kind of connects the picture where your downward precipitating electrons are actually your upward field-aligned current, your downward precipitating, or your upward moving electron, your downward precipitating electrons are your upward field-aligned current. Your upward moving electrons are your downward field-aligned current. And then you also have to have a closure current within the ionosphere to close the current systems, because currents don't just flow to wherever. You have to currents close. And you can kind of see how these current pictures are related to this original picture that we had from Bostrom. So as I mentioned with the convective electric field, what we found with the field-aligned currents is that, in fact, the picture is quite a bit more complicated than sort of this large-scale, very averaged picture that we got from the 1970s. And so what I want to show here on the right here, this is data from the Ampere constellation, which was a very clever repurposing of Iridium constellation satellite magnetometers to be able to provide magnetometer data, which could then be used to derive these field-aligned current patterns. So this shows an example of the Iridium magnetometer perturbations. This is the reconstructed magnetometer field, and then this is the actual upward and downward field-aligned currents, which result from these data that go in. The other thing to think about with these field-aligned currents is that the picture from Agemo and Patemra were a large-scale, highly averaged picture. In fact, the field-aligned currents, these region 1 and region 2 currents, actually have a multitude of scales associated with them. And so, for example, Yarylov and McGranahan have both studied some of the scale size dependence of field-aligned currents using two different data sets. So Yarylov studied using ST5, McGranahan more recently studied using Ampere data and have examined the scale sizes of these field-aligned current perturbations. And even in aurora that I've seen on sounding rockets, you can have significant you can have a lot of structuring that can happen within the electron precipitation that you're actually seeing. So these upward and downward field-aligned currents close within the ionosphere and thermosphere. And the way that they do this is because as you start to go lower and lower in altitude, the thermospheric density starts to increase more and more. So the ions are somewhat carrying the current, and what ends up happening is, based on this current difference that you see between the ions and the electrons, as you go lower and lower, the ions will begin to start colliding with neutrals, which cause them to decouple relative to, this is something called the E cross B drift. They decouple off the E cross B drift and begin to start flowing perpendicular to the local magnetic field. So this situation creates a case where you start to have a current that gets formed horizontally. By horizontally, I mean relative to the local magnetic field. And so this, as a result of increased ion or increased neutral density as you go to lower and lower altitudes. So this causes a current to flow perpendicularly. Now, the reason why this is important is because these currents, the closure of field-aligned currents causes energy dissipation. So that's the reason why this is important. And this is kind of a large-scale figure that's taken from Richmond and Thayer. But it shows that, so what's shown here are these green lines here are the Poynting vectors. These correspond to basically the energy input into the ionosphere-thermosphere system. And then down at this region here, you have these cross-field currents which form. You also have the field-aligned currents shown here as these red lines, but you have these cross-field currents which flow. You also have a neutral wind which flows as a result of thermospheric processes, and you have your enhanced Hall and Pedersen conductivities. And you can relate this back that the perpendicular current composed of the Hall and Pedersen currents dotted with the perpendicular electric field, which maps from the magnetosphere to the ionosphere, is related to the Pedersen conductivity times the electric field squared times this other term. And this term right here, the Joule heating, corresponds to your energy that's being dissipated within the ionosphere-thermosphere system. So that's the reason why this all matters, because the ionosphere-thermosphere basically forms the resistor to the magnetosphere. It's one of the ways that energy is dissipated away. Now, to make things more complicated, of course, we've also mentioned that there's this neutral wind component, which you can see here this is represented by UN here. But this shows an actual profile in the E region of the ionosphere that was collected from a sounding rocket experiment from 1995. This is published in Larson et al. And you can see that the neutral winds for both the zonal and meridional winds actually show these significant shears that happen between 100 to 120 kilometers. And so the point here is that, this is a coupled system in the sense that you might have energy coming in, but the neutrals are doing their own thing and can actually modulate the rate of energy transfer that's actually happening within the ionosphere-thermosphere system. And so the neutral wind is actually very important, and the neutral dynamics are important for modulating the amount of energy that is dissipated. So finally, I'd like to talk a little bit about the thermospheric response. This is kind of the blue part that embeds these ionospheric, which again are the plasma components. And the first thing I'd like to talk a little bit about is the thermospheric winds. And so what I've plotted here, or what's plotted here, is to mention that the thermospheric winds are driven by a different set of forces, some of which are driven by the ion convection from the magnetosphere, but there's also pressure forces, the pressure gradient force, and also a significant force that affects the neutral winds overall, as it does in the lower atmosphere when we have weathers, the Coriolis force. So the Coriolis force really starts to become significant. You can also have other forces such as advection, which can be significant at different times. Now, at high latitudes, particularly in the F region, one of the forces that has been shown to be significant is the ion drag force at high latitudes. And this is a figure from Hepner and Miller's paper from 1982. And what's shown here are the lines here are vectors which correspond to neutral wind observations that were taken, whereas the contours here correspond to the ion convection pattern. And one of the first evidence that the neutrals were being affected by the ions was they took this pattern here of ion convection and simply shifted the winds by 2 hours. So they moved the winds by 2 hours in local time. And what you can kind of see pretty clearly in this figure is that the agreement's not so great here, but if you shift by 2 hours, things are starting to line up a lot better in terms of the overall magnitudes that you're seeing. You're starting to see some of this turning. So this was kind of some of the first evidence observationally that the ions are actually playing a role in driving the winds that we see in the F region. More recently, from some satellite observations, this is reconstructed wind fields. And you can see that the wind fields, especially for sort of semi-quiet conditions, generally show this two-cell convection pattern. I mean, you certainly see it on the dusk side here, a little bit on the dawn side, but you see this, and also you see this over the cap flow as well, which is very similar to this two-cell ion convection pattern that we see. And you can see that it gets enhanced during active conditions. And what's shown over here is a decomposition of these winds into the non-divergent components and irrotational. So the rotational and non-rotational components, as you can decompose vector fields using that. And you can see that there's clearly a dusk side cell and also a dawn side cell, along with general sun to night movement as well. Excuse me, sorry about that. All right, so the other thing we can have is that during geomagnetic conditions, you can also have significant changes that can happen in composition and other things, where Joule heating can increase upwelling and cause other kinds of compositional changes. So this is an example showing over about a 24-hour period. Excuse me, actually it's longer than that. It's a little bit more than 36-hour period, showing a compositional change in the mean molecular mass as the result of a storm activity. So you can see that not only do you get an enhancement, but this enhancement also rotates as well with respect to time, and also dissipates, and it dissipates because of diffusion. So you can see that this is the enhancement or the increase that you get from upwelling and from other effects which are caused by, for example, Joule heating. So they cause these compositional changes. I just want to make a note, by the way, too, that this is actually a model-to-model comparison. So it compares a background model where nothing's happening to a model simulating a particular event. And you can find this in a Fuller-Rowell monograph as well, along with the associated text. So finally, what I'd like to talk about before switching topics a little bit is that the thermosphere, of course, can be driven from the lower atmosphere. And what I've really done in this presentation is talked primarily about this side of the equation, so to speak. And that corresponds to kind of what comes down below and how you get joule heating and the different kinds of effects that you can have. However, you can also have atmospheric and wave processes such as gravity waves, planetary waves, and other things, which drive and can cause a lot of forcing from below that can drive the system as well. And so I'd really like to direct you to talks by Heel, by Lieberman, and also there's a paper by Jens Oberheit, who's a colleague of mine here at Clemson. And one of the big claims from this paper, one of the most important paradigm shifts that our field's experienced in the last 10 years is that the waves from below can drive as much energy as the magnetosphere from above. And so this was kind of the thinking previously, was that the magnetosphere was the big dog, it's the main driver. But it turns out the picture is much more complicated and much more interesting in the sense that we really have to take into account the lower atmospheric forcing as well, because it can also be supplying us a lot of energy into the ionosphere-thermosphere at high latitudes. Quick question, how much time do I have left? That. All right, well.
You should have around 15 minutes.
15 minutes? Okay, all right, cool.
Yeah.
All right, so I'm doing good on time. All right. Okay, so one other mechanism that I wanted to mention that's also important in terms of a feedback mechanism that was I showed in this diagram is ion outflow. So the idea is, or there's sort of a fundamental question that people have had is they have these observations out in the magnetosphere, way out here in the magnetosphere of, for example, O+, and there's a question of, well, how does O+ get out there? The sun can only supply so much of that, so where did it come from? And an important mechanism in terms of sort of ionosphere to thermosphere or thermosphere to magnetosphere coupling is ion outflow. And so there's a number of mechanisms that can, which is described in this figure here as well, that can cause heating or other situations where ions start to get, and also there's a mechanism called the polar wind mechanism that can get ions basically out into the magnetosphere. And there's a lot of questions about exactly, so in a lot of cases you can have an upflowing that can happen, but the question becomes, at what point does it go from upflow into outflow, where it goes sort of past just kind of rising in the ionosphere thermosphere and actually getting all the way out into the tail of the magnetosphere. I just want to mention, by the way, too, that there's been a lot of work on this, particularly in the last decade. And for example, the regulation of substorms, how substorms are regulated is, there's a strong correspondence to the O+ density as well for regulating these types of events that you see and how substorms are regulated. So that's one of the reasons why this is actually really important for understanding the overall coupling between various systems. Excuse me. Okay. So what I'd like to do now is kind of shift gears back to where I started a little bit, and also to start talking about where we're going in terms of a field, and sort of my perspective on where we're going in terms of a field. So I started off with this basic configuration from Bostrom. We have these two basic cases, and it turns out that observationally case 2 seems to be more consistent with what's observed. That being said, it's not to say that case 1 doesn't happen, but it's still sort of an open question, in my opinion, about, you know, in what situations do either one of these cases dominate. But more observations seem to suggest that case 2 here is what's basically observed. However, where we are now is we're working on filling in a lot of these details about, you know, how does the different, you know, what's happening both in the magnetosphere and for our field, what's happening in the ionosphere and thermosphere. How is this whole system, like, what are all the different pieces that we have? We understand a lot more than we did back in the early 1960s, but we still have a long ways to go to really understanding in a comprehensive way even this basic picture. So in terms of this conference this year, I'd like to talk a little bit about a couple of sessions in particular and talk a little bit about the connection between some of the big questions that these sections are trying to answer. So there's the Grand Challenges Magnetoscale section, and they're really asking questions about how are physical mechanisms in the IT system like coupled between really large scales to kind of mesoscale to basically really small scales. And what's the physics that explains this coupling that happens back and forth? To go back to I'll give a couple of examples, but to go back to the field-aligned current example, how much field-aligned current do we have being driven by sort of small-scale field-aligned currents versus the very large situation? Is it just we always averaged? In the Poynting flux section, the basic question is where is the energy input? What is the energy input into the IT system? So your Poynting flux is your basic quantity of energy that's being input into the system. And then also, where is that energy distributed? And I'll talk a little bit about some observations which suggest that maybe there's room for greater understanding here. And also, not only where is it distributed, but then how do we model that and get that into the models so that way it's properly represented and represented accurately and with high fidelity so we can drive models properly and understand the physics. And then also there's a cold plasma section, which is on Friday, and this asks basic questions about what are the mechanisms that cause ions to be accelerated and flow into the magnetosphere, along with a number of other questions as well. So it's a good section for understanding some of this MI coupling. And these are sort of three examples that I can pull from and that are very close to the presentation that I've just given. So that's why I wanted to present the material that I did. So speaking a little bit about multi-scale coupling, I'm going to fast forward just a little bit. This is an image from the Themis All-Sky Imager, which shows what you see here. These are auroral arcs. This is a green line light that you see. This is aurora. So this is over very, very large scales here. And we're talking, this is the whole thousands of kilometer scales. And you can see that there's a lot of dynamics and everything is, so you have Alaska over here. This is Canada. And you can see that these systems span thousands of kilometers. So, this is a large scale view of what's happening. But if you go down a little bit smaller, one of those fields of view of those imagers might look like this. And this is a much more mesoscale size. So you're talking a couple hundred kilometers. This is 200 to 300 kilometers on this side and 200 to 300 kilometers on this side. So you've gone all the way from thousands of kilometers down to hundreds of kilometers. And then if you take the Poker Flat Incoherent Scatter Radar, PFISR, now you're talking about going down to say 50 kilometer scale sizes. So the question is, how do these large scale, thousands of kilometers, thousands of kilometers scale phenomena that we're seeing connect to the things that we're seeing at 500 kilometers, connect to the things that we're seeing at 50 kilometers, connect to the things that we can't even really resolve very well except using sounding rockets because they're high time cadence measurements. So PFISR, is this size on the overall scale size. I should also give, by the way, this is Nitin Savadis's work as well. So I just want to make sure I give him credit from one of his previous posters. Nitin did a great job representing this. I couldn't do a better job than this, so I just grabbed it. Regarding the Poynting flux, so back in the early 2000s, in 2003, there was a paper by Keeling which showed that, primarily that the Poynting flux, this was a diagram from a science paper that they published, which showed that the Poynting flux was primarily distributed, primarily in the auroral regions. And if you look at, this is MLT, if this is kind of auroral latitudes here, you don't really see a whole lot happening in the polar cap, a little bit here, but not a whole lot. It's primarily in the auroral zone. So they found that Poynting flux is primarily in the auroral zone using the polar spacecraft. Well, more recently, using DMSP, Huang showed that, there's a large distribution well within the polar cap of, so you can see this is the auroral activity here, but you also see that there's a lot of Poynting flux that's happening in the polar cap as well. And so the question is, and even in some of the more active events and larger dissipation, you're still seeing this. So there's a question of do we really understand where the distribution of energy is going down? Maybe there's more that's happening in the polar cap than we previously understood. What are the implications of that for these large scale models? So these are the kinds of things that I suspect people are going to talk about this week. So what I'd like to do now is shift gears into kind of the final set of things that I wanted to talk about, which is sort of future directions and what I see as being some some unresolved issues and where we're going as a field. So speaking from the modeling perspective, I think that one thing we're really moving towards is higher resolution. Basically needing to have higher resolution within the models to be able to understand and resolve some of the phenomena. So a couple of strategies people are really starting to work with is one, assimilating data directly. Using different data assimilation techniques. You're going to probably hear a lot about that this week. And so to kind of give an got a little ahead of myself here. Another thing is also improving the resolution within models. So right now, a lot of the models that we use, the general circulation models, the resolution is kind of set and kind of fixed. We can also try to play with different things like different kinds of grids. Is there some sort of more optimal grid? Another technique that could be used would be to completely sort of rewrite the models and try to do them using spectral techniques instead. So some of the lower atmospheric models that predict tropospheric weather are actually spectral models. So they solve things in more of a Fourier domain rather than using grid point methods, which is what's currently used. To kind of give a little bit of an argument in favor of why you might want to do increased resolution. This was a paper from 2009 from Miguel Larson and Cassandra Feason. And one of the, even if you just read the abstract, one of the important conclusions that they drew was the agreement between the model and the observations improves significantly, however, in a statistical sense, when the altitude resolution is increased. They're talking about the E region thermospheric winds here. The improved height resolution in the model appears to produce a greater improvement in model predictions than any other factors we examine. So even just increasing the altitude resolution, the scale height resolution can cause a significant, can be a significant improvement. So there's sort of a question about why aren't we doing this as a field, or how can we be moving that forward, especially with the advent of more computational horsepower. I just want to highlight this really quickly that another example is direct assimilation. This was from Honan Wu, who's a graduate student here at Clemson, and Shen Liu, who's also a professor here at Clemson, which shows that they are directly assimilating in SUSY electron flux directly into the TIE GCM models, and sort of the impact that this has on the Joule heating, on the neutral density, when you're actually using realistic flux. They're also using AMY as well. The second thing that I want to bring up is a future direction, which you're going to hear a lot about, particularly from Ryan McGranahan and Asti Bhatt, the using of new machine learning and data and analytics techniques. So there's a large field of these techniques that are used. And also, how can we harness those to do better space physics? And I cannot do justice to this, so I'm going to let Ryan talk about this. But Ryan is a strong advocate for this, and I think it's a great idea moving forward in terms of our community about how can we really use this to extract the most out of the data sets that we have. The final thing that I want to bring up is that observationally, for the decades up to this point in time, we've really been focused heavily on sort of these 1D or 2D cuts through the ionosphere and thermosphere. And we need to really move towards 3D measurements, ideally with high temporal resolution. So true 4D measurements of the severely undersampled system that we have in space. And this is really a huge challenge, actually. So one of the ways we're starting to combat this is actually flying constellations. The other way is more serious efforts of using ground and space-based observations in tandem with each other. Traditionally, the communities have been a little bit separated, but I think we need to come together more and more. And Themis was the first real example. The movie I showed before was one of the first real pioneering examples of using combined ground and space-based observations. To kind of motivate this 1D slice, by the way, too, this is sort of the fast picture where here you have sort of a single cut through, sort of a meridional cut right through all the aurora that you see. Whereas recently there was a rocket launched out of Norway, the Azure mission, which is sort of trying to do a three-dimensional look in a region of space. So these are the TMA trails showing the winds. You have the barium and strontium at the higher altitudes. We're really trying to look at the three-dimensional picture, even in a localized sense. I mean, this is very local, but which brings me to basically my last slide, which is one of the big directions we're going into is one of the big things that we're going to be working on in the coming 10 to 15 years is going to be this GDC, or Global Dynamics Constellation, which is really going to look at a lot of the phenomena that we have, but at multiple, using a constellation of these satellites to actually examine at a number of different magnetic local times and latitude as well. So there was a report that came out about this. This just sort of highlights some of the sort of high level highlighting of what we see here. So with that, I am done. Thank you so much for the opportunity to present here. And if there are any questions, I'll take those now. Hopefully I did not go over on time.
Thank you, Steve. That was a wonderful talk. Yes, we did go a little bit over time, but we also started 5 minutes late. We would quickly, we have many variety of questions that we got from audience. So I would be quickly asking 2 questions, and then we'll move on to next session. So the first question for you, Steve, is thermosphere strictly the neutrals in the atmosphere? Does it span the same height as the ionosphere?
Yeah, so I typically think of them as overlapping regions. So they span, I mean, you know, the neutrals are sort of exponentially decaying with respect to altitude. So it's kind of, it's not like, it's a gradual exponential decay of the neutral mass density, but they do span and overlap the same regions.
Thank you, Steve. The another question for you is, do convection patterns set up electric fields, or do electric fields set up convection patterns? What is the most causal explanation?
That is one that I don't think there's a fast answer to that. I actually am not, I'm going to be completely honest, I'm not entirely comfortable answering that question because it's a complicated question.
We'll be sending you out all the rest of the questions that you can answer later.
Yeah, that would be great. Whoever asked that question, it's not an easy question because it sort of asks the question of what causes what. And I think it depends on your perspective is the short answer to the question.
Thank you, Steve. Can you answer quickly for one more question? Is there
Sure.
more or less auroral activity during solar minimum?
Yes, there is auroral activity during solar minimum. It's just typically they're not, I mean, you do get general activity that happens kind of all the time, and it happens at, you know, near magnetic midnight is when you'll see aurora. I mean, I was in Alaska during the last solar minimum, and we saw aurora, you know, a lot of the nights. There were a lot of nights it was dead quiet, but some of the nights we did see aurora, it was just too far north to launch it to. So you do get auroral activity that happens during solar minimum.
Thank you, Steve. So we will be sending you rest of the question later.
Okay,
thank you very much. We'll be moving on to the next speaker, Shasha Zhao. Shasha is an associate professor in Department of Climate and Space Sciences and Engineering in University of Michigan in the United States. Her research focuses on the dynamic coupling between the Earth's magnetosphere, ionosphere, and thermosphere during geomagnetic disturbances, such as storms and substorms. She has extensive experience in analyzing, interpreting, and modeling observations obtained by various ground and space-based instruments. Shasha will be talking today about future direction in terms of effect of geomagnetic storms on the thermosphere-ionosphere system. So Professor Sasha, whenever you are ready, please go ahead.
Okay, thank you, Kamal, for the very nice introduction. Can you hear me okay?
Can you speak louder a little bit, please? Thank you.
Okay, how about now? Is it better now?
It's a little bit more louder, please. Can you go closer to the screen? That would be, I think, helpful. Otherwise, yes.
I'm actually, okay. So let me try it again. Is it showing up now? Okay. Can you see it now? Okay, perfect. Thank you very much. I'm very glad to have this opportunity to give this tutorial. And today I will focus on the large scale responses of the IT system to geomagnetic storms. So Steve just now have give a really nice introduction about the MIT coupling. And then, so before I go to the IT system, I'd like to first zoom out into the interplanetary space and look at the general solar terrestrial relationship. Okay, so both the solar radiation and the solar wind are the two important energy sources that's provided by the sun to the geospace system. The solar radiations can penetrate through the Earth's own intrinsic magnetic field without much of an effect, but the solar wind needs to first be processed through the magnetosphere and then reaching down to the IT system. So when we talk about geomagnetic disturbances, you will hear a lot of that terms in this talk. We are talking about how the solar wind and the interplanetary magnetic field embedded in the solar wind interact with the Earth's own intrinsic field and how that interaction changed the configuration of the magnetosphere. Okay, so this is a very short movie just trying to show you how the dynamic solar wind and IMF conditions affecting the Earth's magnetosphere. This is a numerical simulation using the space weather modeling framework, and the color shows the plasma pressure and the white lines are the magnetic field. So you can see that the whole geospace system dynamically responds to the changing solar wind conditions. Okay. We'll come back to the inner magnetosphere later, so don't worry about that. Moving forward, this is a static picture of the Earth's magnetosphere. When the energies of the solar wind gets into the magnetosphere system, they power several current systems. For example, some of the currents are perpendicular to the magnetic field, like the cross-field currents, the ring currents, which is very important for geomagnetic storms. And some of the currents are actually moving along the magnetic field. They are called the field-aligned currents. Those field-aligned currents are the ones that's communicating between the magnetosphere into the ionosphere. So the locations, the strengths of the field-aligned current is a very good indicator of how strongly the magnetosphere and the ionosphere are coupling with each other. When the field-aligned current goes down into the ionosphere, it will close through horizontal currents. Depending on the background conductance distribution, if it's uniform, and then those field-aligned currents would be closed completely due to the horizontal Peterson currents. And so in this case, the Peterson current region is also the region that's where most of the energies are dissipated in the ionosphere-thermosphere system. So now I want to separate the effect of the solar EUV and the solar wind. First, if we only have the solar EUV as the energy source, most of the IT dynamics would occur only in the equatorial to low latitude regions. Here in this diagram, that means the neutral vectors are moving away from the day side solar heating region, and they move away from the equator to the pole. They move from the day side to the night side. The white arrows here indicate the plasma drift. So during the daytime, we have the solar-driven E-region dynamo. That E-region dynamo will set up the electric field that's pointing eastward, and that eastward electric field will drive what we call the equatorial fountain effect that moves the plasma to higher latitude near the equator, and then those plasmas will descending to higher latitude due to the diffusion and the gravity. Okay, but as you can see in this picture, if we only have the solar EUV as the forcing, most of the dynamics happens only in the equatorial and the low latitude regions. Things change dramatically once we add the solar wind energy forcing. Okay, as Steve just mentioned, the solar wind interact with the Earth's magnetic field, and then the energies coming into the magnetosphere while flowing down into the IT system and following those magnetic field lines. So this energy input into the high latitude IT system drives what we call the two-cell convection pattern, drives the aurora oval, and here is the field line current going downward and upward. Okay, so during quieter times, the solar wind energy getting into the magnetosphere is limited. The two systems, the high latitude and the low latitude systems, they do not interact with each other very strongly. Things change when we have strong disturbances, what I like to call when the sun sneezes. So both the solar wind and the solar UV are highly variable and create space weather. When they drive the geospace more strongly, for example, during geomagnetic disturbances, the high latitude system will extend equatward. At the same time, the equatorial system also extends to higher latitudes. So this is the time where we will start to have those cross-latitude coupling. And some of the very interesting phenomena that I'm going to talk about today, like the ionosphere storm, storm enhanced density, all of those happens in those regions during those cross-latitude interactions. Okay. So nowadays, we talk a lot about space weather. When we talk about space weather, we are actually focusing on more of the practical issues or societal impact of those space dynamics. The 5 major space weather threats that's highlighted in the recent National Space Weather Strategy and Action Plan include the induced geoelectric fields, ionizing radiation, ionosphere disturbances, solar radio bursts, and upper atmospheric expansion. The first and ionosphere disturbances, atmospheric expansion, all of those happens in the ionosphere-thermosphere environment. So this actually highlights how important for us to understand the underlying physics of the IT system and how important we should do a good job in terms of the forecasting. Okay, so next I'm going to talk about geomagnetic disturbances. The solar winds and the interplanetary magnetic field embedded are highly variable. They can cause geomagnetic disturbances, including storm, substorm, or shock compression. Substorm and shock compressions can occur independently of the storm, so they can occur even during relatively quiet times. The geomagnetic storm is the largest disturbances among the 3, and they are of global scale and can last for a couple of days. The transient interplanetary structures causing geomagnetic storms, including coronal mass ejection and co-rotating interaction regions. So the coronal mass ejections happens more often during the solar maximum, and then co-rotating interaction region happens more often during the declining phase of the solar cycle and even during solar minimum. Okay. Now, during geomagnetic storms, most often the IMF will have a large BZ component, and that BZ component will enhance the data reconnection that Steve just mentioned and efficiently transfer the energy from the solar wind into the geospace system. We're talking about an order of 100 of petajoules of energy that can get into the geospace system during storm time. A lot of that energy can be stored in the current called a ring current. As I just mentioned before, ring current is moving westward. And so if you use your right hand and look at the magnetic perturbations generated due to this current and measure on the surface, you will see that the ring current generates negative perturbations on the surface. And so a very easy way of understanding the formation and then the strength of the ring current is by looking at how the magnetic perturbation changes near the surface. So the disturbance index that's derived based on that principle is called the disturbance storm time index. It's an hourly index that's traditionally used to identify storm and to define its magnitude. And nowadays, we can also use the higher version, like SIMH, like symmetric H component, which is a 1 minute version of the hourly index GST. We can also use the supermax symmetric ring current index, SMR, to look at the ring current evolution. Okay. Now, in terms of the geomagnitude storm classifications, traditionally we divided them into 4 different categories. The minor storms with the DST between minus 20 to minus 50 nanoTesla. This is really small. So most of those storms are caused by the CIRs that I just mentioned, so the co-rotating interaction region. For the moderate, intense, and superstorms, vast majority of those geomagnitude storms are caused by the coronal mass ejections, especially for intense and superstorms. Almost all of them are caused by, at least partially, the coronal mass ejections. Sometimes there can be a mixture of coronal mass ejection with the co-rotating interaction region. Okay. The picture on the right showing you a time series of a recent geomagnitude storm that happened in September 8th, 2017. This is a CMH, so it's a 1 minute index. And then I showed you the plasma pressure in the equatorial plane, which is often used to indicate the strength of the ring current, because the current carrier is the ions is also the contributing most to the plasma pressure in this region. So shortly after the IMF southward turning, we start to see the ring current become stronger. So here the lighter colors indicate a stronger current. And as you can see, actually the ring current is not a symmetric ring during the main phase of the geomagnitude storm. It has a peak in the pre-midnight sector. This is what we call the partial ring current. Okay, the partial ring current is a very important one because it is the region where the region 2 field line current are generated, and then they communicate the partial ring current region with the ionosphere. Okay, we'll come back to this later. So this slide showed us the energy flow during geomagnitude storms. At a given time, we can have about several hundred of gigawatts of energy coming down in 2 different forms, particle precipitation and then electromagnetic energy or Poynting flux. The electromagnetic energy is the dominant energy source, contains about more than 80% of the total incoming energy. And this energy is further dissipated in 2 different ways, including joule heating. And the joule heating also is more than 80% of the incoming Poynting flux. The kinetic energy, that is the energy goes to drive the neutral wind, is less than 20%. Okay, so all of those energies, like the particle precipitation and the joule heating, will affect the ionosphere and the thermosphere temperatures, will generate aurora illumination, like what Steve just mentioned, and they will drive the thermospheric wind. Okay. So during geomagnitude storms, the whole IT system is modified by those incoming energies. And there are many different current physical quantities that we can look at. So in this tutorial, I will highlight 4 of them: the electric field, the ionosphere plasma content, or we will look at the ionosphere storm, the thermospheric wind, and its composition. Okay, so first, let's look at the high latitude electric field and the neutral wind response during storms. So Steve just showed a very similar picture as this. During geomagnitude storm time, we can have very strong southward IMF. This strong southward IMF will reconnect with the dayside Earth's own intrinsic magnetic field, generating the 2 new open field lines. And those open field lines will move to the night side and then reconnect on the night side. The newly generated closed field line will eventually return back to the day side. So at the same time, the footprint of those magnetic field lines will follow those complete circles. Those are the convection patterns that we are talking about, right? So in this fluid descriptions, we can understand the global scale magnetospheric convection together with the ionospheric convection. So here is another example of the September storm. The middle panel here, I'm showing you the convection pattern with the field line currents. And the bottom rows are again, the plasma pressure indicating the rain current. So comparing the second and the third rows here, you can see that the high latitude convection pattern and the field line current are strongly modulated by the rain current dynamics. The stronger the rain current, the stronger the region 2 field line current. And that also means that it can shield most of the convections going into lower latitude region. So the mismatch between the convection pattern and the field line current can generate either penetration or shielding electric field. If the electric field can penetrate equatward of the region 2 field line current, and those are the penetration electric field that we often observe near the equator, they can be established globally nearly simultaneously. So here, this slide basically want to highlight that the rain current evolution is very important since it modulates the convection pattern and the field line current pattern. This is how the magnetosphere controls the plasma motions and the currents flowing into the ionosphere. Now, once we have enhanced the convection, this convecting ionosphere can be a significant source of momentum and energy for the thermosphere due to ion-neutral collisions. The neutrals cannot feel the electric field or the magnetic field. So the momentum and the energy that's coming into the IT system needs to be transferred to the neutrals through the ionosphere. And this interaction can modify the thermospheric circulation, its temperature, and composition. And this will, in turn, affect the ionosphere. We will look at a lot of the examples later. In terms of the efficiency of the coupling, it is highly depending on the plasma density. And we know in the ionosphere, the plasma density can change significantly 2 or 3 order of magnitude, even during the same day. And this will affect the time constant for how fast the ionosphere can set the thermosphere particles in motion, okay? So if the plasma density is on the lower side, like 10 to the 3rd per cubic centimeter, we are talking about several days that's needed to set the thermospheric plasma to thermospheric neutral to motion. And if the plasma density increases to 10 to the 6th, and then it will respond in like 10 or 20 minutes. Okay, so this is a very big time difference there. Looking into more details in the ion neutral coupling. Now let's look at the time derivative of the ion temperature here, showing in the first equation. Within the parentheses, we're basically looking at 2 factors. The first factor is the temperature difference between the ions and the neutrals. So this is the thermal exchange term. This term here is due to the velocity difference between the ions and the neutrals. So this is the frictional heating term. And those terms are then modulated or weighted by the ion neutral collision frequency. Okay, so the time scale for the ions to respond to the frictional heating whenever we have a velocity difference between the ion and the neutral. This time scale is inversely proportional to the ion neutral collision frequency. And this time scale is typically on the order of a few seconds to a few tenths of seconds. This means whenever we have a velocity difference between the ion and neutral, we can almost see immediately the heating in the ions. On the other hand, the time scale for the neutrals to respond to frictional heating is inversely proportional to the neutral ion collision frequency. And then this frequency is order of magnitude smaller than the ion neutral collision frequency. that means the time scale for the neutrals to respond will be order of magnitude longer than the ions. And so this time difference between the ion and the neutral response to the energies coming leads to many very interesting responses in the IT system. In terms of the evidence of ion-neutral couplings in the high latitude regions, many of those observations actually coming from the DE satellite, back in the 70s. So like the plot showing on the right is showing northward IMF conditions where the convection pattern versus the neutral wind. So we can see the wind basically mimics the convection pattern, although the magnitudes are much smaller, but then the directions are very similar. Okay, so this is another evidence of showing you how the ionosphere affects the polar thermosphere. And the left plot shows the southward IMF conditions, and you can see that over the pole we have strong anti-sunward wind and then sunward wind at lower latitude. So again, this is very similar to the high latitude convection pattern. Now, as I mentioned, the neutrals cannot feel the electric field into the magnetic field. So when the energy is coming down in terms of the electromagnetic energies, they affect the ions and they set up the two-cell convection pattern. After some time, the neutrals will start to move in a very similar pattern as the convections. At this time, if we turn off the high latitude driving force, for example, the IMF BZ turned back to 0, that means we will turn off the electric field almost instantaneously. So that E cross B drift should disappear. But at the same time, that is not affecting the moving neutrals. So in this case, the moving neutrals will start to give momentum and energy back to the ions. And then they will drive a convection pattern that's very similar to the wind pattern. This convection is much smaller than the original, convection pattern due to the higher energies. But still, you can see that in this case, it's very interesting to see the neutrals now start to drive the ions. And then we might also have the Poynting flux actually coming out from the ionosphere and back into the magnetosphere. So this is called the neutral flywheel effect. And it is a very interesting one showing how the thermosphere actually fights back when the driving forces are too strong. Okay, so next I'm going to talk about how the ionospheric density responds during geomagnetic storms, or we call them ionospheric storms. When we call ionospheric storms, we are basically talking about how the ionospheric density disturbances will change during the geomagnetic storm. There can be positive phase or negative phase, depending on whether the density or the total electron content increase or decrease comparing with acquired values. Okay. So here is a picture showing pioneer work by Mike Mandillo back in the 70s, and they used the ground-based receivers to receive signals coming from the satellite geosynchronous orbit. And then based on about 28 storms, we were able to superpose epoch analysis and find out that basically during the first day, we will have a positive phase, and then in the next couple of days, we can have negative phases. Nowadays, in many cases, the low and mid latitude, the density increase is also referred to as storm enhanced density. So many of you probably heard about the storm enhanced density before. Here is a picture of the two-dimensional storm enhanced density, as you can see here over the United States continent. This is a 2D GPS vertical TEC map during storm time. So those increased densities can sometimes actually get into the high latitude regions, across the polar cap, down to the night side aurora, although during extreme cases, they can actually return back to the day side following the convection pattern. Okay. Now, if you're wondering how the ionosphere vertical profile looks underneath each one of those red pixels, this is a picture of that. The blue curves showing the vertical profile during storm time, and the black curve shows the vertical profile during quiet time. So you can see that within the SEDs, both the peak density of the F2 layer and also the height of the F2 layer increases significantly comparing with the quiet time values. So this is what we call a very strong vertical lifting. The vertical lifting within SED is very important because it is the most important reason for the generating of the plasma content increase. Now you may be wondering why when I lift the F-region ionosphere to higher altitudes, I can increase the plasma there. So I'm gonna show you later. So first I want to talk about how to generate those vertical liftings. Now this is a picture showing in the inertial reference frame. You can see that the co-rotation is now added at lower latitude, and higher latitude, this is a superposition of the co-rotation and together with the reconnection-driven convection. This drift can be decomposed into two directions. One is a horizontal drift, and another one is a vertical drift. What's more important here is this vertical drift. On the day side, you can see those numbers are positive. This means that we can have positive vertical drift, and on the night side, those drifts are downward. So how to understand that? Thinking in a situation that we have a non-vertical magnetic field. So the polarward convection flow, this E cross B flow here, will have a component, positive component, projected in the vertical direction. So whenever we have polarward motion, we can have a lifting in the vertical direction. So this can move the F2 layer to higher altitudes. This is not the only way to move the F region to a higher altitude. Thinking about this situation, now in the middle one, we have equator Mariano neutral wind. This neutral wind will try to push the ions to move with them due to the ion-neutral collision. But the ions feel the magnetic field, so they cannot go across the magnetic field easily. Instead, they would tend to move along the magnetic field to higher altitudes. And as you can see here from this chart, this field-aligned movement will also introduce a positive vertical drift. Now, the third condition is that if we have a vertical forces, this is a more generalized vertical force. You can think of either pressure gradient force, or you can think of the gravitational force. So this vertical force also has a component that's projected along the magnetic field. So they can move the plasmas either downward or upward, depending on the sign of the force. So the total vertical plasma drift should be a combination of all of those three different components: the convection electric field, the thermospheric winds, and also the ambipolar diffusion. Within the parentheses, we included the effect of pressure gradient force and the gravity. Okay. Now you may be wondering, when I move the F region plasma to higher altitude, then the plasma content should be the same, right? It's just moving up or down. The total content should be the same. So it's very important to consider those major chemical reactions now in the F region. Atomic oxygen is the dominant ions in the F region. Direct radiative recombination of the atomic oxygen with electrons, the last chemical reaction here, is a very slow one. So this is not an important loss process for the F region. Instead, the two-step dissociative recombination is more important for the O+ in the F region. So first, the O+ needs to charge exchange with the molecular neutrals like N2, O2, or NO, and then generate NO+ and O2+. The NO+ and O2+ can recombine with the electrons very quickly. This reaction rate is about 5 orders of magnitude than the radiative recombination, the bottom one. So the equations from 1 to 5 are the most important ones in the ionosphere F region. Now, think about this. If you lift your ionosphere F region to higher altitude, And then that means the O plus will move away from the dense neutrals. This means you are slowing down the first three reactions, right? In this way, the lifetime of the O plus in the F region will increase. So in this case, you are reducing the loss. If in the meantime, the plasma is on the day side, you can still have the solar EUV ionization going on. So the total plasma content will increase. All of those combine the imbalance production and the loss produce the plasma content increase on the day side. There are several numerical simulations that carried out to look at this impact. Using the Utah State TDIM simulation, and Healy et al. Back in 2009 did a very simple but interesting test. So first, let's just move the plasma from 11 local time to 13 local time without changing its latitude. So there is no polar or equatorial motion of the plasma. In this case, after 2 hours, the total electron content in the ionosphere increases about 3 TeV units, which is less than 10%. If we, at the same time, move the plasma up to higher latitude by 5 degrees, then we can have a 30 TeV unit change. This color scheme also shows you the F region peak density and the peak height also increase due to the lifting force. And in this case, only due to the electric field. The last panel here shows you if the plasma is actually moving equatorward by 5 degrees. And then we will have about 60% of this plasma content lost due to enhanced recombination at a lower F region here. So this simple test tells us how important the convection electric field is for the storm-time ionosphere. Using the GTEM simulations, we also looked at how the ionosphere vertical profiles would change right after the IMF southward turning and northward turning. This would give us an idea of how efficiently the IMF controls the F layer height, right? So the black curve here indicates before the southward turning. The blue curve here indicates after the southward turning. So you can see that the F peak is lifted to higher altitude, and then the topside ionosphere density increased significantly. Now, the panels on the right basically shows that the instantaneous electron density changes due to the vertical motion, due to chemistry, or due to horizontal transport. In this case, as you can see, most of the topside ionosphere density increase is due to the vertical transport from lower altitude and away from the dense neutrals. On the other hand, once we have the IMF northward turning, the IMF northward turning will shut down the lifting electric field. So the ionosphere will gradually descending to lower altitude to the region where they can meet with dense neutrals, and then the chemical reactions will increase and then create the true plasma loss here. So, okay. So the next case I want to talk about the interplay between the electric field and the Meridianal wind. Using the TIEGCM simulations, Lu et al. Back in 2012 looked at the importance of the electric field and the wind at different latitudes. So what she found is the convection electric field is more important in the subaurora region. So remember that this is the penetration in the shooting electric field region. The Meridianal wind, on the other hand, actually plays an important role at mid-latitude regions. So if you look at here, those reddish colors are due to the equator Meridianal wind that's pushing the ionosphere to higher altitudes. So in order to understand the F region ionosphere dynamics, we have to understand the interplay between the convection electric field and the thermospheric wind. Using the phasor radars, we have been looking at the contributions of those two, and we found that they can be highly variable. Sometimes the E cross B contributes significantly, but working against the wind, and so generating a very small lifting force. And sometimes both of them contribute positively, and so generating huge lifting. And sometimes both of them can push the plasma to lower altitudes, and then the storm enhanced density will disappear very quickly. So I like to compare this with the roller coaster ride, right? When the plasma is enhanced or the content increased on the day side SED region, they can be transported to higher latitude. But then this transport is never a smooth ride. It's just like a roller coaster, depending on the local wind and the electric field direction. Now, the last but not to the least is during some superstorms, the equatorial ionization anomaly region will move to a higher latitude region. So they may also contribute to the storm enhanced density here in the mid-latitude region. During those superstorms, we might even have those plasmas in the EIA region join the global plasma circulations. So this is a very interesting thing that's happening only during very strong driving forces. Okay. So next, I'm going to talk about thermospheric wind and the composition changes during storm. You probably noticed that I concentrated only on the positive phase, but not the negative phase of the ionosphere storm. Because in order to understand the negative phase of the ionosphere storm, we have to first understand the wind and the composition change. This is a cartoon showing the thermosphere thermal structure and its energy budget. Okay, the blue words and those arrows indicate the energy input. So for the thermosphere, the solar EUV is the direct heating source, and the solar wind is an indirect heating source. But those are the very important ones to control the general shape of the thermosphere. We can also have tides and the waves coming from the lower atmosphere, and I believe that Ruth will talk about this later today, and so I'm not going to talk about this. As for the energy source, energy loss, we can have the heat conduction. The heat conduction will be vertically downward whenever we have a positive temperature gradient. Okay, so the true loss of the thermosphere energy through heat conduction is at the bottom of the thermosphere, and that heat will go down to the mesosphere. Another way of dissipating the thermosphere energy is the infrared radiation due to the NO and then CO2 here. So let me go to the next slide. Okay. So here is another picture of showing you the thermospheric wind circulation during storms. This is a quiet time, and you can see that the thermosphere temperature is higher on the day side, lower on the night side, because it's driven by the solar heating mainly. The wind is in general anti-sunward, also due to that solar heating. During storm time, we can have very strong geo heating that's deposited into the high latitude aurora zone that will affect the thermosphere neutral wind circulation. On the night side, we can have very large equatorial wind that's moving away from the aurora zone. This is because that in this region, both the solar forcing and the aurora forcing can be superposed together to generate those large equatorial winds.
Hi, Shasha. If you could wrap up in just 2 or 3 more minutes, that would be great. Thank you.
Okay. Yeah, almost there. Yeah. So in the aurora region, we have very large geo heatings, and those geo heatings happen in the E region. This is where the molecular neutrals are the dominant neutrals. And so the geo heating will cause molecular rich air to uplift to higher altitudes. And these disturbances can be transported to lower latitude as well. So here is a picture showing most of the composition perturbation can be generated here, but then they can be brought to lower latitude due to that Mariniano wind surge, and they can even affect the day side when those composition disturbance region co-rotate to the day side. The thermosphere composition or the O/N2 ratio is a very important factor in determining the density of the ionosphere, because the oxygen is the one that controls the production rate of the ions, while the molecular nitrogen actually controls the loss rate. So this ratio is a very sensitive indicator of the density of the ionosphere. The storm-time thermospheric wind and the composition change can be superposed on top of the seasonal variations. If we can have the heatings in the southern hemisphere, right, like during the winter, northern hemisphere winter times, this solar heating will move the molecular rich air to higher altitude and then transport all the way to the northern hemisphere, creating such a large thermosphere wind circulation. This wind circulation will actually change the O over N2 ratio distribution in the summer and the northern hemispheres, creating higher O over N2 ratio in the winter hemisphere. Now, adding the aurora heatings during storm time, this can create smaller circulations, and then the molecular rich air can be generated in the aurora heating region, and then they will move equatorward, push the O over N2 ratio peak into the subaurora region. Here I'm just showing you an example of the quiet time. This is during January, so it's a northern hemisphere winter. We can see that during quiet times, we have a higher O over N2 ratio in the northern hemisphere, exactly due to the reason I just mentioned. When we have a geomagnetic storm going on, and that can perturb the O over N2 ratio and push the peak O over N2 ratio to subaurora region here. And at a higher latitude, this is what we, this is the region where we will see the negative phase in the ionosphere storm. Now, this is opposite to what I just talked about of moving the ionosphere away from the neutrals. In this case, we are heating the thermosphere. So we are pushing the neutrals to higher, especially the molecular rich neutrals, to higher altitude. And then they can be more efficiently recombine or affect the recombination of the O plus there. Okay. So the last I want to talk about thermosphere cooling due to the NOs during storms. The left panel shows the NO flux during quiet time in comparing with the storm time on the right. As you can see it from here, during storm time, we have a lot of NO that's generated in the aurora zone, and then they can be propagated to lower latitude due to those equatorial winds. And this NO radiative cooling is a very efficient way of cool the thermosphere. Okay, due to the time limit, I'm just jumping to the summaries. So in this tutorial, I basically talk about the geomagnetic storm as the most severe geomagnetic disturbances of the Earth's magnetosphere. Hundreds of gigawatts of energy flow into the IT system. Most of this energy deposits themselves in the aurora zone, but then their impact is far-reaching. They affect the low and mid-latitude ionosphere and thermosphere by changing its temperatures, the wind circulations, and the composition. There are many other smaller and mesoscale features during storms, but not mentioned here in this tutorial, such as the traveling ionosphere disturbances. You will hear a lot about the TIDs in the CEDAR meeting. I want to end the presentation with the GDC mission. Steve mentioned the GDC mission in his talk, but because the GDC is especially concerned about how the complex IT system will respond to the forcings from both above and below. So I think it's very important to have this showing here, and really looking forward to see the GDC data in the next a few years. Thank you.
Okay, thank you very much, Shasha, for that excellent talk. We're running a little behind, so we have time for one question. So our most upvoted question on Slido right now is, why is the Peterson conductivity related collision frequency often referred to as the ion neutral collision frequency, but the Hall term is not?
So the question you asked is the why the Peterson conductivity is more important for joule dissipation. That's my understanding, right?
That may be the point of the question, yeah.
Okay, yeah. So if you think about the equations of the joule heating, that is the sigma E dot E, right? So the current and the electric field needs to be in the same direction. And the definition of the Peterson current is that this current is in the direction of the electric field. So that's why when we talk about joule heatings, most of the time we were talking about the Peterson current.
Okay. All right. Thank you very much, Shasha, again, for your talk. So we're running a little behind schedule, so we're going to reduce our break to 5 minutes. So we'll see everyone in 5 minutes from right now. Okay, so welcome back from our first break. During the first few talks, we had a couple comments about audio being quiet. Our recommendation for the best audio would be to use headphones. So with that said, we're going to continue on to our next talk. Our next talk is by Christopher Heel. Christopher is a research associate at Embry-Riddle Aeronautical University. He earned his PhD in 2015 from Embry-Riddle Aeronautical University, where he continued as a postdoc and then a research associate. He predominantly studies the generation, propagation, and dissipation of gravity waves in the Earth's atmosphere using high-resolution large eddy simulations. In particular, his current interests include convective wave generation from large mesoscale convective systems, MCS, over the Midwest US and their effects on the upper atmosphere and ionosphere, as well as secondary wave generation from mountain wave breaking. He's going to be speaking to us today about an introduction to gravity waves. So whenever we're ready, we'll go ahead and play his presentation.
Hello, my name's Christopher Heel, and I'd like to thank you all for coming to the talk today. I'd also like to thank Kumal for inviting me to give this talk. I predominantly study small-scale, short-period gravity waves using high-resolution modeling, and I wanted to talk to you a little bit today about gravity waves and hopefully give you an intuitive overview and understanding of their processes. So this is the contents of the talk here. I'll start by describing what a gravity wave is and then why we care about them. I'll then briefly go through how they are studied in terms of instruments and models. Then I'll go through the gravity wave life cycle and finish up with some of the current problems in gravity wave research. So let's start by talking about what is a gravity wave. Crudely put, they can be described as wiggles in the atmosphere. And in fact, this is what Colin Hines described them as in his original 1960 paper. They were irregularities and irregular motions in the upper atmosphere. And this can be seen from the figure on the right hand side, which shows a wind profile with altitude. There's a mean wind with wiggles or gravity waves superimposed on top of them. And this initial 1960 paper provided the framework and theory to study these wave motions. So gravity waves are actually driven by a balance of forces. They're created by perturbations to a stably stratified atmosphere, which are then restored to equilibrium by the forces of buoyancy and gravity. So the atmosphere is stratified by density, and what this means is that the density is constantly decreasing with altitude. So if an air parcel is lifted from its equilibrium position, it will find itself surrounded by less dense air, and then gravity will tend to pull that down back towards its equilibrium. However, it will shoot its equilibrium position, and then it will find itself surrounded by regions of denser air, and it will be driven back up by buoyancy, and you get an oscillatory motion. The energy from these oscillations are carried away in the form of waves, and these are gravity waves. And the figures in the bottom right here just show some indication of wave motions in the lower atmosphere. So for a more formal definition of gravity waves, we begin with the inviscid Navier-Stokes equation, which represent conservation of density, momentum, and energy respectively, with the energy partitioned into the internal energy and the kinetic energy. We then assume that the state variables are made up of a linear combination of a mean background state and a wave-like perturbation of the quantity. So you can see that our U vector here, which represents the wind, is made up of U, which is the zonal wind, V, which is the meridional wind, and W, which is the vertical wind. Then we also have the pressure and the density. So the overbar state represents the mean state, the background state, and the primed quantity represents the wave-like perturbation. And the wave-like perturbations are made up of some yet unknown function of altitude, or Z, and then a wave-like solution in x and t, which is given by the e to the I kx minus omega t. So we take these form of the state variables and then we plug them into the Navier-Stokes equations, do some algebra and rearrange, and we end up with the Taylor-Goldstein equation. And this provides a description of the vertical velocity amplitude of the gravity wave in terms of m squared, the vertical wave number. The solution to this is just a wave-like solution, e to the I kx plus or minus mz minus omega t plus z over 2h, and we'll talk about that term later. But what is crucial is that these waves are dispersive and they have a dispersion relation, which describes how the wave parameters relate to each other and to the background atmospheric parameters. So just to describe this in more detail, m squared represents the vertical wave number squared, k squared represents the horizontal wave number squared, n squared is the buoyancy frequency of the atmosphere squared, which is proportional to the density and temperature gradient of the atmosphere. Omega is the ground relative frequency of the wave, and U bar is the local horizontal mean wind. So the denominator of this equation, the omega minus uk, is known as the intrinsic frequency, and this is the frequency of the wave in the frame of the relative mean wind. Cp is the normal definition of the phase speed, omega over k, and then you have the group velocity, d omega by dk, or dm for the horizontal and vertical group velocities respectively, and this describes the direction of propagation of the wave packet and also the energy propagation direction. It's key to note that it's this dispersion relation that makes a gravity wave a gravity wave. If you see a gravity wave in the atmosphere, it has to fit this dispersion relation in order to be a gravity wave. So this really is a key concept in describing gravity waves. I'll now describe some of the important characteristics for gravity waves. Firstly, the amplitude grows exponentially in altitude. So the density decreases with altitude, and gravity waves conserve energy and momentum, which is proportional to this decrease in density. Thus, the amplitude of the wave must increase with altitude. Also, gravity waves are bound by the buoyancy frequency of the atmosphere. So the buoyancy frequency is the natural oscillation frequency of the atmosphere if a parcel is lifted vertically from equilibrium. And it's proportional to this theta term, which is the potential temperature, but it's essentially equal to the proportional to the gradient of the density. The n squared term gives information on the stability of the atmosphere. So if n squared is positive, the atmosphere is stably stratified. If it's equal to 0, it is neutrally buoyant, and if it's less than 0, then the atmosphere is locally unstable. It also represents the highest frequency at which a gravity wave can exist, and on average is about 5.5 minutes for the atmosphere. Also, the wave parameters, in particular the frequency, can determine the propagation angle of the wave to the ground. So if the frequency is high, then you tend to have more vertical propagation of the wave, and if the frequency is low, then you have more horizontal propagation of the wave. Another important characteristic is that the phase velocity of gravity waves is perpendicular to the group velocity. So as the whole packet moves upward in the direction of the group velocity, denoted by the red arrow, the vertical phases are actually moving downward in the direction of the blue arrows. So here's a schematic representation of wave propagation. You can see this wave is propagating up and to the right in the direction of the red arrow, or the group velocity, where the phases are moving down and to the right in the direction of the phase velocity, the blue arrow. There's also a set of polarization relations which define the amplitude and phase relations between the atmospheric parameters for gravity waves, and you can see that these are often dependent upon the relative values of k and m, so the horizontal and vertical scales of the wave. Gravity waves can also be highly dispersive, and you can see that it's very hard to distinguish a single packet in some cases. You can see in this figure here that by 100 seconds, which is on the x-axis, the packet actually spans 100 kilometers in depth. So it's difficult to define a single wave when you have it spread out over the whole atmosphere like this. So when we're talking about gravity waves in the atmosphere, we expect them to have horizontal wavelengths between 10 and 1,000 kilometers, and vertical wavelengths between 5 and 40-ish kilometers. Their periods are likely to be bound by the buoyancy frequency, so a few minutes at the low end to several hours in the high end. It's also crucial to note that the gravity wave spectra will vary considerably with altitude because of variations in the background wind and temperature structure, which will filter these waves as they propagate upward. So why do we care about gravity waves? Well, gravity waves are a primary mechanism for carrying energy and momentum away from a source region in the lower atmosphere and distribute it throughout the rest of the middle and the upper atmosphere. So this Fritz and Vincent paper in 1987 states, our analysis reveals that over 70% of the momentum flux and inferred zonal drag was due to gravity waves with observed periods less than 1 hour. So how does it do this drag on the atmosphere? Well, this is done by this term, the momentum flux divergence or body forcing. So the momentum flux is highlighted in red, and this is conserved for a non-dissipating gravity wave. But when a gravity wave dissipates, it deposits its energy and momentum into the background flow and will accelerate or decelerate the mean flow locally. Equally, from a divergence of heat flux or from viscous damping, it can create a heating or cooling of the atmosphere and change this temperature structure also. So through the deposition of its energy and momentum, gravity waves can influence the thermal structure, transport constituents, provide mixing and circulation of the atmosphere through these dissipation and wave-breaking processes. One consequence of this is the quasi-biennial oscillation, and this is a 2-yearly reversal of the mean zonal winds in the tropics caused by directional forcing of gravity waves over time. Another is the general circulation of the atmosphere. So gravity waves contribute highly to the Brewer-Dobson circulation, which is a summer to pole circulation in the stratosphere, and also primarily drives the mesospheric circulation. So under thermal conditions, you'd expect the summer mesopoles to be the warmest part of the mesosphere, when in fact it's the coldest. And this is due to gravity wave forcing, which generates a mean circulation with a lifting of the air and adiabatic cooling of it at the summer pole. But fundamentally, we cannot accurately predict weather and climate without understanding gravity waves. Gravity waves are unresolved in general circulation models, and they need to be parameterized. And these parameterizations use very simplified physics, which have a lot of problems. For example, they constrain all gravity waves to the grid cell that they're generated in the model. They have instantaneous propagation from their source to their demise. They have no consideration of nonlinearity, and they also essentially tune the parameters of the sources so that the observations look right rather than based upon physical arguments. So how do we observe gravity waves? One method is in situ measurements from aircraft, balloons and rockets, and these will typically measure the state parameters such as the pressure, the temperature, the atmospheric constituents. Another method is imagers. And these imagers often measure the perturbations to the air glow in the upper atmosphere through the hydroxyl bands at 87 kilometers, the atomic oxygen green line at 95 kilometers, and the atomic oxygen red line between 200 and 250 kilometers. LiDAR is another popular way of measuring gravity waves, and this provides a altitude time profile of the wind's temperature and density in the stratosphere and mesosphere, depending on the type of LiDAR that you're using. Radars provide another popular measure of gravity waves. This can be done through various radars, and you can measure from the troposphere up into the ionosphere, in fact, using these different radar methods. Satellite is also really useful for looking at global coverage of gravity waves. However, you struggle to get good temporal resolution because of the satellite passes and how fast they're passing over. So this image at the bottom shows the AIRS imager upon the NASA's Aqua satellite, and you can see these gravity waves in the stratosphere over the United States. The total electron content can be measured by GPS and GNSS networks, and this will measure a manifestation of gravity waves in the electron density. And these are actually known as traveling ionospheric disturbances, but they are manifestations of gravity waves in the ionosphere. So when we talk about models, there are three main types of models. The first are local models, and these are concerned with explicitly resolving all of the gravity wave processes and the turbulence processes as well. So the direct numerical simulation will resolve all scales down to the smallest turbulence scale, whereas a large eddy simulation will typically parameterize part of the turbulence spectrum. So these are very high resolution localized runs with resolution in the order of meters and temporal resolution of seconds and a range of seconds to a few hours. The second type of model are numerical weather prediction models. These are your typical forecast type models. These are much larger in scale and as such have larger resolution. So their resolution is the order of tens of kilometers and a temporal range is approximately days at 3 hourly intervals. So these will resolve part of the gravity wave spectrum, but also another part below the resolution of the model will need to be parameterized. And parameterization is just a simplified description of the physics and how they will affect the atmosphere in general. The third class is a general circulation model. This is a large-scale global model concerned with predicting climate. The resolution of these is much lower, so they are typically an order of a degree, and their temporal range is years. So in these models, gravity waves are almost exclusively parameterized, and these parameterizations are incredibly simplified. So all gravity waves are confined to the single cell. The propagation is instantaneous, and also there's no nonlinearity included in these parameterizations. You need to specify the source spectrum as well, which at the moment is not particularly well constrained. So there's a lot of problems with these gravity wave parameterization, and it's an ongoing area of research. So we know that gravity waves are born from displacements of the atmosphere at periods greater than the buoyancy frequency. But what are some of the main sources? So one of the main sources, in fact, is topography. So as the wind flows over mountains, it is lifted, and as it's lifted, it gives rise to these gravity waves, these propagating gravity waves. And you can see an example of that in the figures on the right. A second large source is convection, so this is from lifting of the air from thunderstorms, hurricanes, tornadoes, and any large-scale storm system really. You can see in this figure these concentric waves in the mesosphere in the black and white image with the thunderstorm superimposed in colors and below. Some other sources, geostrophic adjustments, are basically when there's an imbalance in the flow and the imbalance acts to correct itself, the energy from that correction can be turned into gravity waves which propagate away. Also natural hazards such as tsunamis, volcanoes and earthquakes can cause gravity waves, as well as man-made sources such as bombs, rockets and mining explosions. So let's talk a little bit more about mountain waves. So if we imagine a steady horizontal flow over a mountain where the mountain height profile is given by h of x, we know that the flow must be parallel to the mountain, and so the air is lifted over the mountain, and the vertical velocity can then be described by the horizontal flow times by the gradient of the mountain profile itself. And it's this lifting, this vertical lifting of the air, which gives rise to the gravity waves. There's two things to note about mountain waves. Firstly, they're stationary, and this means that they have no ground relative frequency. You'll see their phases do not move over the mountain. Secondly, a mean wind must exist at all altitudes for them to propagate. So if that wind goes to zero at some altitude, then the wave will cease to exist and actually be critical level filtered and absorbed into the mean flow. So I'd just like to show this 3D mountain wave simulation in WRF from Chris Cruzy. Here we have a constant background wind of 30 meters per second at the source, and then we have a mountain which is 200 kilometers wide and 1,000 meter tall and defined by a simple cosine function. The left hand panel here shows the distance on the x-axis and the height on the y-axis, and you'll see this gravity wave start to propagate. You notice its phases are not moving, they're constant, and then the wave will break at some altitude and start to dissipate away. So I'll move on to talk about convectively generated waves. There are three main proposed mechanisms for these generations. The first is by latent heating. So as the moist air in a thunderstorm is converted to rainfall, this generates a latent heating which provides the energy to generate the gravity waves. Second is the mechanical oscillator effect. So as the air in a thunderstorm rises, it will impinge on the tropopaules and start to oscillate about the tropopoles because it can't rise into the stratosphere, and this oscillation will generate gravity waves. The third is the obstacle effect, which suggests that this thunderstorm blocks the mean flow, which then has to be redirected over or around the thunderstorm, and this lifting generates gravity waves. In reality, all three of these mechanisms are present and linked via the nonlinear advection term in the Navier-Stokes equations. So I'll just provide a simulation here of a convectively generated wave from a single plume. So on the left hand side you've got a horizontal slice of the atmosphere at z equals 85 kilometers, and on the right hand side you have the zonal distance on the x-axis, the altitude on the y-axis, and you'll have this blue line represents the mean wind. So you'll see, if you look at the right hand figure, you'll see this plume go off at the bottom, and then the gravity waves will start to propagate up and fan out. There'll be a preferred direction, and then eventually you'll get this wave break-in form, which you can see in the left and the right hand figure, which then propagates around the arc of the concentric gravity wave generated by the convection. So the previous simulation was for a single convective plume, and here's an entire storm. So in the top left you have the precipitation rate coming from the thunderstorms, and in the other grey figures you have the gravity wave response at different altitudes, so 15 kilometers, 55 kilometers, 70, 100 and 130 kilometers, and you can see how complex this wave field becomes as you have all the multiple plumes from the waves, from the storm generating waves, which then interact, and you get a lot of wave breaking and merging of phase fronts and interference between the gravity waves as they propagate up into the atmosphere. So this figure from Hoffman et al. In 2013 shows the distribution of gravity wave sources across the globe. This is taken using the AIRS imager and measures the sources in the stratosphere. Each of the panels in the figure represents a collection of months over the year, and this is for the daytime pass. So you can see particular hotspots over the world. So for example, in the tip of South America, over the Himalayas and Northern Europe, you get these sources from mountain waves, essentially, and you also get these convective sources associated with the storm tracks and also over North America. One problem with these sorts of climatologies is that they are limited to the time of day, or they're biased by the time of day with which the instrument takes the measurement, and also by the biases in the instrument itself and which portion of the gravity wave spectrum it is sensitive to. So now let's talk about the life of gravity waves. So gravity waves, when generated from their sources, they propagate into a varying background atmosphere at a variety of angles. And the distance that they can travel depends upon three parameters. First, the wave parameters themselves, i.e. the wavelengths and the frequencies. Secondly, the amplitude. And thirdly, the ambient atmosphere, so how the winds and temperature vary along the wave propagation path. And these varying atmospheric conditions can have three main effects on the gravity waves. That is refraction of the waves, reflection of the waves, and ducting of the waves as well. So first let's talk about refraction. Both the wind and temperature act to refract the wave. So if we look at the dispersion relation on the left hand side, you can see you have this n squared term and the u bar term. The n squared is proportional to the temperature gradient, and u of course is the mean wind. So if we assume that these background wind and temperature is varying with altitude, i.e. a function of z, then we end up with a vertical wave number which is also a function of z. So the vertical wavelength is changing with altitude dependent upon how n and u bar change with altitude. So how does this work? Well, if the wind or n increases with altitude, then the vertical wavelength will decrease with altitude, and this will make the wave propagate more horizontally. Vice versa, if the wind or n decreases with altitude, then the vertical wavelength will increase and the wave will travel more vertically. So here is just a schematic showing what would happen. So here we have a wave propagating up and to the right, and you can see as it encounters this wind which is increasing in the direction of wave propagation, then the wave is refracted to smaller vertical scales and more horizontal trajectories. So in this case, we have a wind which is opposing the wave propagation direction and increasing with altitude. And here the wave is refracted to larger vertical scales and starts to propagate more vertically, as denoted by the red arrow in the group velocity. So now let's look at reflection. If you examine the dispersion relation again and pull out that k-squared term, there could be a case where the numerator and the denominator of the dispersion relation are equal to each other. And this essentially means that the intrinsic frequency of the wave is shifted to the buoyancy frequency of the atmosphere. And when that happens, the vertical wave number goes to 0 and the vertical wavelength goes to infinity. And this is known as a turning point level where the wave will reflect. Above this level, the wave is evanescent and cannot propagate. So just to give you a more intuitive visual idea of how reflection works, imagine you have a gravity wave which is propagating in the direction of the red arrow upward and to the right, and it's propagating into this opposing mean wind which is increasing with altitude. So as it propagates, it will be refracted to larger vertical scales and larger vertical trajectories, and eventually it will hit a point where the intrinsic frequency of the wave is equal to the local buoyancy frequency of the atmosphere. And here it cannot propagate upward anymore. The vertical phases are completely vertical and the wave will reflect. As it does so, it will then go downward and to the right and will go into a decreasing opposing mean wind and will then refract to more horizontal trajectories. So this is a figure from a simulation I ran of a packet reflecting, and it's evolving from top left to bottom right here. And the packet is propagating up to the right, and the arrows and the Gaussian shape represent the mean wind. So you can see that what happens is that when the wave packet hits the reflection level, you actually get, in reality, a reflection and transmission of the wave. And this occurs because the wave packet is actually a spectrum. It's not a single frequency and wave number, and only part of that spectrum meets the condition to reflect, whereas another part of it will actually not reflect and be transmitted up into the atmosphere. So in this respect, the reflection layer can actually act like a filter for waves, allowing certain frequencies and wave numbers to transmit rather than be reflected. So this can lead to the concept of ducting. If you have two turning point levels in the atmosphere, with a region in between where a wave can propagate, the wave can become ducted. So let's look at how this works. Imagine you have an instant wave coming up to a reflection level or a turning point level. Then, as in the previous example, you'll get a partially reflected wave and a partially transmitted wave. But as that transmitted wave hits the second turning point level, it will be reflected again and then will bounce off the first turning point level, and you'll get this stuck wave which just bounces between these two turning point levels. And what that actually allows for is the facilitation of long-range propagation of waves that normally would not be able to propagate large horizontal distances. It's also key to note that these ducts are leaky, so you'll get energy leaking out of these ducts at each time the wave reflects off one of these layers. So this is just a simulation of a leaky duct that I performed. The wave is propagating upward and to the left initially, and the black lines represent the duct boundaries. So you'll see as the wave propagates, you'll get reflection and transmission each time that it hits one of those black boundaries, and part of the energy will leak from that duct up into the upper atmosphere. But so this is a method by these short period waves can actually travel large horizontal distances and distribute their momentum and energy far away from the source region where the wave itself was generated. So now that we've talked about the life and the propagation of the gravity waves, let's talk about their death. So in general, there are three main mechanisms that waves can end their life. Firstly, critical level filtering. Secondly, by wave breaking. And third, by viscous dissipation. It's key to note in all three of these cases, either part or all of the wave energy and momentum will be deposited into the mean flow, and all three of these mechanisms are actually likely to generate secondary gravity waves as a result. So let's start by talking about critical level filtering. So if we examine that dispersion relation again, there's a point where the denominator, this omega minus uk, can go to 0. And when it does so, the vertical wave number goes to infinity because you're dividing by 0. And so the vertical wavelength actually goes to 0. This is known as a critical level, and the wave is absorbed into the mean flow. In reality, this actually happens where the phase speed of the wave, omega over k, is equal to the mean flow. So if you get an altitude level where the phase speed, the horizontal phase speed of the wave, is equal to the mean flow velocity, then this will happen and the wave will be critical level filtered. So this is another simulation similar to the reflection one, except this time the mean wind is in the direction of the wave propagation as opposed to opposing it. Again, we're evolving from top left to bottom right. So you can see as the wave propagates up and to the right, it encounters this increasing mean wind and it starts to be refracted to smaller and smaller vertical scales, and eventually it hits this critical level where the mean flow is equal to the phase speed of the wave, and the wave itself is absorbed into the mean flow and will actually accelerate the mean flow here. So now let's go on to talk about wave breaking. So if you recall, a wave's amplitude will grow with altitude as it propagates upward due to the decrease in background density. But of course, the wave's amplitude can't increase forever. And eventually, the wave amplitude will grow so large that the wave will steepen, and what will happen is the peak of the wave, essentially the horizontal perturbation velocity, will overtake the phase speed of the wave. So the top of the wave sort of overtakes itself and you get this breaking of the wave, this overturning of the wave, and this is known as the saturation point. And the saturation point occurs when the horizontal perturbation velocity is equal to the wave's intrinsic phase speed, as denoted by the equation in the bottom left. So here is just a simulation of this effect, and the wave will start in the bottom left and propagate upward and to the right, and you will see from the color bar on the right hand side the wave is increasing in amplitude as it goes up, and as it gets up to the top here it will start to steepen, and then the wave will cascade into breaking as it meets that condition where the phase speed, intrinsic phase speed, is equal to the perturbation velocity. So another way of describing instability in the atmosphere in general is the Richardson number, which is made up of the buoyancy frequency on the numerator and the wind shear in the denominator. And if the Richardson number is less than a quarter, this implies unstable conditions. The Richardson number describes two types of instability. The first is a convective instability driven by if n squared turns negative. And what this implies is an inversion of the density, where you have higher density over lower density, and the atmosphere will become unstable in order to correct itself. The second is shear instability, which is when the vertical wind shear is large enough that it overcomes the tendency of a stratified fluid to remain stratified, and then Kelvin-Helmholtz instabilities and vortexes will form as shown in the bottom right hand figure here. So the n squared and the shear term that make up the Richardson number have both mean state and also wave components as well, and you can see they're dependent upon the amplitude but also the vertical gradient of these parameters, which will bring out the m, or the vertical number, wave number, when you differentiate. So both of these terms will be proportional to the amplitude and the vertical wavelength of the wave. So if you get wave steepening, you're going to cause these larger temperature gradients and shears, which can drive the Richardson number to instability, but also shortening of the vertical wavelength leads to larger temperature gradients and shears, which again can drive the Richardson number to become unstable. The initial break-in scales are roughly proportional to the depth of the unstable region, defined by a region where the Richardson number is less than a quarter. So I'll just show the simulation here. On the left-hand side you have the temperature perturbation of the wave as it propagates upward. On the right-hand side you have a vertical cross-section on the white line, which shows three lines. The blue line is the wind, the purple line is the temperature, and the red line is that Richardson number. So as the wave becomes steeper, the Richardson number approaches the yellow line, which represents the unstable point, and eventually the wave will become unstable, as you see there, at about 110 kilometers, and that is bounded by where the temperature gradient is maximum, as denoted by the purple line, and at the bottom end by where that wind gradient, the wind shear denoted by the blue line, is also maximized. So from here you can see on the left hand side that the wave becomes unstable, will break and cascade into ever smaller and smaller turbulent scales, which will then be dissipated by the molecular viscosity when they get to a certain small scale. So now let's talk about viscous dissipation. So kinematic viscosity and thermal diffusivity increase exponentially in the atmosphere, and the values become significant in the thermosphere. So you can see the kinematic viscosity here on the left and the thermal diffusivity on the right, and they're both inversely proportional to the density, which decreases with altitude. So the amount of dissipation that occurs for a given gravity wave is dependent upon two factors. Firstly, the magnitude of the local viscosity, and secondly, the vertical wavelength of the wave. So you can see from the diffusion and heat equations here that they're proportional to the second derivative of z, which brings out this m squared term, which is the vertical wave number. So what this really means is that viscosity will act to damp small vertical wavelengths more rapidly than waves with large vertical wavelengths, and this translates into the fact that you'll have smaller vertical wavelengths dissipating lower in the atmosphere, whereas larger vertical wavelengths can actually propagate higher into the atmosphere before they dissipate. So if you look at a vertical wave number spectra with altitude, you will see ever increasing vertical wavelengths as you go up into the viscous regions of the atmosphere. So actually all waves die from viscous dissipation eventually. If you remember with critical levels, we said that they're refracted to increasingly small vertical wavelengths and then absorbed into the mean flow. But from the previous slides we learned that viscous effects act to dissipate waves stronger if they have smaller vertical wavelengths. So what's really happening here is they're refracted to smaller vertical wavelengths. Viscous dissipation is becoming stronger and dissipating these waves. Secondly, waves that break will cascade through turbulent processes to smaller and smaller scales, and then eventually they'll get small enough that again viscous dissipation becomes strong and will dissipate these waves. And thirdly, waves that survive critical level filtering and breaking will propagate up into the thermosphere, where the molecular viscosity and thermal diffusivity is very, very large, and they will just be dissipated naturally. And typically the ceiling on this is around 300 kilometers. It's also key to note that dissipation is accompanied by the momentum and heat flux diversion, or the deposition of the energy and momentum, and this can create mean flow forcing and heating or cooling of the atmosphere, and it can also, as a third process, generate secondary gravity waves. So secondary waves can be created by two main mechanisms. The first is the linear response, and this occurs from a packet scale dissipation, which leads to a body forcing over the packet scale and dissipation period and generates larger, longer period secondary waves. So you can see this wave packet evolving from left to right. The amplitude of the wave becomes smaller and smaller as time goes on. The mean flow is forced, as denoted by the blue arrow, and the wind is accelerated in the direction of the wave, and then these secondary waves are generated which have longer periods and larger scales than the original. Second is the nonlinear response, and this occurs from wave breaking and wave-wave interactions, and these create very localized transient forcings which generate secondary waves which are actually smaller and higher frequency than the original breaking wave. So here is just a simulation of a secondary gravity wave generation by a breaking mountain wave. So you'll see this wave propagate up. It's actually hitting a critical level at about 90 kilometers. 80 kilometers, and then you see this wave breaking, these small scale structures form, and then these secondary waves appear above 100 kilometers, and those actually break again at larger scales and generate even further waves, such as tertiary and even higher order waves as well. So I'll finally talk about some of the current problems in gravity wave research. The first one is still having a good description of the source distributions, their intermittency, and what spectra of waves are generated from these sources. in general. This is still not well known. We have these satellite studies, but again, they suffer because of the temporal resolution of satellite images. They move over so fast and they sample a single point maybe once or twice a day, so you don't get any sense for the evolution of these sources. Secondly, because gravity waves are deep, i.e. they occupy almost the whole depth of the atmosphere from the ground to the thermosphere, it's very hard to measure the distribution of their momentum and energy and how they deposit those throughout the atmosphere. You really need a large suite of instruments which can measure the whole depth of the atmosphere to do that. Thirdly, how do these waves evolve non-linearly? So most of the theory is a linear theory, and we don't really have a very strong understanding at this stage of how non-linear evolution, such as wave-wave interactions, wave-mean flow interactions, turbulence generation, and a secondary wave generation work, and what spectra that they produce. They can't be well predicted at this stage. Fourthly, what are the effects in the ionosphere? To do this, you need to couple the neutral atmosphere with the ionosphere, and we know that there's these traveling ionospheric disturbances, a subset of which corresponds to the manifestation of gravity waves in the ionosphere, but they can also possibly produce effects like the ion outflow and also seeding of things like equatorial spread F. But really, we don't know. This is a topic of research that is only beginning to be fully explored. And all of these really feed into the parameterization in general circulation models, which at the moment are poor. They need to prescribe a source distribution throughout the atmosphere and also an intermittency, which there's been some strides into this, but in general it's still not well understood. Again, you have instantaneous propagation of these waves from their sources to the wherever they deposit their momentum, which is crudely described by linear theory. There's not any consideration of non-linearity in these parameterizations, and also they're confined to a single column. So if a gravity wave is launched within a single cell in the GCM, then it stays within that cell, and you don't get any description of the horizontal propagation of these waves. So these are all big problems that need to be solved in gravity wave research, and hopefully upcoming missions, for example the ALL mission, which is going to look at the mesosphere, the temperature of the mesosphere using AMTM imagers from the International Space Station, might start to answer those questions, along with satellites which are measuring the thermosphere, such as ICON and GOLD, the thermosphere and the ionosphere. And really you need sort of systems level approaches to these problems. So you need a suite of instruments in conjunction with models which can span across multiple scales, from the global scale down to the very smallest turbulence scales, in order to describe these processes. So there really is a lot of work to be done, and I hope that this talk has given you some interest in gravity waves, and perhaps you can pursue and solve some of these problems. So I thank you for listening to this talk, and I'd like to leave you with this wonderful simulation by Hanli Liu et al. In 2014. And this is from the Wacom GCM, and this is a high-resolution GCM run with part of the gravity wave spectrum resolved. And you can see how complex this wave field is over the globe, and this really is just a beautiful simulation that shows how much there is to understand about gravity waves in the atmosphere. So I thank you for your time and welcome any questions.
Thank you, Chris. That was a wonderful and very interesting talk. We'll move on to Q&A session for Chris now. We have many interesting questions. So the first question for you, Chris, is what distinguishes a gravity wave from a planetary wave?
Thank you for the question. Predominantly, it's the scale of the wave. Gravity waves tend to be smaller scale, up less than sort of 1,000 kilometers, and have much shorter periods, less than a few hours. Planetary waves are much bigger in scale, as their name suggests. They can cover the whole planet, and actually planetary waves are sort of a catch-all term for a number of large-scale waves, such as Rossby waves and thermal tides and such. But another big distinction is the sources of those waves and also the restoring force. The restoring force for gravity waves is buoyancy and gravity, but for these larger scale waves, the Coriolis force plays a significant role as well. So it's a combination of the scale, the restoring force, and also the source of the waves itself, which differs between gravity waves and planetary waves.
Thank you, Chris. We have another question as well for you. At what altitude gravity waves affect the upper atmosphere dynamics directly and indirectly?
So they actually affect the whole depth of the atmosphere. This depends upon what the source is and also the time of year, but they can affect the stratosphere, in which they drive things like the quasi-biennial oscillation and the Brewer-Dobson circulation, but they also have this very predominant effect in the mesosphere. And I think that's where the gravity waves of the scales that we're talking about are most significant, because it takes those are the most vertically propagating waves, and they're the ones that can get up to those heights. So in terms of where they dominate, certainly the mesosphere, the mesopoles, and the lower thermosphere is where they become very significant.
Thank you, Chris. I would just go to one quick question again. What is the main mechanism that keeps gravity waves from penetrating the E and F regions?
The main mechanism for that is just the dissipation by the molecular viscosity. So certain waves can still get up and influence that region, but that again depends on the scale. If you have a large vertical wavelength wave, then it can propagate up into about 200 and 250 kilometers. But there, the viscosity is so strong because of the low density that the wave just dissipates and is smoothed out. So yeah, they can't really get much higher than that, but they can couple to things like traveling ionospheric disturbances, which can continue to propagate in those regions.
Thank you, Chris. I think we'll wrap up questions for you for now. We will be sending you the rest of the questions later to answer. We'll move on to the next speaker. And our next speaker is Ruth Lieberman. She's a research scientist at NASA Goddard Space Flight Center. Ruth earned a PhD in atmospheric sciences from the University of Washington. She was a postdoctoral researcher with the Upper Atmosphere Research Satellite mission at the University of Michigan. In 1997, Ruth joined Northwest Research Associates in Boulder, CO, and migrated with their dynamics group to GATS in 2012. From 2016 to 18, she was the aeronomy program director at National Science Foundation. Since August 2018, she has been a research scientist in the heliophysics division at Goddard Space Flight Center. Ruth's work focuses on observation and observation-driven modeling of tidal and planetary wave dynamics. Today, Ruth will be talking about atmospheric tides, planetary waves, and vertical coupling. So with that, Ruth, whenever you're ready, please go ahead. Thank you.
All right, I'm here. Can everybody hear me? Have I unmuted? All right, I'm assuming the answer is yes. So with that, thank you very much for that wonderful introduction. Thank you to the student committee for inviting me to speak here today. It's a real pleasure to be here with everybody, even virtually. And I also want to thank you all for scheduling me so appropriately after Chris, because he gave such a terrific introduction to gravity waves and a nice little segue into the whole discussion of planetary waves. So I will head off to the next slide, which my computer is not allowing me to advance. And the motivation for many of the things I'm going to be talking to you about are what we now know from 2 decades of research to be a lot of evidence that the quiet time ionosphere is influenced by waves below 100 kilometers. And tides turn out to be particular enablers of coupling of the lower atmosphere to the upper atmosphere. And one of the ways in which they do this is through their interaction with planetary waves. So by the time I finish this talk, I hope that I will have provided some appreciation for what are tides, what are planetary waves, how they can couple to each other and potentially reach the ionosphere. So it's really going to be a very simply laid out talk. I'm going to start with tide and planetary wave basics, and show some examples of vertical coupling and talk about observational requirements and exciting new opportunities. So to begin at the very beginning, tides are global scale oscillations with a period that is an integer fraction of a solar day, of any kind of really rotational period of a celestial body, but here we're talking about Earth tides. So the origin of solar tides, and I'm referring in my talk to thermal tides, the origin is solar heating. And this function, which is a half sine wave, a daytime half sine wave, breaks down into several harmonics, primarily a diurnal harmonic, 24 hours, and a semi-diurnal, 12 hours. And there's also an 8-hour and even a 6-hour harmonic, but I will not be talking too much about those today. And tides, the way tides force the atmosphere, the way the solar heating forces the atmosphere, is through absorption of the irradiance in various parts of the atmosphere, and through the through the transmission of the heating into latent heating, into convection. So I hope the arrow is visible here, because that's the only pointer effect that I have. Near the surface, we have heating, absorption of solar heating in the near IR by water vapor, which is a fairly smooth and uniform function primarily at low latitudes. And it uniformly maximizes at 12 o'clock noon over much of the globe. And its magnitude is on the order of 10 milliwatts per kilogram. And this function maximizes at the surface and in the lower troposphere. Chris spoke about deep convection. There is a strong diurnal cycle that goes with the sun of heating up the continents. And so over the continents, we have very large scale daily convection patterns that maximize heating at around noontime, and there are secondary maxima over the oceans, which actually maximize near midnight. And this function, this diurnal heating function, the latent heat release function, is about 1/3 of the solar heating function. So it's like 3 or 4 milliwatts per kilogram. And in the stratosphere, we've got the well-known ozone heating that that we hear so much about, and that's roughly about 1/10 of a watt per kilogram. And higher up in the upper atmosphere, we have heating. We have UV heating of the O2, dissociation, and photoionization at even higher altitudes. So these all create diurnal cycles of heating in the atmosphere. So I'm now going to talk a bit about the behavior of tides and planetary waves, because it turns out that tides and planetary waves, as Chris sort of hinted at, they share many characteristics. But fundamentally, the basis for their sameness is that they are all, it's what you get when you cast the Navier-Stokes equations on a sphere in a frictionless atmosphere with a resting background state. So doing this leads to a system of equations that looks like so. It may look a little bit different from what Chris showed, but the terms are pretty much all the same. We have local accelerations that are balanced by a Coriolis force. Those are the terms that are multiplied by F. And pressure gradient forces that have to conserve mass. This is the continuity equation. And the bottom equation is the first law of thermodynamics, perhaps not as familiar as we're used to seeing, but this is internal energy. This phi term is proportional to temperature. So it's the internal energy, which is offset by the work done by or on an air parcel, which in this framework of it, which in this spherical framework I'm speaking of, the work is primarily done through vertical motion of the parcel working against gravity and buoyancy, exactly like Chris spoke to us about earlier. And the difference between the work and the internal energy is the diabatic heating. And you may run across these equations in other places referred to as Laplace's tidal equations. Okay, the spherical equations of motion on in a resting background state. So I consider this to be quite an eyeful, too much to process, really, too much to comfortably process. And so I find that it's easiest to understand what's going on if we can kind of plane things down to particular situations. And so the situation I'm going to plane down to now is the equator. So it is the equator, so we're going to knock off these Coriolis terms because they are functions of latitude and they are zero at the equator. And I'm also going to restrict the discussion at the moment to the semi-diurnal tide, whose frequency is twice omega. So if we look at that system, then it's a fairly straightforward system where the horizontal force restoring the motion is basically the pressure gradient force. So this is what the semi-diurnal tide looks like, and I want you to look at the equator here. And this is a calculation from a model, and it is by design showing a wave that is propagating westward in time. So how does the pressure gradient force work? It forces air down the gradient from high to low pressure. So if we go to a spot where the pressure gradient is maximal, which is at this zero pressure contour line, contours are pressure, the arrows are winds, then at this particular site, the pressure gradient force is blowing, if you will, or pushing air from high to low pressure, so from west to east. And so if that's the acceleration, then 1/4 cycle later, we expect to see the wind blowing from west to east, which indeed we do if we look 1/4 cycle upstream. So at low latitudes, the waves are basically restored by pressure gradient forces. And although my equations don't really explicitly show this, where the air is diverging at the surface, it will be filled in. This void will be filled in through vertical motion coming down from aloft. And so the semi-diurnal tide is then going to be characterized by vertical motions as well. And in fact, it will be characterized by a vertical, by oscillatory motion in the vertical, as well as in the horizontal. If we stick with the semi-diurnal frequency, but start moving into the latitudes where the Coriolis force counts, which is to say, as we start moving more poleward, when we reach the pole, the semi-diurnal frequency will be equal to the Coriolis frequency, or otherwise known as the inertial frequency. So as we move closer to the poles, we expect that there'll be a relatively weak pressure, there'll be weak pressure forces operating, because there really won't be any way for them to play any role if all the balance is going to occur between the local acceleration and the Coriolis force. And sure enough, as we go up to higher latitudes, we see that the pressure, semi-diurnal pressure attenuates. And the main thing fueling it is restoring it is the Coriolis force. The Coriolis force acts to the right of the motion in the northern hemisphere. And so at this particular location where we're seeing an east to west wind, the Coriolis force will turn the air parcel to the right, northward, and 1/4 cycle later, this upstream pattern with the northward wind is going to be occurring at the site where this acceleration took place. So these waves are called inertia gravity waves. They are gravity wave. They They have gravity wave dynamics very similar to, very much like what Chris Healy described to us, but they are also influenced by the Coriolis force. Now we're going to do the same kind of exercise, which is to say we're going to look at the way waves behave at low, middle, and high latitudes. And this time we're going to focus on the diurnal tide, which obeys all the same equations and all the same balances of forces and so on, except we now have a frequency of omega, not 2 omega. At the equator, it's still going to collapse into the same kinds of equations that we saw for the semi-diurnal tide. So since we understand tides so well now, let's go take a look at the diurnal tide. Well, it looks quite different from the semi-diurnal tide, but the same forces are still operating. Near the equator, where the Coriolis force is 0, we have the pressure gradient acting in equator to pole directions. In other words, it's forcing air from the equator. It's accelerating air from the poleward from the equator, and so one quarter cycle following this strong pressure gradient that we observe here, we're seeing southward flow in the southern hemisphere and northward flow in the northern hemisphere, responding to the pressure gradient. The inertial effect kicks in much sooner for the diurnal tide because the diurnal frequency equals the Coriolis frequency, not at the pole, but at 30 degrees. So already by 30 degrees, we're seeing this, we're seeing the Coriolis effects kicking in. And if we go to even higher latitudes, where the Coriolis force only gets stronger, we might start thinking that the Coriolis and the pressure gradient are going to start working more and more with each other. And that is characterized, I won't go so far as to say that the tide is exhibiting geostrophic motion, but we're certainly seeing some shades of it down here at the higher latitudes in the southern hemisphere, where the flow is parallel to the pressure contours, which is characteristic of a system in which the main forces operating are Coriolis and pressure gradient. And the air is flowing cyclonically around the low and anticyclonically around the high. So a couple of more words on vertical propagation. Chris kind of touched on this earlier. Vertical, especially when we talked about the difference, when he referred to the differences between planetary waves and gravity waves. Vertical propagation is basically going to occur when the motion, when the frequencies are, when the periods are faster than Coriolis periods. The Coriolis force has a tendency to pull motion into the horizontal plane, not only horizontal, but non-divergent. And so in order to effect vertical propagation, the frequency of the wave has to be relatively fast compared to it has to be faster than the Coriolis. For the semi-diurnal tide, this will be the case globally because, as we saw, the pole was where the inertial frequency occurred. So the semi-diurnal tide propagates vertically everywhere. So the semi-diurnal tide is one big, huge, gigantic, global scale gravity wave, inertial gravity wave. The tides, on the other hand, propagate vertically only to 30 degrees in a windless atmosphere. If the atmosphere has a background wind in it, then that can kind of shift things off the 30-degree latitude. You know, we can have some Doppler shifting of the, we can change the intrinsic frequency, and so it might wobble around 30 degrees. But the tides basically propagate mainly mainly up to the subtropical latitudes, and then beyond that they do not vertically propagate. And their main vertical wavelength is between 25 and 30 kilometers. Where they propagate, tides behave like internal gravity waves, just the way Chris described them. They amplify with altitude in order to conserve energy and to work against the decreasing density. So I just want to show some examples here. I apologize that I couldn't make these plots from real live data. They come from a model, but unfortunately, we just don't have data sources that cover tidal temperatures and winds. and both wind components all the way through the entire atmosphere, which is what I'm trying to show here. So I'm plotting temperature on the top and zonal wind in the center, meridional wind in the bottom. These are the diurnal tides in latitude and altitude going from the stratosphere up to the lower thermosphere. And even if all you notice are even if all you do is vaguely take in the contours and the colors, you will see that the diurnal tide very much is hugging the subtropical latitudes, and that it attenuates away from those latitudes, and that at those tropical latitudes it shows. I've plotted the tides at a fixed phase here, and so we see positive and negative centers of action that are amplifying with height. These are the wave effects, or these are how waves look when they're frozen in time, wiggles. And this is the amplitude of the semi-diurnal tides. It's kind of an analogous plot, but it's only amplitude because the semi-diurnal tide is propagating everywhere, and it has a very weak phase change with altitude anyway. And so you see that unlike the diurnal tides, the semi-diurnal tides are more global. And we have a view of the tides above the lower thermosphere, provided by the UR's windy instrument that sampled winds up to 300 kilometers. So between 90 and 110 kilometers, we still have a strong diurnal tide. And above that level, the semi-diurnal tide is kind of coming into play here. It's unfortunate that many measurement techniques for the thermosphere are sensitive to daytime-only emissions, and so it's been quite difficult to separate from observations alone the diurnal and the semi-diurnal tides between 100 and 200 kilometers. So that's kind of what I'm going to say for the tides, and I'm going to say a few more words about planetary waves. The only thing that really distinguishes tides from planetary waves is their fixed periods. The tides, as I've said, have periods that are integer multiples of 24 hours. But if we dare to think of waves that have periods of, say, 1.8 days or 2.2 days, or 3 or 4 or 5, these aren't tides. These are no longer tides, but they are they are planetary waves. So, and they are governed by the same forces that that describe the tides. So, and because we understand these forces so well, I invite you to I invite you now to imagine what a 2-day wave, for example, might look like. A 2-day wave just happens to be one of the free oscillations of Laplace's of this system of equations. So let's kind of imagine what a 2-day wave would look like. At the equator, we know that we're going to have basically just the pressure force restoring the motion. But in this case, the acceleration owing to the 2-day wave at the equator, we might expect it to not be quite so strong as that associated with the tides, because we've got something lower frequency going on here. We have a frequency of omega over 2. But still, at the equator, we expect to see internal gravity wave dynamics for a 2-day wave, and that is indeed what we see. At the equator, we have flow up and down that good old pressure gradient. At about 12 degrees, where the 2-day frequency equals the Coriolis frequency, we see we see that inertial effect coming in. We see the rotation of the wind occurring, and at the high latitudes, we expect the Coriolis force is going to be substantial. Is going to be at least 4 or 5 times stronger than the 2-day acceleration. And so at high latitudes, we expect to see something, sort of geostrophic-like. And we are seeing this. We are seeing flow parallel to the pressure contours, going clockwise around the high and counterclockwise around the low at the high latitudes, mind you. And so in fact, a wave like this is actually called a mixed Rossby gravity wave. gravity wave at the equator and Rossby wave at the higher latitudes. I'll define Rossby waves more fully in the next few slides. Let's consider a 5-day wave, which also happens to be a solution, a free wave of this system. So what do we expect? At the equator, we expect to see, as the periods of these waves start getting, planetary waves start getting higher and higher, in a windless atmosphere, we expect to see weaker and weaker tropical action going on here, because there is simply at the equator nothing that can balance the local acceleration in the absence of a Coriolis force. So for a 5-day wave, we expect weak pressure at the equator, and that most of the action is going to be occurring. Most of the action in this wave, the amplitude of the pressure amplitude and the winds, we expect that this is going to be mostly a middle and high latitude phenomenon. And this is a 5-day wave in the windless atmosphere, and it's very much what we would have expected. We have weak pressure at the equator, and two huge and basically just big, gigantic hemispheric scale circulations, geostrophic looking circulations at the high latitudes. What happens if what happens when we get down to stationarity, or something very, very close to stationary? If there's no mean wind, then nothing happens. Everything basically just collapses into a stationary system that will be purely geostrophic. That's if there's no mean winds and utter stationarity. If there's a mean wind, then there is some potential for a wave to be moving to be advected along with the mean wind. And if we have a mean wind and a very slowly moving system with weak divergence, then this whole system, all these equations that you're seeing here, collapse down into something fairly straightforward mathematically, although we are going to be bringing in some new terminology. The system collapses into what we call a conservation of potential vorticity. The quantity here called Q. And Q is basically the curl, the curl of a column of air in between two log pressure surfaces. And this equation states that vorticity, that the local time and the advection of vorticity is controlled entirely by, I'm sorry for this beta, phi sub x term here. I was trying to be mathematically cute here, but this beta phi sub x term is basically V. Phi sub x is V if you look at the definition of phi, which is basically just geostrophic V. This term here is basically the meridional advection of the Coriolis acceleration. The Coriolis force, as we have noticed, as we saw before, is a function of latitude. And we saw in all of these previous figures how the change in Coriolis force with latitude so strongly controlled what the diurnal tide looked like, and the semi-diurnal tide, and the 2-day wave, and the 5-day wave. And so this is sort of the ultimate expression of it, that basically vorticity is controlled by advection if there's a zonal wind present, a local acceleration if the flow is non-stationary, and the transport of the transport of the Coriolis acceleration of the gradient of Coriolis acceleration and latitude. This is the so-called planetary wave system, and its solutions are known as Rossby waves. And what do they look like? This is a Rossby wave. It is actually pretty familiar to anybody who's who's done meteorology. It is primarily in geostrophic balance, with the air flowing parallel to the pressure contours. The magnitude of the wind is determined by the strength of the pressure gradient. And the waves are forced primarily by large-scale heating patterns and by large-scale mechanical and heating patterns owing to ocean-continent contrasts and topography. As I said, they're governed by conservation of quasi-geostrophic potential vorticity. And despite the very, very weak divergence in the system, these waves are able to propagate vertically under very, very specialized conditions. And that is, they can propagate as long as they are moving westward relative to the background wind. So if there's no background wind, they're just propagating westward. If there is a background wind, then the wind has to be lightly eastward relative to them. So let's see how that works. Note, you noticed that this example I showed you from January was confined to the winter hemisphere, to the high latitude winter hemisphere. Here are the background winds between the surface at 1,000 and roughly about 90 kilometers. So this is the stratosphere here. So the Rossby waves are for the most part going to hug a wave guide loosely defined by eastward winds between 20 and 30 meters per second. And this is seen here. This is a plot of the combination of planetary waves number 1 and 2 in SABRE data over the winter season. And so you can see that these waves are very much hugging the latitudes where the background zonal mean winds are not too strong. It's staying out of the jet core. The same dynamics, by the way, apply to the 2-day wave, which we saw earlier. The 2-day wave is very strongly affected by the background winds, but the 2-day wave, which propagates westward, is only able to exist in the summertime hemisphere, where the westward jet is not too strong, because the 2-day wave is propagating at at about 50 meters per second westward. And so the background wind has to be, maybe between -30 and -20 and -50. And so we really see how the background wind pushes the 2-day wave, which in a windless atmosphere we saw occupied the whole globe, but in reality, the background wind really shoves it only into the summer hemisphere. So I am at this point somewhat pivoting and talking now about coupling by tides and planetary waves. The simplest, because tides propagate vertically and have very deep vertical wavelengths, if there is some kind of variability in their forcing at the surface, we talked about how the diurnal tide is forced by heating, by surface heating in the water vapor layers, which are very strongly influenced by sea surface temperature. So if there is some systematic variation in, say, the water vapor heating pattern, then one might expect that the diurnal tide will respond to that. And indeed it did in the case of the 1997-1998 El Nino. The El Nino shifted, the El Nino modified sea surface temperatures shifted the centers of water vapor heating in the lower atmosphere, which transmitted itself into a tidal pattern that registered in a stronger than average migrating diurnal tide for this particular year. So that's one example of what I would call sort of a very direct coupling effect. Another example that I still refer to as direct is the imprint of a convectively generated tide in the F layer plasma emissions. And the plot I'm showing here is basically a modeling result, but basically the modelers showed how a convectively generated tide would get up into the lower thermosphere and then distort the equatorial ionization anomaly, to register in its associated brightness. And so even though we need to have all this stuff going on in the in the dynamo region, I still call this a direct effect because it basically results from some tidal pattern that registered tropospheric activity in it and in it alone, and then just propagated straight up. However, planetary waves can play a role here. When I spoke about Laplace's tidal equations, I emphasized how they were frictionless and relative to a motionless background state. But if we actually were to put the friction term back into the equation for the zonal momentum, then it would consist of lots and lots of nonlinear terms, including including wave-wave transports. And so one form of transport that can occur is when tides can transport planetary wave momentum north and south. Because the tides are a low latitude phenomena and the planetary waves are a middle and high latitude phenomena, but planetary waves, when they amplify, get refracted equatorward. And so it's conceivable that tides and planetary waves can nose into each other's neighborhoods and then get together and interact. And when they do, we can predict the outcome, through wave, frequency and through frequency and wave number, sums and differences. We can predict product waves. And so it turns out that the diurnal tide can interact, for example, with the two-day wave. This is a model simulation because the most prominent product of this interaction is very, very difficult to observe since it has a 16-hour period. But I bring this up to show two important features, two important consequences of tide-planetary wave interaction. One is that the wave product, the products of this interaction, can show up in areas where the parent waves don't live. So, for example, you remember how I made a big point of the two-day wave being shoved into the summertime hemisphere because of the background wind, which for this plot would be the southern hemisphere. But its progeny, the progeny of its interaction with the tide is a 16-hour wave, which actually lives in the opposite hemisphere. It's a westward propagating tide. It also penetrates to higher altitudes than the two-day wave can get. This 16-hour wave can get up to at least 110, and then and even higher. So when tides and planetary waves pick up on each other, it's sort of like all limits are off. The effects of tide-planetary wave interaction, the effects of the nonlinearity between tides and planetary waves can result in imprinting, in planetary wave imprinting in areas that are very, very, very far away from the waves themselves. And the same thing has been shown to happen in regards to sudden stratospheric warming. Sudden warming is characterized by the polar vortex. Well, I'm not going to go into this polar vortex terminology, even though it's fun to use. Sudden stratospheric warming is characterized by very strong planetary wave activity in the stratosphere, which is manifest as the polar vortex being literally torn apart. But the upshot of this activity is strong planetary wave growth in the stratosphere. These planetary waves can, get spliced with the tide, and there's already been some work done showing that in fact was exactly what happened. But what we really want to know is whether in an event that occurred in January 2009, what we really want to know is whether that kind of action is responsible for perturbing the vertical drifts, at Hikomarka that same year. So with this, I'm going to move into my final two slides. I hope I haven't taken up too much extra time here. But as I see it, the observational challenges involving tides and vertical coupling. The observational challenges are to define tidal variations on relatively short timescales, like less than the 30 to 60 days that the current fleet of NASA satellites requires in order to get sufficient global local time coverage. So we need short-term tidal definitions because if we want to look at the effects of tropospheric weather, which is a day-to-day, which are subweekly phenomena, if we want to know how tropospheric weather can affect space weather, we need to know how the agents of vertical coupling, the tides, we need to know how they vary on the same time scale as the weather. The other challenge is that we have some sense now of how the neutral, of how tides and planetary waves can imprint their variability upon each other in the neutral atmosphere. But there's a bit of a blind spot in how the tropospherically generated tides that can transmit their variability into the MLT. There's a bit of a blind spot in observing how that observing how that gets into the F region. So fortunately, we have some new opportunities to close those gaps. I am not going to say any more about this now because there are going to be a lot of really terrific talks that are showcasing the new results from ICON. ICON is measuring thermospheric neutral winds and ion winds as well along common magnetic field lines. So we can actually try to map the to actually map the dynamo effect. And GOLD is observing the disk, is observing the Atlantic and South American disk. And there are going to be plenty of talks on that as well. So at this point, I am going to wrap up and take some questions. Thank you very much. You've been a great audience.
Thank you very much, Ruth, for your excellent presentation. And I do agree that this presentation complemented Christopher's presentation very well. We have several questions, and I think we have time for a few. So our most upvoted question for you today reads, very nice to hear from Dr. Ruth and very nice talk. Are the tidal sources different in temperature and wind fields?
Yes, well, I'm not sure I understand the question. I mean, I guess it depends what sources you're referring to.
Right.
I spoke when I spoke about tidal heating sources. But when people speak about tidal wind sources, I'm not sure what they're referring to. Are they referring to like internal momentum forcing?
So we don't have the ability there's an anonymous question, but what we can do is I can ask the person who submitted that question to resubmit it with an elaboration, and then we'll send it to you after the day concludes, and then we can publish your answer.
I guess. I mean, I guess I can answer that. I mean, I think the answer is yes. I haven't said much about non-thermal sources, but the answer is yes. It is possible in theory and perhaps even in practice to also have mechanical sources for the tides. We tend to not really think about that too much on Earth. Perhaps we should, but certainly for anybody doing modeling of tides on Mars, then I know that orographic forcing of tides is a big, it's a big term that Martian tidal modelers definitely have to include. So I hope that I've somewhat answered this question.
Okay, thank you. Our next question is, what is the importance of the tides and the E and F region dynamics? If we remove the tides, how big of an effect in the dynamics would occur in approximate percent?
The short answer is, I would have to consult a modeler, and if I understand, I guess people are wondering to what degree do the tides to what degree do the tides are the tides able to transmit the lower level perturbations up into the F region?
That could be, yeah, that could be what they're asking.
I have not personally looked into that, and I imagine there are probably modeling experiments that perhaps have done there might be perhaps controlled modeling experiments in which the tides can be stripped out of the system, or maybe averaged over 24 hours so that their effects wash out. I don't have at the tip of my tongue an answer for that. I'd have to look it up, and then I guess I can provide it if we're supposed to be providing written answers to the questions we can't get to.
Okay, that would be great. So we're a little bit behind. I think we'll go ahead and wrap the questions up for Ruth at this point, and we'll send you the rest of the questions that you can answer at your own convenience.
Thank you.
So we're going to, I think, we're going to try to keep on schedule here and resume at the correct time. So I think that puts us at around a 20-minute lunch break. I hope that's okay for everyone. And so I think we'll go ahead and see everyone back here in about 20 minutes. Thank you. Okay, welcome back everyone from lunch. We're going to continue on with our afternoon talks. So our first talk of the afternoon is from Siting Chu. She is a postdoctoral fellow of the High Altitude Observatory from the National Center for Atmospheric Research. Her work focuses specifically on coupled upper atmosphere data assimilation. Her research interests include inquiring the predictability of the ionospheric and upper atmospheric weather, assessing remote sensing data impacts on the predictability of the TI interaction region, and ensemble analysis of the coupling of the ionosphere and the neutral atmosphere. So whenever you're ready, Tsuting, go ahead and take it away.
Hi everyone, my name is Zhiting Xu from NCAR AKO, and my personal research interest is the upper atmospheric data assimilation. So today I'm very excited to be here to share with you my personal opinion on the state and future of data assimilation on space science. When I get the invitation to talk about the state and future of data assimilation, I feel like, wow, that's a really big topic. So I try to narrow it down, and in this talk, I will mainly focus on three parts. In the first part, I will give you a brief idea of what is data assimilation and why we need to do data assimilation. And in the second part, I will give you an introduction of the data assimilation method that we use. And then in the third part, I will show you some example of the application of data assimilation. And from those applications, I will point out the challenge in the future. So for those of you who never heard about data assimilation, in the first section, I would like to give you a brief idea of what is data assimilation and why we need data assimilation. So data assimilation is a method that can combine observation with a prior state that is background knowledge usually comes from numerical model or empirical model. Then why we not just use data or just use model? To answer this question, I need to talk about the limitation of model and observation. So let's talk about the limitation of observation. We all know that observation has error, and this error includes systematic error, as known as bias, the error of representativeness, and noise. So by combining model information with observation information, we are able to reduce the error and increase the accuracy. Another thing is that observation has a special temporal gap. For example, here shows a very famous ozone data assimilation case. The left-hand side is the ozone observation from satellite. And you can see that there's a huge gap between the orbit, and it's hard to see what the ozone distribution. And the right-hand side is the ozone forecast from numerical model. Although it has well global coverage, the structure is too smooth here. So by combining these two information together, we are able to get the ozone analysis, and you can see the blue structure is more clear now. And the other example is the vertical total electron contact VTEC data assimilation. The top panel is the VTEC from ground-based GPS receiver within 1 hour window, and the mid panel is the VTEC from a numerical model, a couple model of thermosphere and ionosphere, TIGCM. So you can see that the top one, the vertical TEC above ocean is almost blank. But by combining this observation information with numerical model, we are able to get a bottom figure, which you can see that it fill up the gap of above the ocean. And next, let's talk about the limitation of numerical model. Here shows a very famous Lorentz butterfly pattern. And the red line is from the Lorentz model with initial condition 0, 1, 1.02. And blue one is with initial condition 011.03. So you can see that if we look at the XYZ component on the left hand side, you can see that the red line and the blue line are very close to each other at the beginning, and after a few model time step, this difference start growing up, and this result emphasize the importance of get a good initial condition, and data assimilation can help us to get a better estimation of initial condition by combining model observation information into the model. So now we know that the data assimilation can help us combine observation information with background knowledge optimally to reduce the observation error, fill up the gap of the observation, and also get a better estimation of the initial condition. Next, I would like to give a brief introduction of the idea of data assimilation method. So the basic idea of data assimilation can be explained by Bayes' theorem, as shown in the equation on the left-hand side. The x is the state that we want to estimate, and y is the observation. And p is the probability. The red part is the probability of the posterior state, which is proportional to the probability of the prior state times likelihood probability. And if we plot out the probability distribution function PDF as shown on the right hand side, we can see that the blue line is a prior PDF given by model and the background error variance from model. And the width of this blue line is can represent the uncertainty of the model, and the black line is the likelihood PDF that determined by observation and the error of observation. And from this blue line and the black line, we can see that the most possible state is somewhere between the yellow part. Now, by multiplying blue line with the black line, we can get a red line, which is the posterior PDF, and this you can see that the mean of this posterior PDF is in between the blue line and the black line, and also the width of this posterior PDF is smaller than the blue one and the black one, indicating that by combining observation information with model information, we are able to reduce the uncertainty. And practically, there are two ways to solve this problem. The first one is trying to find the state with minimum variance. This will lead to the common filter methods, include the ensemble common filter. And the second way is trying to find the most possible state. This will lead to the variational methods, include the 4D variational method. And next, I would like to detail these two methods. Okay, let's talk about the 4D-dimensional variational method, 4D var. The 4D means 3 dimensions in space plus time as the 4th dimension. And the basic idea of 4D var can be shown in this figure. Let's say we have a prior initial condition xb at time t0, and we can use our numerical model or forecast model M to find a trajectory with this initial condition as shown in the blue line. And we also have some observation at different time as the green star shown here. So you can see that the difference between model and observation are really huge. And what we want to do is in 4D var is to find a new initial condition that can minimize the difference between observation and model, and also the prior and posterior initial condition. So now we can form a cost function J. And this J looks pretty complicated, but actually it just combined by two terms. The first term is related to the difference between prior and posterior initial condition, and P is the background error covariance. And the second term is related to the difference between observation and model, and the R is observation error covariance. And next, I would like to detail a bit about how we actually do to compare the observation with numerical model. For example, if we have, let's say we have the observation at time ti, then what we need to do is for a given initial condition, we use the forecast model to advance our model state variable from t0 to ti to get the model state variable x at ti, which is xi. And then we use an H operator or forward operator to convert this xi from model space to observation space. Then we can do the comparison. What does it mean to convert the x from model space to observation space? One simple example is the linear interpolation. For example, it's hard to find an observation that just at the same location as the model state variable. So what we need to do is that we need to first of all interpolate our model state variable from the model grid to the observation location before doing the comparison. In that case, the H is the linear interpolation operator. A more complicated case is the vertical electron density, total electron contact VTEC data simulation that I showed in the very beginning. So in that case, the numerical model will only provide us the electron density distribution. And what we need to do is we need to integrate the electron density vertically to get the vertical TEC from model, and then we can do the comparison between with the TEC from ground-based GPS receiver. So how to form this forward operator is basically determined by what kind of observation you want to assimilate. Okay, let's get back to the cost function. So the idea of 4D var is trying to find a new initial condition that can give us the minimum of this cost function, as shown in the second equation. And you might notice that the forecast of model or numerical model is actually related to the cost function. If the forecast model or numerical model that we use is a low dimension and linear model, it's easy to solve this problem. However, most geosystems are high dimension and nonlinear, so that makes the implementation of 4D var become more difficult. Next is ensemble common filter, ENKF. So what we have in ensemble common filter is that we not just have one prior initial condition, instead we have a set of initial condition x01b to x0nb, and we use the numerical model to advance this set of initial condition from T0 to T1, which is the assimilation time step. Now we can have a set of ensemble member, and the green line is the ensemble mean. So what we want to do in ensemble common filter is that we want to assimilate all observation, which is the green star here, into the assimilation time step T1. And the observation will weighted by the time difference. And then we will get a new set of initial condition x11a to x1a, and then we can use this new set of initial condition to advance to next data assimilation time step, which is T2. So you can see that in ensemble common filter, what we actually do is that we run the forecast step, which is from T0 to T1 and T1 to T2, and for a simulation step, which is at T1 and T2 alternatively. And what we actually do when we do the data assimilation in the assimilation step is that we use the update equation on the left hand side to do the data assimilation. And the first equation is the update equation for ensemble mean, and second equation is the update equation for each ensemble member. And you can see that this equation shows the posterior initial condition is equal to the prior initial condition plus a term that related to the difference between observation and error of observation. And also the case showing here is so-called the common gain that compute from background error covariance and observation error covariance. And the background error covariance in ensemble common filter are estimated by model ensemble, meaning that we don't need to know the background error covariance in advance. We only need to compute this time-dependent background error covariance from model ensemble at given time. And by doing so, we can get a background error covariance that can capture the dynamics in your model. Here I list some advantage and disadvantage of the 4D VAR and ensemble common filter. The first one is that ensemble common filter is easier to design and code comparing with 4D VAR, because in ensemble common filter, forecast and assimilation steps are carried out alternatively, meaning that in the forecast step, you just run the model that you already have, and in the assimilation step, you can use some open source module for ensemble common filter that you can download online to do the assimilation, for example. And next, I would like to show you some example of the application of data assimilation. There are many different kinds of application of data assimilation in different fields. And since this is a CEDAR student workshop, I will mainly focus on the application of data assimilation on the upper atmosphere, including the mesosphere, ionosphere, and the thermosphere. So in my personal opinion, there are three major applications of data assimilation on upper atmosphere. And this application that I list here is what I personally think is important and also has been published before. They include generate model initial condition and time-dependent forcing for upper atmospheric weather forecasting, evaluate the impact of observing system on forecast and specification, and finally, produce reanalysis for better specification of upper atmosphere for science investigation purpose. Next, I will list one example for each application, and from that example, I will point out the challenge of that application in the future. So first of all, let's talk about the upper atmospheric weather forecasting. So the upper atmosphere is not only affected by the initial condition, it's also very sensitive to the drivers such as solar irradiance, magnetospheric energy forcing, and also the tide and wave from the lower atmosphere. So therefore, to get a good predictability of the upper atmospheric weather forecasting, both initial condition and time-dependent forcing are very important. So the first case is a data assimilation of the geomagnetic storm published by Chen et al. In 2016. The observation used in this study is the ground-based GPS TEC, and the model is the TI-UCM, and data assimilation scheme is ensemble adjustment common filter, which is a variety of ensemble common filter. For the ensemble member used in this study, for each ensemble member, they will give them different value of Kp and F10.7. The Kp in TI-UCM is used to determine the magnetospheric forcing, and F10.7 is used to determine the solar irradiance. So these two values will be different among all ensemble members. And for a given ensemble member, these two values will be a constant over the entire data assimilation period. Entire experiment period, because they assume that we are not able to know the variation of Kp and F10.7 in advance before storm happen. So the purpose of this study is trying to see the predictability of the system with a fixed driver. And in this study, they will have 3 experiments. For each experiment, the data that they are going to assimilate and the model are all the same. The only difference is that they're trying to change the length of forecast period, or you can say the time interval between T1 and T2 from 1 hour to 30 minutes to 10 minutes. And by doing so, they are able to see the predictability between 2 data assimilation steps. So the main results are showing in the middle. The top panel is the DST index and KP index during the entire data assimilation, entire experiment period, and the bottom 3 panel are the RMST for each experiment. RMSD. Root mean square. The RMSD means the root mean square difference, which is shown in the equation on the right hand side. So this represents the difference between the observation and the model. In this case, is TEC. And now let's zoom in a little bit to see what's going on here. So the gray line showing here is the RMSD for control run, which is the one without any data assimilation impact, and the red dot is the prior RMSD, and the blue dot is the posterior RMSD. So you can see that by doing the data assimilation, we are able to bring the red dot to the blue dot because we assimilate observation into the model, and so that bring our model become closer to the observation. And you can see that from the posterior RMSD to the prior RMSD at the next assimilation time step, the arrow grows up. This means that during the forecast step, this arrow grows up. And by looking at the arrow growth between these 2 assimilation steps, we are able to assess the predictability of our system. So from the first experiment, which is the experiment with 1 hour data assimilation interval, we can see that the prior RMSD is almost back to the original the gray line, which is the control level, meaning that the system loses its predictability within 1 hour. And by shorten the interval from 1 hour to 10, we can see a better result, the smaller RMSD. So now from this experiment, we know that the system's predictability is less than 1 hour if we use a fixed driver. Our case shows the importance of time-dependent forcing for upper atmospheric weather forcing. But the question is how to generate the time-dependent forcing. In my personal opinion, I think there are 2 ways that we can generate, at least 2 ways we can generate the time-dependent forcing. First one is the machine learning. By use machine learning, we can get the variation of index, such as the variation of KP index or DST index. Another one is use a coupled system. For example, we can couple ionosphere with lower atmosphere and magnetosphere so that we can simulate the energy transfer between different systems. So let's move on to the impact of observing system. For a given type of observation, the impact of two different observing systems on the same data assimilation system will still be different because the observation area, location, data volume approach are all different. Let's see an example here. For the electron density data, radio occultation and ionosphere can both provide us electron density data. For the radio occultation, the GNSS receiver on the LEO can receive the GNSS signal travel through the ionosphere and then retrieve the slant total electron contact along each radial path. And by this kind of data, we are able to compute the electron density at tangent point. And this kind of data is more accurate in F region than E region, and also the location of this data is depend on the position of GNSS and LEO satellites. On the other hand, for the ionosphere, the ionosphere transmitter will sweep the high frequency range radio wave, and the radio wave will propagate in the ionosphere and reflect it at various layers. And by the echo received by the ionosphere receiver, we are able to analyze the electron density profile. And we know that this kind of data is more accurate in the bottom side ionosphere than the top side. So and also this kind of data is will fix above the ionosphere station. So it's clear that the electron density data provide by these two different observing system will be different. Sorry, the impact of the electron density data provided by these two observing system will be different. Okay, let's look at one example of Formosa 3 cosmic and Formosa 7 cosmic 2. So in this study, they trying to investigate the impact of Formosa 3 cosmic and Formosa 7 cosmic 2 on the same system. The Formosa 3 cosmic and Formosa 7 cosmic 2 are two constellations that are designed for radio occultation mission. The Formosa 3 cosmic was launched in 2008, and because it's due to the success of Formosa 3 cosmic, for the follow-on mission Formosa 7 cosmic 2 launched in 2019, and the left-hand side shows the data coverage of these two systems within 1 hour window. The blue dot is from the data coverage of Formosa 3 cosmic, and the red dot is Formosa 7 cosmic 2. So you can see that the Formosa 7 cosmic 2 is more focusing on mid-low latitude region. And the observation used in this system is the synthetic Formosa 3 cosmic and Formosa 7 cosmic slant total electron contact STEC data. And the new model used here is a couple model of plasma sphere, thermosphere, and ionosphere, GIPT-IGCM, and data assimilation scheme is ensemble square root filter, which is also another variety of ensemble common filter. So this study was published in 2018 before the Formosa 7 cosmic 2 launched. The purpose of this study is trying to see the impact of Formosa 7 cosmic 2 in the future at that time. And since Formosa 7 cosmic 2 was not launched at that time. So the data they use for this study is synthetic data. So next, I would like to explain detail a little bit of how to generate the synthetic data. So basically, there are two ways to design a data assimilation experiment. The first of is the observing system experiment (OSE), and the second one is the observing system simulation experiment (OC). So for OSE, we assimilate real data into the model and then comparing the result with the independent observation. So the first example, the storm case, is OSE. Although we did not compare the result with independent observation. So the disadvantage of using OSE is that it's hard to get a global vision of the impact of data assimilation by use of OSE, since we just have limited amount of observation. And the other way is OC. In OC, we first of all run a nature run. And the nature run is a run that's different from the run in your data assimilation system. And then we sample some synthetic data from this nature run and assimilate that into your data assimilation system. By comparing result with the original nature run, we are able to have a global vision of the impact of data assimilation. This is OC. And this study is OC. Now let's look at the result of this study. So you can see that here shows the difference between the nature run and the result from Formosat 3 Cosmic and Formosat 7 Cosmic 2 OC at different altitude. We want the result after data assimilation can become closer to the nature run. And that means the data assimilation have positive impact. And from this figure, we can see that the green means almost no different, and blue means negative bias, and red means positive bias. So it's obvious that Formosat 7 Cosmic 2 has higher impact on the ionospheric specification in middle latitude region comparing with Formosat 3 Cosmic, but still need to be improved in high latitude region. And this study shows the importance of studying the impact of two different observing systems. Nowadays, we already have many different kind of observing system for upper atmosphere, but the impact of most of these upper atmospheric observing systems haven't been studied in detail yet. So we definitely need to put more effort into it. And study the impact of observing system can not only help the data assimilation performance, but also can give us a more clear idea of how the impact of observing system in geosystem and further help us for mission design in the future. Finally, let's talk about reanalysis data for science investigation purpose. Here shows a basic idea of how to use data assimilation for science investigation purpose. First of all, we can combine observation with numerical model using data assimilation to get a better specification of upper atmosphere or any other field. And then we can compare them with independent observation. If there are differences, means that there might have some missing physics in your numerical model, or the hypothesis that you use to form your data process that might have some problem. So you can by using data assimilation to find out the problem and fix them. And next, so here shows an example of using data assimilation to study the pre-reversal enhancement. The observation is vertical, is the GPS TEC shown on the map, and the model is TIEGCM. The data assimilation scheme is ensemble adjustment common filter. The main results are showing here. The left-hand side is the longitude-latitude map for vertical TEC. The mid panel is the latitude-altitude profile for zonal wind at local evening. And the right-hand side is the longitude-altitude map for the electro field. And the top one is the one with data assimilation, and the bottom one is the one without data assimilation, which is the control run. So you can see that with the help of data assimilation, there's a clear trough structure in the TEC map in the evening. And then the zonal wind also becomes stronger on the top side and weaker in the bottom side. And in the electric field, there's a strong electric field in the local evening. So what they actually do is that they use the data to change the TIEGCM's electron density and the zonal wind in the data assimilation step. And since the zonal wind are changed, so it will further change the electrodynamic process in the forecast step. And this change will affect the electric field, as shown on the right-hand side. And the change of this electric field will further change the equal-speed drift. So here shows a comparison between the the equal speed drift from data assimilation result, which is the red line, with the empirical model, which is the black line, and the Hikamaka data, which is the blue line. So you can see that generally data assimilation has a good agreement with the data. So right now I have shown you an example of how data assimilation can use for science investigation. But the question is, what kind of science topic might be benefit by using data assimilation? So in my personal opinion, I list 3 kind of topic that might be benefit by using data assimilation. The first is something that can be observed by more than one type of observation or by more than one observing system. So in this kind of case, you will want to combine all observation information together into a numerical model. By doing so, you can get a more comprehensive vision of that phenomena. Or the second one would be something that you don't have enough observation. So for example, the ozone data assimilation that I showed you in the very beginning. For this kind of case, you can use the data assimilation to fill up the gap in space and time. And the third one will be some phenomena that is a hidden state. For example, the electric potential in the previous slide. So that kind of the global electric field is hard to be observed. It's a hidden state, but we can by changing the neutral wind, we can get a better idea of how it should look like in the model. So if you are right now interested in this kind of topic, you might want to try to use data assimilation. Now come to my conclusion. This talk has 3 parts. In the first part, I introduced what is data assimilation and why we need to use data assimilation. Data assimilation that is a method that can combine observation information and background knowledge optimally. This can help us reduce the observation error, fill up the spatial temporal gap of observation, and get a better estimation of initial condition for numerical model. And then I also introduced the basic data assimilation method. The basic idea of data assimilation can be explained by Bayes' theorem. And I also introduced 2 kind of data assimilation model, the 4D VAR and ensemble common filter. And nowadays, the most widely used data assimilation method for upper atmosphere is the ensemble common filter. finally, I show you some example for the application of data assimilation on space science and point out its challenge. Those challenges are find a better time-dependent forcing for upper atmospheric weather forecasting and space weather forecasting. And then the second one is study the impact of more observing systems. Finally is using data assimilation to to the science investigation, including phenomena that are observed by more than one observing system, or those phenomena that don't have enough of data, or those phenomena that hard to be observed. So I will stop by here and thank you for your attention.
Thank you, Ziding. That was a great and a wonderful talk on data assimilation. We do have some interesting questions from audience. The first question for you is, in previous examples, the synthetic data was not reflective of life. How does the OSSE method improve accuracy rather than propagate an inbuilt model error?
Okay, so I think this is a really good question. So actually, to answer this question, I need to mention that for OC, so first of all, you will have a nature round, and then you have a data assimilation system, that the numerical model that built in your data assimilation system. And this nature round, the model that you use, numerical model you use for the data assimilation system, is not necessary to be the same model you use in the data assimilation system. Meaning that, for example, if we can sample more the synthetic data from a higher resolution numerical model, and then assimilate that synthetic data into your data assimilation system. So this way we can compare the difference between the two numerical model. And second thing is that I think it's not able for a synthetic data to, you are right, it's not able for a synthetic data to reflect the real life. So after doing OC, after we know the impact, what's the impact of data assimilation, we still need to compare the result by using OSE, which assimilating real data.
Thank you, Ziring. That was a great answer. We have another question. Do increasing ensembles yield diminishing returns in the assimilation step?
Oh, so I think I'm not quite sure what this question really means. I think is the dimension means the ensemble coverage. If so, I think this question we need to discuss two parts. First of all is what's the impact of increasing ensemble, and then second thing is the ensemble spread before and after the data assimilation. So increase model ensemble do help us to get a better estimation of the background error covariance, and so that will help us to get a more accurate posterior initial state, and so that you might get a more accurate ensemble spread after doing data assimilation. And if you don't have accurate background error covariance, you might need to, there are actually many different ways to tune the ensemble spread after data assimilation. For example, you can use the covariance inflation method to give a little bit spread in the ensemble after doing data assimilation. So the other question is, will the dimension return in the data assimilation step? So I think for this one, after data assimilation, the ensemble will coverage should coverage to the true state. So Yeah.
Ah,
I don't know
all
whether
right.
this written answer this question or not.
Yes, thank you.
Yeah.
Thank you, Ziling. Yeah, thank you. So I think with that, we will wrap up the questions Q&A session for Ziling.
Yeah.
We'll be sending you the rest of the question later, Ziling. All right, thank you.
Yeah, thank you.
We'll be moving to the next speaker. Our next speaker is Ryan McGranagan. Ryan is a principal data scientist at aerospace engineering scientist. Oh, sorry, my bad. Ryan is a principal data scientist at Astra LC. At Astra, Ryan leads data science and machine learning efforts to improve our understanding of the Earth's space environment. Ryan began this role after completing a Jack Eddy Living with a Star postdoctoral fellowship at the NASA Jet Propulsion Laboratory, during which he studied the Earth's and solar system planets' interactions with the Sun. Ryan was selected as a National Science Foundation Fellow to complete his PhD research at the University of Colorado Boulder and completed his degree in aerospace engineering sciences in the fall of 2016. He also holds a master's degree in aerospace engineering sciences from CU Boulder and a bachelor's degree in aerospace engineering from the University of Tennessee. Today, Ryan will be talking about living with a star in the age of data science, tools, technologies, and mindsets for the modern space environment. So, with that, thank you, Ryan. You can start whenever you're ready.
Great. Thank you so much, Kamal. And thank you to the Student Steering Committee and the CEDAR Steering Committee for making this opportunity available to everyone. I know it's difficult that we were restricted to the virtual setting, but Astrid Mauta and Dolores Knepp and Matthew and Kamal have done a really outstanding job of making this possible. And I'm really appreciative of the opportunity to talk with everyone today. So as Kamal mentioned, my name is Ryan McGranagan. I'd love to be with each of you in person, but we'll have to save that for a future year. But just quickly, I kind of consider myself a concoction of space physics and engineering, data science, and even design innovation. And I mention that just because I think that combination that is non-traditional maybe underscores one of the central movements that I'd like to make in this talk, and that I think I want everyone to kind of rethink what the CEDAR community looks like. And how you spread and broaden the impact of your work. So at the moment, I'm working across a few different NASA agencies on different initiatives, and I work with a small aerospace business called the Atmosphere Space Technology Research Associates. So I look forward to kind of interacting with each of you throughout the week this week. So I was charged with a pretty broad question. What tools are necessary to predict the variations in the space environment using both small and large data sets? And so that is a massive discussion, obviously one that we can't have in 30 minutes. We could easily run a week-long workshop on this and still only barely scratch the surface. So what I want to do today with this talk is just provide some food for thought, some things to inspire your curiosity and to help you get started in studying these different methods and these different technologies that are available to study the space environment. And so what I want to do is drive to the mindsets that are needed for space science understanding and prediction. So these mindsets really will be the takeaways from this talk. They're what going to lead you to the capable tools and technologies that we can't completely cover in this time. So what I do want to do today is to introduce the tools and technologies that are making waves across the sciences right now. And that I think have the potential to transform the Earth and space sciences. So it kind of gives you a foothold to investigate further and expand your own views and awarenesses. So I realize that people in this room probably don't know a ton about me, so I just wanted to quickly share a little bit about myself. I thought Kamal did an excellent job of introducing me, so thank you for that, Kamal. But just a little bit about my background. I kind of consider myself a lifelong traveler. So you can kind of see a number of the different stops that I've made that have included traveling the country numerous different times across the breadth of the country to do a PhD at the University of Colorado in Boulder, over to Dartmouth at the other side of the country, and then back over to Los Angeles, where I was at the Jet Propulsion Laboratory for a few years. At the moment, I work again at this small aerospace business, Astra, which is located in Louisville, Colorado. I'm actually part of a DC branch that's sparking up from Astra as I lead data science interactions with a number of initiatives across 3 different NASA centers. So the Goddard Space Flight Center, the Jet Propulsion Lab, and the Ames Research Center. But I kind of consider myself a lifelong traveler in discipline as well. So not just remaining within the space science focus, but broadening that to understand what other disciplines do we need to bring into space science and collaborate with to really make advances. And that's what I'll talk about today. But outside of work, I consider myself a performer. I love to communicate about science and a number of other things. And so you can see that I've had a good fortune to do a TEDx talk that I encourage you to check out. Also lead a podcast with a number of different people that are in and out of our community that you might be interested in. So that's me. And what I wanted to do today, again, was drive to the tools and technologies. And so when we talk about tools and technologies that are available to us now, it's easy to get overwhelmed. So this is 2019's data and AI landscape. So you'll hear in this talk that I'll talk a lot about data science and what it's doing to transform our field. But one of the big challenges is that this is not helpful. This web and zoo of different models and approaches and capabilities across the data landscape. But what we need is to understand where this fits into our science and allow that to dictate which of these tools that are most useful to us. And so that's my goal for today. So the ultimate goal will be to start a discussion that I hope each of you will help sustain, expand, and really change. So if you're on the Slack channel and active, I encourage you to join the CEDAR Data Science channel and start to enrich the discussion there. So at the end of this talk today, you're going to know what data science is and its importance for the future of space science prediction. Again, we'll only be able to scratch the surface, so this will not be comprehensive, but just a starting point. Our discussion will naturally lead to new mindsets that we must adopt as a community to realize the potential for CEDAR data science and to keep pace with the changing landscape that you see here, these tools and technologies. So again, we're going to let the science dictate what we need. And so let's look at the environment that we're working in. So I'd like to structure our discussion around this image. From it, I will raise key considerations as I see them, and some of the tools and technologies that are critical will emerge. We will use that emergence to drive to the open conversations and ultimately the mindsets that we may need to explore and adopt. So I'm going to do this in 3 considerations. The first is you hear often this buzz term, big data. But I think it's more appropriate for what we're considering to realize that we don't have a data problem, we really have an information problem. So when you talk about data and you look at the heliophysics observational fleet, we realize that they are coming in many different forms from many different platforms and studying independent but connected phenomena. And these data are really unorganized facts that really need to be processed. So these data can seem simple, random, or useless until they are organized. But when we do appropriately process, organize, structure, and present these data, they become information. And so this process of making data and transforming it into information is what data science does. So I just want to give a definition, since I think that data science has often become a buzz term as well, and it's often helpful to start on at the same footing, essentially. So one of my former colleagues at the Jet Propulsion Laboratory gave a definition for data science that I kind of carry with me and I think is particularly useful. So he called data science scalable architectural approaches, techniques, software, and algorithms, which alter the paradigm by which data are collected, managed, and analyzed. And something that I added was also communicated. But I think it's that final point here that data collection, management, analysis, and communication are all under the umbrella of data science. So a lot of times people will consider machine learning synonymous with data science. Machine learning is just a small component of data analysis, which is indeed just one small component of data science itself. So I like to give that definition as an important component. So with that definition in mind, what does it take to predict the variations in the space environment? Well, the first step is that it takes more capable data systems. So I want to look today at one specific example of what we need for more capable data systems. So if we look at the Solar Dynamics Observatory, so this might be a little bit foreign to some people in the CEDAR community, but the Solar Dynamics Observatory is the premier mission for studying the sun that's currently in space. So it sits between us and the sun, constantly observing the sun, and the data from this satellite are extremely large. So these data it's collecting terabytes of data. But we realized that instruments like this are becoming the new norm. So coming soon are new instruments that are going to help propel heliophysics science into the realm of big data proper, so really large volumes of data. So one of the examples I like to use is that there's a new solar observatory coming called the Daniel K. Inouye Solar Telescope. Just for a little eye-opening facts, that telescope will generate 25 terabytes of data per day for about 50 years as it's planned. So we're talking about 400 petabytes total data volume. And so we're expecting first light on that, or maybe first light has already occurred for this telescope, but this is where we're heading. And so we have to develop systems that disrupt how we traditionally analyze those data, because we can't physically move through that volume of data or that complexity of data in the normal ways that we do our science. So what do I mean by a more capable data system? So the Solar Dynamics Observatory is supported by a really wonderful community that spans data science to physical science. And they've been able to work together to produce new tools for quickly labeling data, for quickly analyzing data, and discovering with data. And so I just want to give one example of that. This is called the HelioViewer. So this is what you would call an outcome of some of the data science activities that go on. So this is benefiting from very careful data management from the Solar Dynamics Observatory. And you can just see all the different things that you can do with this. You can look at the sun in different wavelengths. You can change the time period that you're looking at. You can select different active regions on the sun that show you where to look and focus for potential space weather activity. These things are all labeled using either manual labels or even machine learning algorithms, which we'll talk about in just a few minutes. But these are the kind of tools that we need to really discover and really utilize the full amount of data that are being generated by instruments like the Solar Dynamics Observatory. And so I think that the HelioViewer is an excellent example of the tools and technologies that we need to just explore the data. So I think that these new technologies are making strides, but I really want to talk about how do we produce these tools. So what underlies the development of something like the HelioViewer? And I want to bring that into the context of Geospace and CEDAR science as well. So I want to step through these 4 V's, as they're called, of big data. So they're not just the growth in volume, but the first one I'll talk about is the clearest example, and the one that everyone thinks of, is the growth in volume of data. So obviously we have instruments from the ICON mission in space, from GOLD. They're collecting more data. They're making it harder to bring those data together and analyze them comprehensively. So what are some of the tools that really help us analyze just greater volumes of data? So I'm putting forth a few here that I think might be beneficial for people to be aware of. There are a couple of examples of unified analytics frameworks for big data analysis. So I'm citing Apache Hadoop and Spark here. So basically these are general purpose, high performance computing frameworks. They allow you to process more information and grow the amount of data that you can analyze in a fault tolerant way. So those are 2 examples, but then there's also the cloud environment. So 2 of the examples there that I've worked with are the Amazon Web Services and the Google Cloud Platform. And so you have unique access as students to resources on the cloud. And so it's a really excellent time to start moving some of your analysis there, starting to play around with what can be done with the cloud, what affordances that gives you. And it's really a great playground for learning data science and learning how to improve the data analysis that you do. The second V that I want to talk about, and this one is particularly important for heliophysics and space weather, and that's data variety. So this is a bit more difficult potentially than volume. And so I just want to mention a few important tools here. One that I think is a really important wave for CEDAR science is something called a knowledge graph. So how do we take the different data sets and very explicitly relate them to one another? So that if you're familiar with working with something like ground-based magnetometer data, you can understand the relationships of those data in the context of something like the ICON mission. So how can you discover what ICON observations are important to your work when you're only familiar with the ground magnetometer data? What allows that to happen is something like a knowledge graph. And so that's something that basically provides the data along with the explicit relationships between those data. It fundamentally relies on things like relational databases. So I'm citing a SQL database platform here, Postgres SQL. And this is a free and open source relational database management system. And it's just one example of the tools that are out there for relational databases. But I think that this is an area to focus if you're interested in learning about this. And really, I encourage you to embrace this knowledge graph concept and explore that as well. There are two other tools that I really want to drive to with this, and I'm not going to say much about this because I think ASTIBot next is going to talk about these, but they're very important for really growing the amount of variety of data that you're using. And so these allow greater collaboration. So you can use something called Jupyter Notebooks to really robustly share the code that you're developing, the data that you're using, and the techniques that you're applying. And you can use something like a version controlled software like GitHub to share those seamlessly and widely across the community and allow different people to contribute to the development of those algorithms. And so I think that those are two very important tools that we're going to have to predict the space environment moving forward. So the third V that I want to briefly mention here is veracity. And this is one that I think sometimes is not discussed comprehensively enough. So veracity is about the accuracy of the data. And for our science, this is extremely critical. If you think about how people predict the terrestrial weather environment, you're not given a single number. So if you want to know if it's going to rain tomorrow, you're not given a single number for that. You're given a number with uncertainty bounds. You're given it's 60% chance that it'll rain tomorrow. This is something that we don't do widely enough in space weather. And so I think enriching our tools and technologies to embrace uncertainties in the data and to have a better quantification of uncertainty in the data is very important. And so I just mentioned here the Bayesian statistics approach, which you've heard a little bit about in the previous talk by Qi-Ting. So Bayes' theorem underlies much of data assimilation, and it's extremely important because it does generate those uncertainty bounds that are so critical for our field. And then the final V is velocity. And there are a couple of components that I want to point out here. This is becoming increasingly important in space science prediction. So we've kind of seen across the community that low latency observations that are really relevant to space weather prediction have not advanced to a significant degree. And so what we want to do is better generate those data. So that can come from things like autonomous instruments that we put into space, distributed platforms. We've all seen the advent of CubeSats that have made more distributed observations available. But the challenge will be to analyze the data that are coming down in real time and really building those into our models. And so how do we keep up with the velocity of data that are coming down? So in addition, one of the tools that I'll point you to that can help keep up with velocity of data are streaming data platforms. And so I've cited a few different Apache platforms here. The one that helps with real-time data is Apache Storm. But I'm just pointing to those as examples because they're software packages that have emerged from the open source community. And so they're made freely available, they're maintained by the community. And I think the prevalence of the Apache Foundation just underscores how important it is to be open by default and really share your data and allow people to reuse and build on your algorithms. So it's one of the things that I really wanted to focus on here. So that's the first consideration. We don't have a data problem, we have an information problem. These are a few of the tools and technologies just as a summary slide for you that I think we emerged. And then finally, I just want to point to the mindsets that accompany this. The first is to just interact with data. Do that more broadly and rapidly. Find the tools that help you do that and that help you collaborate with others to do that, that really help. The second is the need to quantify the information of observations and relate that to the benefit to prediction. And I'll talk a little bit about that more in the second consideration. But I really want to drive home this point of being open by default. I think the benefit of allowing your models to be shared and to develop them as a community is something that's very important. I think it is really a wave that's happening in our field right now. So the second consideration that I want to talk about is that the inherent complexity of space weather requires new approaches to predictive modeling. So it's easy to think of these systems when we look at the heliophysics observational fleet as more simplistic when we look at that high level than they actually are. But what if we look closer? So this is a picture that I'm sure everyone's seen a million times. But if we look closer at the Earth's system, all we recognize is that the complexity of that system is astounding. There's so many phenomena going on. There's so many coupled phenomena across multiple scales that we recognize that some of our simplistic approaches to prediction don't have the expressive capability, that capability of representing and finding nonlinear relationships that we need to push the envelope for prediction. And so going back to the question of what does it take to predict these variations in the space environment, the point that I want to make in this consideration is that it takes more capable models. And so I'm going to give you two examples that cut across the geospace environment that explore the capability of models. The first is one that I have led using global navigation satellite system signals. And these are things like GPS, which are communicating with the ground through radio waves. And based on how those radio waves are disrupted as they pass through the ionosphere, they can tell us a lot about that environment. But the problem is that those are extremely complex. And so if we just look a little bit closer, say that a GPS satellite is communicating with the ground, that satellite will experience some kind of disruption as it passes through the ionosphere. And based on that disruption, we can infer very important properties such as the total electron content or the integrated electron density along that ray path. And we can use that to infer characteristics and behavior of the ionosphere. But one thing that happens is during geospace activity or geomagnetic activity, there are these irregularities. There are density pockets that emerge in the ionosphere, and we're very interested as in our community, and it's very important to be able to predict those irregularities and to really quantify when those irregularities will occur and try and provide that information. So the approach that we used with this project was, can we pull together these signals from all GNSS satellites over many years worth of data to understand and try to predict when those irregularities would occur, how they would affect the GNSS systems, and better protect the systems from those disruptions. So the way that we went about this was we took that data science approach, but we realized that in the analysis component, we were going to need a model that was capable of expressing these relationships in a more nonlinear way. And the reason for that was that these irregularities are random electron density fluctuations. And so they're very complex and they evolve nonlinearly. So if you think about that, the situation that we have here are many different GPS satellites orbiting through space, and they're communicating with many different ground stations. And any one of them could be impacted by an electron density irregularity. It could completely miss an electron density irregularity, or it could encounter multiple. And these irregularities are moving all the time at different speeds and different directions. And so we have a highly complex situation here that we need to see if we can use a method to predict these irregularity locations and evolutions. So the approach that we took was to build a machine learning model that would try to predict when a GNSS signal would experience simulation. So I think when people consider a machine learning model, they often default to a deep neural network. So that's kind of one of the ones that are regularly put forward. But I want to point out that there are there's a huge spectrum of machine learning algorithms. And so these exist across the spectrum that I like to use that range from something that's very statistically based, something that we can very easily explain, to something like a deep neural network that's more difficult to explain. And I think we have the opportunity with these advanced models to create a new narrative of new scientific understanding by analyzing each step in this process. So how do we build new scientific understanding going from a more simple method that may not have the expressive capability of a neural network, but ranging across that spectrum? And so that's what we did with this approach. I'm just going to present one result of this analysis, the outcome with the support vector machine. And so what you're seeing here is essentially the outcome where we've taken one ground station and we're predicting the ionospheric disruption to the GNSS signal that is communicating with. So this is a machine learning model that we've trained over years worth of data, and we're just predicting for this one ground station over 1 day. And so what you see is the 1 day's time series. At the top, we're showing some of the input data that we use to make these predictions. So that's the interplanetary magnetic field Z component in red, the Y component in blue. The next input is the global KP index. And you can see that over the course of the day, this rises from no activity up to mid-range activity around a KP of 5. And then the auroral electrojet index, which is another important parameter for characterizing these signals, telling you how much current is flowing in the upper atmosphere. On the bottom, what we're showing are 3 time series representing these data. So the first is the truth time series. This is a classification model. So we're trying to predict when the scintillation that you see here, represented by the phase scintillation index, will rise above this threshold that we set. So these are the really important times that we want to predict so that we can understand when this signal will be disrupted. So the middle plot is the results of our model. And I've classified it according to the contingency matrix here, where you want to see mostly blue and green. So that means true negative, you correctly predict when no scintillation would occur, or true positive, when you correctly predict when scintillation itself will occur. And then on the off diagonal, the red and yellow represent false predictions. So that's a false negative and a false positive. So what you can see on the very bottom plot is the current state of the art. So the best model that we have essentially for scintillation prediction right now is persistence, which is just saying that whatever exists now are going to be the conditions that exist next. And so you can see how the prediction of these models compares. So one thing I want to point out is that the support vector machine is doing a much better job of capturing this intense scintillation that occurs in the middle of the day. You can see that the persistence model just essentially completely misses this. One point of consideration that I'll drive to in a minute is that you see that there is a large amount of data where there's a false positive, where the support vector machine is predicting scintillation to occur, but no scintillation does occur. And so that interrogation, looking at that and being able to look at it in this way and understand where the model is incapable, gives us information about what new information we need to include in the machine learning model to be able to distinguish those fringe cases. So that interrogation gives you information based on your physical understanding of how to improve the model moving forward. And so this is just one example of how we can use machine learning to better predict and better characterize the space weather environment. I want to give one more example though. And I want to look at a system that may be less familiar to this community, and that's the Earth's radiation belts. And so the question that we have here are, how can we characterize this complex environment, the radiation belt environment, using some very sparse data that we have? And is machine learning an approach that we can use for that? So what you see here is the orbit of, just a cartoon of an orbit of the Van Allen probes. Right? It's a set of satellites that orbit in the Earth's radiation belt, and they've been orbiting for years. And what they've discovered from some of these data are that the radiation belts are extremely complex. And so I'm just showing here the observations from some satellites orbiting in the radiation belts compared with the DST index. And so you can see that you have similar disturbances in the DST index across these 3 different orbits. And despite the similarity in that we have intense activity from DST, we see drastically different behavior in the radiation belt. And so what this is indicating is that there's not a simple relationship between the radiation belt density and the disturbance storm time index. And so it's again pushing us to explore what more capable models can do in terms of representing this nonlinear relationship. So a colleague of mine, Jacob Bortnick, produced a new neural network that was capable of reconstructing the 3-dimensional relativistic electron fluxes in the magnetosphere, which is a critical parameter for monitoring the space environment and protecting space assets through the low Earth orbit environment and the geospace orbit environment, or the geostationary orbit environment. And so I'm going to play this video in a second, and what you're going to see is that this model is cued to that DST index, the space weather activity indicator, and the corresponding reconstruction of the electron fluxes throughout the inner magnetosphere as produced by this neural network that he put together. The goal of this is, given a set of sparse measurements, so the Van Allen probe's radiation belts, of some quantity. In this case, it's the relativistic electron fluxes that it's observing. At location R and time t, can we reconstruct Q over all R and at any t? So can we build a model that can reconstruct this whole density? And so the approach that they developed was a neural network approach. And they developed this neural network at several different energies. And I'm just going to play this model. I'm not going to get into the details of the neural network. I'd be happy to discuss that with people offline. But I want to show what this model is capable of doing. So basically, going from these point measurements, trained in a neural network model with only the disturbance storm time index and its time history included, we can actually make full maps of the electron flux data. And you start to see a few things emerged from this, but the network is very accurately capturing the areas where the data density are high. So when at energies of 1.8 mega electron volts and 2.1 mega electron volts, the observations that the Van Allen probes provide are very dense. They see those energies quite a bit, and so you can get an accurate reconstruction there. But during the same movie, you're going to see some artifacts in these higher energy ranges. And one of the reasons for that is just that there's a sparsity of data at those higher energy ranges. So while machine learning is very appropriate for some of these lower energy ranges, we might need to bring in other information to fill out this higher information. And so it's very important, again, that we be robust and rigorous in our interrogation of these models. So like most successful machine learning efforts, the ones that really have the greatest success are the ones that utilize physical understanding. So machine learning is most successful when combined with real knowledge about the physical system itself. But I want to drive home one important message before moving on, and that's that the machine learning models can obviously fail. And so this is just an example I like to show where basically you have a number of images of chihuahuas and muffins, and this presents a huge problem for many of the state-of-the-art machine learning image classification models that we have. And so it's critical that we develop ways to understand our data and interrogate our models so that we don't end up with a model that can't distinguish between a muffin and a chihuahua. And so if you think about the space weather environment, we actually have, you can draw an analog to this. We actually have a lot of data that look very similar, but may represent extremely different phenomena. So we need that ability to interrogate a model that I was presenting before and to understand them. And then also to provide uncertainty bounds by rigorously interrogating those models. So to summarize this second consideration is that a few of the tools and technologies that we need are available in readily available statistical and machine learning software packages. So there are a number here that you can explore, but I think one of the areas that is really important to our community to really push the limits of our prediction is to develop more robust evaluation metrics and be more familiar with how we can interrogate our models so that we can emerge those artifacts that we've seen with the support vector machine and the radiation belt neural network models and build more robust models. The mindsets that I want to summarize here are that the most successful machine learning efforts are the ones that unify physics information with those. So the methods that are going to be most valuable in the future are those that bring together these two different approaches. It's also, the second mindset is what I started off with, in that we really need to understand how the science dictates what we explore, what machine learning models and what other data science methods that we explore. And so it's really starting with the science questions and then using those science questions to drive to the new approaches. And then finally, exercising care and rigor when we evaluate our data analysis results. We can do that. We can emerge areas where the model is not performing well in those cases. And I've provided in the backup slides that I will make available to everyone a number of resources that look at new ways of evaluating those results. So in the last couple of minutes, I just want to talk about the third consideration. And that's that I think progress requires a systems perspective that transcends disciplines. And so some of you might recognize this from the CEDAR strategic plan, which talks about complexity and what's required to analyze that. And one of the ways that we do that is to embrace unifying these different systems. So CEDAR science is focused on the near Earth space environment, but we realize that the near Earth space environment is inextricably linked to solar physics and interplanetary physics and the magnetospheric environment. And so what we need is a better capability of bringing those different disciplines together. And then I think that we can do that through adopting a systems approach. And being what I like to say, calling radically interdisciplinary. What the potential value of that is that this expands well beyond the heliophysics environment as well. We recognize that all of the critical science areas are dealing with these same problems. So you can talk about astrophysics dealing with extremely large volumes of data, or earth science dealing with the need to couple different systems together in a complex way. And so I think that the approach that's been taken to this point has been one that tries to look further in on specific fields. So for instance, in heliophysics, we'll focus on our own sun. Then there may be a subcomponent of that community that focuses in on a few observations nearer to Earth. And then there's a subcomponent of that community that focuses on one subcomponent, one mission, one set of data. But I think that the real value, and what I mean by taking a systems perspective, is looking at the areas between these fields. So what can we learn from the way that the astrophysics community analyzes their data? What tools are available and utilized in the earth science community that we can bring and transfer over into CEDAR data science to understand the system more comprehensively? So the quote that I just want to leave you with for this component is that the most fruitful areas for growth of the sciences are those that have been neglected as a no man's land between various established fields. So I encourage each of you, just as you're moving through this week and in your research, is to think about how you can expand and broaden what you're looking at and become more radically interdisciplinary. There's a lot of value to be generated from the progress that's been made in sister disciplines. And so I think that we have an opportunity to really advance our science by embracing those disciplines. So just to summarize the third consideration, which I just barely touched on, really just want to provide an overview so that we can continue to interact throughout the week, is the tools and technologies that are important to the systems perspective are data integration. So we need to be able to bring data from the earth science or solar physics into our analysis. And I believe one of the really powerful ways to do that is through knowledge graphs or relating these data. We can use tools from information theory to understand our observations and their information content more robustly. There's a pocket of our community that's making some really profound advances in that approach. And then I think there's really some work to be done in team science. So how do we better collaborate with people that we're not used to talking with? And one way that I've found has been particularly effective is to embrace this Jupyter Notebooks component. So this is a way to develop a more fluid exchange with individuals who speak a different language than you. And I'm talking about a language in terms of science. So it's very difficult sometimes to interact with earth scientists because they have different vocabulary than us. Data science and these Jupyter Notebooks offer a common language for us to better understand each other and better exchange information. So a few of the mindsets, I've just linked to a book that I think is very impactful. It's called Thinking in Systems by an author named Donella Meadows. I think it's eye-opening for how we can start to make some of these changes. And then the last point that I'll make is just drive home this being radically interdisciplinary. I personally am inspired by working in the spaces between fields and learning radically new things from colleagues that I'm not used to interacting with. And so I actually like a new term, a new branding of that called anti-disciplinary, which is a field that defies any of these disciplinary boundaries that we've set up. So I encourage you to explore that as well. So I'll end there, and I'd be happy to take questions, and I look forward to taking questions all week. I just want to leave you with these three messages and two final thoughts. One is that we will explore in more detail some of these discussions during our data science session tomorrow. And I encourage you to join that. And I would encourage people who are interested in carrying this conversation forward to join the CEDAR Data Science Slack channel and drop your questions there and start discussing some of these things so we can carry the conversation forward. Thank you, Kamal, and thank you, Matthew, for the time today.
Thank you very much, Ryan, for the excellent and holistic view of data science and the discussions on the role that it plays in space science and space weather. We have quite a few questions, so we'll go ahead and start those off. So our most upvoted question for you today reads, this question has been asked before, but I would like to ask again, is data science just not statistics repackaged in a more fancy and catchy title?
That's a great question. And I would point back to the definition of data science being something that cuts across data analysis methods, but it also incorporates the data collection, management, and communication. So the way that I would say it is distinguished from statistics is that it is also preparing the data for being analyzed. So I think that statistics falls under that data analysis heading, but it doesn't speak to all of what data science is.
Okay. Our next question is, what can data providers do to make it easier for others to use these large-scale tools with their data? For example, reported error, bias, and resolution.
I cut out for just 1 second, Matthew. Could you repeat that?
Sure. The question reads, what can data providers do to make it easier for others to use these large-scale tools with their data?
Oh, that's a great question, too. The term I think I just briefly touched on was analysis-ready data. So one thing that data providers can do is provide data that are enriched with metadata so that people have all the information attached to the data that they need to quickly begin using those data. So a few formats that our community has embraced are the common data format, or the CDF. So that's a self-describing data format, so it comes with those metadata. But there's also other formats like HDF. I think that the key thing is just making your data easily to be picked up and used. So think about someone who's not familiar with the data. What would they need to pick up and begin using your data? I'm working on a few different, very widely disciplinary projects. And one of the ways that we exchange information is exchange a subset of data with a Jupyter notebook that shows how those data are read in, how they're analyzed, and what's possible with those, and maybe even posing a few questions. So I would hope that data providers can start to provide things like Jupyter notebooks to interact with those. You might hear about that in a second from Asti.
Okay, thank you. We have time for a few more questions. So our next question is, how do you decide the most suitable tool to use among so many available ones, especially in the machine learning aspect?
Yeah, and another good question. And thanks for asking that, because it is very intimidating when you think about how many things are available. The way that I go about it is really just taking an experimental approach. So the first thing I'll do when I'm starting a new project is to understand what questions, what objectives am I absolutely trying to answer. So that's before you start doing any Google searches for tools or anything like that. It's understanding, what are you trying to accomplish? What are the science questions? Let those dictate where you go, and then have an open mindset. You can start to explore some of the different options. I mean, it's sometimes a bit of a spin up, but you're going to gain knowledge, you're going to gain experience, and you're going to learn the ecosystem that exists in these tools and technologies by really exploring them widely. So I take an experimental approach and pull together some data set that I can play around with, and then start exploring the different options that are available. But your community is also a valuable resource. So polling the community to find out what they've used in the past, what they've found value in, is also very helpful.
Okay, thank you. The next question is, what is the basic difference between machine learning and empirical modeling?
So if you, I'll give an example to answer that. So there's an empirical model of the Earth's electron precipitation. So this is what information, what energy is coming from the magnetosphere into the ionosphere. And so we use a model called the Ovation Prime model, and this is a set of essentially empirical models that have been binned in magnetic latitude and local time, and provide outputs based on a parameter called the Newell coupling function. And the way that empirical model was constructed was by these somewhat simple relationships between this coupling function and the electron precipitation. One of the ways that machine learning is different than that is that it can drastically increase the expressive capability between input data and the electron precipitation. So for instance, if we wanted to do something similar to what Jacob Bordnick did with the radiation belts, we can incorporate information from the solar wind, from those solar wind time history, the solar wind variable time histories, from the geomagnetic indices, and observations from other platforms that we may not think will be directly related, but may have information important to our problem. And so machine learning offers a way, a very formal construction of how to incorporate all of those diverse pieces of information in a complex model. So I would say that one of the key differences is just the complexity that the model is capable of representing. That response may not be satisfying, and I hope that whoever put that in, whoever upvoted that, would also start a discussion on the CEDAR Data Science channel on Slack or with me individually, just because I think that that's a great discussion to have and an open question.
All right, thank you so much, Ryan. I think that's going to conclude our Q&A with you today. And we're going to go ahead and move on to our next speaker, Dr. Asti Bhatt. She is a senior research engineer of geospace studies at SRI International. Dr. Bhatt is a space physicist with over 10 years of experience. Her specific research pertains to studying continent-scale processes in the Earth's upper atmosphere using a large network of optical imagers, and small-scale transient processes in the Earth's ionosphere-magnetosphere in response to geomagnetic storms using a variety of radio and optical instruments. She builds, installs, and develops data analysis systems for optical imagers that she uses in her research. She also leads a cyber infrastructure project called the Integrated Geoscience Observatory to provide a collaborative software platform to geospace scientists designed to generate reproducible research results. Dr. Bhatt has mentored 2 teams of participants in 2018 and 2019 for the Frontier Development Lab towards predicting GNSS disturbances caused by space weather. Dr. Bhatt is going to talk to us today about distributed instruments, opportunities for next generation CEDAR science. Whenever you're ready, Asti Bhatt, you can begin your presentation. Thank you.
Thanks, Matt, for the very comprehensive summary. Good afternoon, everybody. Now that we heard from Ryan about data science, I'm going to add to the problem of the volume of the data that is going to be available to us as a CEDAR community. The main question is, what type of data should we look for as CEDAR scientists, and how can we have more of it? The distributed array of small instruments is a concept that has been around for some time, but the basic concept is simple. The idea is to create many small instruments, taking a variety of data needed for research and spread them far and wide. The goal is to measure almost everything all the time and everywhere. So what are some of the things that have already been done, right? As a community, we have tried to do this for quite a few years. And here are about 4 different examples of these efforts. For example, one of the oldest instruments that most of you might be familiar with are ionosondes. Ionosondes use relatively simple sounding techniques to measure an ionospheric density profile. And there has been a concerted effort to create a large network of ionosondes, specifically by University of Massachusetts Lowell through their GeoDigison network. And here you can see their network. Similarly, the concept of a high frequency or an HF radar has been around for some time. And starting in the 80s, the idea of creating a network of over-the-horizon radars began to develop. And here we see the result as a big consortium of international groups who are working together to create a network of HF radars known as SuperDARN and make coherent data products available from it. The third example here is something that the scientists didn't go out and create with the goal of getting useful distributed data from. But we realized that existing GPS or GNSS receivers can provide us to study the ionosphere. And using these data products, our community has managed to create a powerful data set that is distributed worldwide. And we can access it from the CEDAR Molecule database. The fourth example is the Themis Optical Network. This was created as part of a NASA satellite mission, and having distributed imagers across Canadian sector observing aurora at all times now has a way to give us a big picture of what aurora looks like across the auroral zone, which is a powerful technique. So let's talk a little bit about where the idea comes from. There have always been these two parallel thoughts and efforts in the geospace community. Some of us focus on super accurate, high quality measurements, while others are more focused on making such distributed, even though they may not be super accurate, measurements. For example, an ionospheric profile obtained from incoherent scatter radar is very detailed and very accurate, but it is very resource intensive to build ISRs, everywhere. What you can do is build many ionosons, even though it doesn't give the exact super accurate profile like ISR. A few years ago, national academics convened a report to come up with requirements and science drivers to justify building more distributed systems. A lot of these requirements were realized by the global modelers, as you can imagine. And here are some of the science drivers that were identified by the committee that need distributed measurements to achieve them. And these range from understanding coupling between thermosphere and ionosphere to ionosphere and magnetosphere. And the key emphasis was on measuring key quantities at various spatial and temporal scales. So this was the origin. So next I'm going to highlight some of the DAISY efforts that are currently ongoing, and they are in various stages of implementation at the moment. The thing is that these are the efforts that will start bringing data online in the next few years, when many of you will be either in the process of graduating or have already graduated, and these data will be useful to you in your research. So first up, a personal space weather station designed by the HAM-SCI group, which you may know as a great citizen science initiative combining ham radio and ionospheric science. The new initiative that is coming from the group is a multi-instrument ground-based device designed to observe space weather. What all does it include? At the heart of it is a software-defined radio receiver with frequency coverage from approximately 100 kilohertz to 60 megahertz, which, as you know, are the frequencies especially sensitive to ionospheric variations. In addition, it will include a GNSS receiver chip and a 3-axis magnetometer. This suite of instrument is useful for both amateur radio enthusiasts and ionospheric researchers, making it available to a vast community that, again, can participate in space weather research. So if you're interested in this, reach out to the groups at University of Scranton, University of Alabama, or Case Western Reserve to know more about this. Next up, something requiring a bit more infrastructure, multiple input, multiple output meteor radar called Zephyr. This is a collaboration between MIT Haystack, University of Colorado, IAP, and University of Tromsø. It is named after the Greek god of wind. And why is that? Because it aims to measure mesospheric and lower thermospheric winds. Meteor radars work by reflecting a transmitted signal off of a meteor plasma trail and inferring properties of the meteoroid and the atmosphere, which includes wind speed and direction based on the return signal. The application of this MIMO technique offers a significant advantage over single output or single output systems, which have been traditionally used for meteor radars. The team has developed a coded continuous wave technique, which allows a network of MIMO systems to scale through additional transmitters or receivers. The advantage of such a scalable network is that each additional transmitter or receiver that you add adds a link to all the other transmitter receivers within range. So the network becomes quite dense. This effort started early this year and will be built in the Rocky Mountain area. What would the data look like? Something like this. Wind field estimate from such a system will have a nice dense 2D estimate of MLT wind fields. These are just 4 examples of what it might look like. All right, so the next one is called MaxStar. And as you may imagine, it has to do with deploying high quality real-time magnetometers across the continental United States. This initiative is by Computational Physics Incorporation and University of Colorado, and they aim to make the data available in near real time with 1 Hz data cadence. The science drivers, again, as you may imagine, are to improve spatial and temporal scales at which the geomagnetic data are available for the ITM science. Speaking of magnetometers, here is another effort where students are directly involved, and these are high school students. The Space Weather Underground is from University of New Hampshire and is working with high school students across New England to build and deploy the magnetometer. Again, the science driver is to study the ionospheric current system in response to geomagnetic variability. As you can see from the map on this page, this will create a really dense network of magnetometers across New England region, while also involving students in actually building and deploying them, which is a great thing that all of you should keep in mind. The next effort is from University of Texas Dallas on creating a low-cost GPS simulation receiver from easily available parts that runs on a Raspberry Pi. The team has currently deployed 1 example site in South America, but they encourage everyone to get their hands on building a system. So in the paper by Rodriguez and Moraes, 2019, this paper references all the instructions for building one. So if you're feeling up to it, you can build one either by yourself or with your buddy or maybe a roommate at this point, and deploy it at your university or your home. The receiver monitors ionospheric simulations from small scale irregularities. So more measurements there are, the better for the science that we all do. And speaking of this type of receivers, similarly distributed network of GPS receivers along with ionosounds and magnetometers already exists currently in South America, which is known as LISTEN. This network has been operating for a long time and has been used to derive information about traveling ionospheric disturbances and equatorial plasma bubbles, among many, many other science drivers. So now on to my favorite topic. What Matt mentioned in the beginning is one of the initiatives that I have been involved in is called Mango. This is a different technique from what you have heard so far. This is for optical imaging. This particular initiative, Mango Nation, involves 2 optical techniques which can work together to address critical science in the ionospheric-thermosphere system. The all-sky optical imager is called Mango. And yes, we definitely came up with the name first and fit it to the actual words later. Mango. So the basic design of optical imagers is publicly available in literature since about 1970s. And they have been used to do important science since then. However, when we started out creating a relatively large network of these imagers, we realized that you cannot necessarily build so many with such high or costly parts. What we did was we used simple amateur astronomy camera and all off-the-shelf parts to build F-region airglow imagers and created a standalone enclosure that can be installed on any rooftop. Here's one such example, right on the left. For the FBI, or Febrile Interferometer, a simpler design called Mini-Me has been in use for past decade. While it requires a trailer-like infrastructure, several components of this FBI have been designed and built by students, undergrad and grad students. So, what are we trying to get at? If this video plays, which is playing, the video shows the waves propagating in the F region of the ionosphere using the data from the Mango network. Now, we can see that these waves are traveling from some point source somewhere. So we know we have much of this smoking gun type of evidence that shows that there's a connection between the lower thermosphere lower atmosphere and the F region. And relatedly, this is a plot from the FBI, which gives us neutral winds in multiple directions. What we don't know is what happens between the lower atmosphere and the ionospheric F region. So combining the neutral winds and the imaging capabilities, we hope to actually figure out what is really going on. What are the thermospheric filtering processes that allow these waves to travel all the way up here? So this is a new initiative called Mango Nation. What we are trying to do is create a network of green line imagers observing air glow at 95 kilometers, and the FBI providing red and green line winds, which will be nested within the larger red line network. And what we are hoping to do is understand better what happens in the lower thermospheric region between the sources like thunderstorm and the effect that you saw in the video. Well, that was a lot. Okay, you heard about a ton of new DAISY initiatives, but the question is, what is it that you as a student should look at? There are two ways. One is to get involved with the hardware, and the second is to get involved with the data. If you are at one of the universities involved in DAISY initiatives, contact the people in charge to get involved in building and deployment of the instruments. Even if you're not at one of the universities, contact the people anyway, because many of us are always looking for working with students to, go and deploy the instruments or build the instruments. It's a great way to get a hands-on experience on not just building an instrument from scratch, but also learning to work with field sites, which can be both exciting and a big learning opportunity. Secondly, the DAISY instruments that are existing and those that are coming online are poised to produce a ton of real-time data. And this goes back to what Ryan was talking about earlier. Can you think of some novel data science application with this data? For example, how can you combine super accurate data from super accurate instrument like ISR and not so accurate, but a lot of data from multiple distributed instruments? What are some of the techniques that you can use? How can you combine data from satellites and these ground-based instruments to derive new insights? As you will hear next, many of these DAISY implementations will also have conjunctions with the new ICON spacecraft, among other spacecraft that are already existing. The possibilities are endless. So I encourage you to keep an eye on them and upcoming DAISY implementations and do some awesome science with all that new data coming online. Thank you for listening patiently. I mean, not that you had much choice, but still. I'm happy to answer any questions now or later on. And thank you, Matt and Komal, for organizing this session.
Thank you, Asti. It was a great talk. Thank you especially for highlighting how students can contribute to this initiative. We have some questions for you. So I think you a little bit covered on that, but someone asked, are you expanding this initiative to other continents as well?
So the initiative that I am personally involved in, the Mango Nation, we are currently not expanding it in other continents, but there have been other initiatives like Listen, which are already in other continents. There is also an existing network from Boston University, which is extending the optical imaging to South America. But if you have specific ideas, reach out to me and we can see where we go.
Perfect. Another question for you. Is there a central repository or one that is planned to collect and store all of the data from all of these distributed observations?
That is a great question and something that is close to my heart. We currently have CEDAR Madrigal database, which hosts lots of data, lots of process data to make available to the community. However, for a lot of this data, the intermediate products may not be available from the CEDAR Madrigal database. And for that, right now, all of these have different systems at their disposal. But it's not really ideal. One of the other initiatives that Matt mentioned in the beginning is called Integrated Geoscience Observatory. One of the ways that we can actually work together to get the data from multiple different instruments and create something that is more centralized is to use more collaborative tools as a community together. And the Integrated Geoscience Observatory project actually gives you an access to use and also contribute tools to access different type of data. So for example, you can currently access Mango data using a MangoPy Python library installed in this NGO platform. And if you are going through the multiple sessions throughout this week, you will hear about a platform called Resin, developed under the Integrated Geoscience Observatory project. And that will tell you a little more about how you can use it. But to answer your question, no, there is not a single central repository for all these instruments. And that is something we as a community should go towards.
Yes, I also agree, Asti. Thank you. Another question is, someone asked, are the data from all sky cameras made available publicly?
Yes, they are. The there is a website called mangonetwork.org. That's where the quick look data products can be made available, and a library, a Python library called MangoPy is available. You can pip install it, and you can use that library to access process data from this.
Perfect. Thank you. There's another very interesting question. How can a student who is willing to join and help in the building, how can a student join and help in the building and installing the instruments?
Oh, again, great question. So in the slides, actually, I've listed out who are the people responsible for each of these instruments. Reach out to them directly, send them an email saying you want to be involved in building and or deploying the instruments. And I can assure you from all of these, you will get at least one or two responses that are favorable.
So that was all for the Q&A session for you, Asti. Thank you so much for letting us know about this wonderful opportunity, especially for students.
Thank you.
Thank you. With that, we will move on to our last and small break. So Asti finished a little early, so we have 20 minutes. So we'll be back basically after 17 minutes with a great talk about Icon, which also talks about the new data. And so please come back for this great talk. Welcome back, everyone. Now we are going to move to our last talk for the day. We have Scott, our speakers for the
Welcome
last
back,
talk.
everyone.
Just
Now we're gonna move to.
my bad. So our speakers for the last talk are Scott England and Colin Triplett. They are co-presenters. They will be talking about the new ICON mission, which was launched last year. I know, just like me, many people in community have been waiting for the first ICON data. So I will let the speakers talk in details about it. Scott England is Dr. Scott England is an associate professor at Department of Aerospace and Ocean Engineering at Virginia Tech University. Scott did his PhD at the University of Leicester, UK, studying coupling of energy and momentum between different regions of the atmosphere via atmospheric waves. He spent 12 years at the Space Sciences Laboratory at the University of California, Berkeley, where his studies focused on the interaction between atmospheric waves and charged particles in the near Earth space environment. He came to Virginia Tech in 2016 and currently focuses on using remote sensing instruments to study the upper atmosphere and near Earth space environment. He's the project scientist for the NASA ICON spacecraft, a co-investigator on the NASA Gold spaceflight mission, and a participating scientist on the NASA MAVEN mission to Mars. Then we have co-presenter Colin Triplett. Colin is an assistant research physicist at Space Sciences Laboratory at University of California, Berkeley. Colin received his PhD from the University of Alaska Fairbanks in atmospheric sciences. His research focuses on dynamics of the middle and upper atmosphere and how different scale waves interact and drive the atmospheric system. He has used both model simulation as well as sounding rocket and LiDAR data to study multiple scales from turbulence to atmospheric tides. Colin is currently working with the ICON, NASA's Explorer mission, to study the interaction of the neutral atmosphere and the ionosphere. Our both presenters will be talking about the ionospheric connection experiment, which is ICON mission and the first data. So with that, I would invite the speakers to go ahead with the presentation.
All right, well, thank you. So yeah, Colin and I are going to talk to you about the ICON mission. And ICON is focused on looking at the low latitude ionosphere and thermosphere and the connection between these two. And ICON launched in October last year, and actually the first data is just appearing right now and is being made public. So the timing of this talk is really excellent, that we can introduce you to what ICON is, what science we were aiming to do with the spacecraft, and therefore what instruments we carry. And then we'll show you the first data. And I know this is focused at students, so we're really going to try and spend some time showing you what the measurements are, what the data looks like, and then where to go get the data. I'll just have a quick shout out that Colin and I are not really introducing like first science results. Those are going to be presented in some of the plenary talks that are occurring during the week. So look out for those through the week. Okay. This is a quick outline. So what I'll do is I'll go through, what we were trying to look at with ICON, how we might go about that, up through to the instrumentation that we carry. And then I'll hand over to Colin, who'll do a bit more about the mission design and the data and where to get more information. So I said ICON is looking at the low latitude region. And if you open a textbook and look at, really simple version of the low latitude ionosphere, it may look something like this, that at low latitudes, we have a very dense F region, a very dense plasma there. And one of the reasons that the F region plasma is so dense at low latitudes is that there's a lot of ion production from sunlight, and that there is this upward lift of the plasma during the day. And if you go look at how it will explain that, it will link this to a process called the E region dynamo. And that's kind of shown in this cartoon on the left, that what we have is winds blowing in the E region, and they're able to move ions at those altitudes and create currents. And where we have gradients in the winds, gradients in the conductivity, we can build up electrostatic fields. These electrostatic fields can map to the F region. And in this region near the magnetic equator, where we have a horizontal magnetic field and some horizontal electric fields, we can produce an upward motion, an E cross B drift of the plasma. And this does a couple of things. One is it takes it away from the region where the sunlight is forming that plasma and allows even more plasma to be created there. And as it raises it to higher altitudes, it increases the lifetime of that plasma, allowing you to build up a very dense F region. You can make measurements of this uplift. In the middle, we see some climatological picture of this uplift. And I shaded out what's happening at sunset, because what I'm talking about is just the E region dynamo. So what's happening during daylight and then nighttime, but not around sunset. And so you can see any season of the year, the climatological picture at the equator is an upward motion at all hours. And what goes up slowly starts to diffuse back down, parallel to the magnetic field under force of gravity and pressure gradients. And we build up two bands of dense plasma either side of the magnetic equator, which is shown in the picture on the right, which is essentially an output from a climatological model of the ionosphere. So if you start digging a little deeper and you say, okay, I understand this textbook case, what does reality look like? It's a little more complicated. And if you go and look at the climatological drifts that we were showing just a moment ago, and those were made at Hickamarka, and you go look at individual days of drifts and plot all those together, you get a plot like this on the right. And I'll say that this is put together from data just from quiet times. So the magnetosphere is not very variable. The sun is not very variable. And if you look at this, you see a lot of traces. And if you squint, you can see that climatological picture in there. But there's days you can see here where the drifts are downwards for the entire day, looking nothing like the climatological picture. And other days where it appears to follow the basic trend, and then suddenly something happens. And we don't understand this. We can get some picture of what's going on by taking a look at other data. Okay, Hickamarka is one point, just measuring the drifts overhead. So if we pull back and we look at an example of a distributed array, here this is TEC data from a distributed array of GPS receivers. We can look at the consequences of this sort of variability. What these plots are, these are 3 days, 3 successive days, and each plot's at the same time of day. It's roughly noontime over kind of Central South America. And on all 3 of these, the magnetosphere is very quiet, the sun is very quiet. So these should, with our textbook picture, all look the same. In the picture on the left, you can see that pattern that we're expecting, these 2 bands of dense plasma either side of the magnetic equator. The very next day, you see the bands are there, it's not as dense, and something is happening. They're well separated on the western side of South America and kind of fusing together on the eastern side. And on the very next day, we don't see 2 bands at all. We see 1 blob at the equator. And you could try and say, oh, maybe this is a manifestation of these changing drifts that we were seeing with Hickamarka. And that may be true. You can also see other things here. For example, the pattern is somewhat coherent on a continental type scale. It's not that every pixel in this image is doing its own thing each day. So what we're looking for has some spatial, perhaps temporal coherence that is medium or large scale in nature. It's not happening down at a microphysics kind of perspective, at least not the the main process we're seeing right here. So in parallel with that, we were doing this work looking at impacts of some large-scale waves that we had a great talk on earlier today. A specific category called non-migrating tides. So these come from zonal asymmetries in energy input in the lower and middle atmosphere. In this case, our work focused a lot on a particular diurnal non-migrating tide that we think is forced by an asymmetry in latent heat released in the lower atmosphere. And then that wave can propagate all the way up to the thermosphere and start interacting with the ionosphere. And when we were looking at that, this is on the bottom left, an image we put together from timed GUVI, looking at the density of the O+ plasma just after sunset in a climatological sense again. So this is using a whole month of data. And you could see the two bands following the equator jump out, but there's a structure within there, even in a climatological sense, this change in the density with longitude that we termed this wave 4 pattern. So even in this climatological sense, we can see some of this, and we can see some of this on large scales, but there's clearly a lot going on smaller time scales and smaller spatial scales. But these two avenues of thought kind of came together and gave us this picture of what might be happening. What may be happening is that a lot of the variability and the energy inputs that we have in the lower atmosphere could be propagating to the upper atmosphere through atmospheric waves, perturbing things like the E-region dynamo and creating changes in the ionosphere that we see. And this sort of gave us the idea for the ICON mission. And so that leads us to what we want to observe. And what you'd like to observe is pretty much everything that's going on in this cartoon. You would want to observe the winds all the way down in the E region, up through to perhaps the F region where they could be blowing the plasma, advecting it directly. You want to be measuring the resultant plasma drifts that occur, and you want to be measuring the plasma density that is building up. And if you dig a little deeper, it's also apparent that measuring the neutral composition will give you information, because that's tied into the plasma production and loss as well. And if you can measure temperature as well as wind, then you can get a lot of information about these waves. So that sort of brings together what we wanted to observe. But there are challenges here, and perhaps one of the most challenging was to make those wind measurements in the E region. These are extremely difficult to make from the ground, and ground-based measurements are hard to get on this global scale. The E region is also too low to fly a spacecraft, so you can't make in situ measurements of these. You have to go to a remote sensing technique. And this, thankfully, is where nature helps us out a little bit, in that we have a phenomena called air glow. So as we get to the upper atmosphere and collision times, or times between collisions of atoms and molecules, gets longer, then when an atom or molecule gets energized, it can de-excite by emitting a photon rather than just losing that energy through collisions. And so we get air glow, this light coming from the atmosphere, and we'll get this in infrared, visible, ultraviolet wavelengths. The visible you can take nice pictures of, like this one shown on the right-hand side. And in there, there's information. You know, the wavelength of light might be telling you the species that it's coming from. The brightness may be related to the density. If you can measure the wavelength very precisely, you can get Doppler shift of that wavelength, which gets you a way of measuring winds. And you can get temperatures from shapes of certain spectral features. And another thing is, from this sort of vantage point in low Earth orbit, looking out on the limb, you can see all of these quantities as a function of altitude by just looking at those, what we call tangent heights, but the height of on the limb on the horizon of the Earth. So this leads us to the complement of instruments that we had for ICON. And here, this is an artist's rendition of the spacecraft, and I've labeled, rather than the individual instruments, I've labeled what we're measuring. So we can measure those ion drifts in situ at the spacecraft. We have 3 other instruments that look out at the limb, and looking in the infrared, we can get information about atmospheric temperature. Looking in the visible, we can get the winds. And looking in the ultraviolet, we can get the atmospheric composition and the ion densities. And I'm going to hand off to Colin here, and he's going to take you from this picture of what we wanted to get and show you the data and the data coverage that we actually have.
All right, thanks, Scott. So I'm going to briefly go over more nuts and bolts of what the ICON mission is about. But what you see here is a rendition of the basic mission plan that we have. So you see ICON flying along its orbit in the green line. It's flying at an altitude of approximately 600 kilometers. And we get in situ measurements there of the ionosphere from an instrument known as the ion velocity meter, or the IVM. So it's sampling things such as the density and the temperatures of the ions in situ of ICON. And at the same time, we have 3 instruments that look out on the limb. Those instruments are the MIGHTY instrument, which measures the winds using those airglow layers that Scott talked about. The extreme ultraviolet, or the EUV instrument, which gives composition. And the FUV instrument, which also gives composition. They do it in slightly different ways, so we get more information out of it. And as ICON flies along, the limb instruments look out, and they give us data that's sort of in situ, or they give us data that's remote along field lines and down lower in the atmosphere where it's hard to actually fly. So as ICON is flying along, we can look at changes and spatial variations of the winds and composition at the tangent points. Now, one of the things that we can also do is we have some special maneuvers. So on the next slide, oh, not this one. So this is giving us a sampling of where ICON can look out upon the limb. So on the right, you see a full month's worth of coverage of the tangent locations. So these are the locations that are looking out upon the limb, and you see that we take data between 12 south and about 42 north, but we can get this whole swath of the planet within a month. And this is when we're looking north, or what the team refers to as normal LVLH. The plot on the left is showing us when we turn the other way, or look south. This now gives us data between the 12 north and 42 south. As of now, ICON is only planned to be looking north, but future operations may allow us to look south in order to get more data on the southern hemisphere than we currently have. But you can sort of see this coverage over the entire planet that we get just within a month. So we have the ability to sample the winds, the temperatures, the composition over a large range of latitudes and longitudes over a large period of time, which allows us to pull out large-scale information about tides, but also looks at sort of smaller scale winds and a much smaller time frames. So if we go to the next slide. So these are the main data products that ICON will be producing or will eventually be producing. There are 4 levels. Level 1 is basically calibrated instrument data. These are things like brightnesses, intensities, the things that we make our measurements off of. Level 2 data are the inverted geophysical data. So these are the actual wind data, the actual temperature data, our composition data, our ion parameter data. And these things are also given to you on geophysical grids. So latitude, longitude, altitude, things that make it a little bit more easier to piece together what's actually going on in a geophysical sense, as opposed to the level 1 data that basically give you out as ICON flies. These are the most important data for pretty much everyone listening to this, both students and non-students. This is where you're going to get the data that you actually do analysis and sort of figure out what different science questions you want to answer. We'll also eventually be producing level 3 data, which is sort of a summary data. And then something that ICON is doing is we have these level 4 data sets. Now, what these are going to be is we are taking large-scale models, the TIE-GCM, or the thermosphere-ionosphere electrodynamics general circulation model, SAMI-3, which is an ionosphere model, and the IDA4D, which is another ionospheric model. And we're actually taking those using ICON data, different data products, depending on what the model is, and actually running those models and outputting those data to give out to the community as well. So we have not only just instrument data, but we also have model data based upon those instruments. Right now, currently, we do have level 1 and level 2 data available, some of it. It will slowly be being released to the public over the next week and possibly into a little bit into July. But as that rollout comes, you'll be able to find it. All of our data will be publicly available. And it'll be easy and without any sort of issues that most people will have behind walls or anything. So if Scott goes to the next slide, I think these are the, yep, a little bit more understanding of the level 2 data products. Again, these are the sort of the most important data that you'll be looking at. We have 7 sub-levels of level 2 data. Level 2.1 and 2.2 are related to each other. One gives a line of sight winds. So as we look at on those tangents, we actually measure the line of sight wind of the mighty instrument itself. And in order to get, we can take those 2 data sets and we can calculate the cardinal wind directions, and those are called the vector winds. So we have both of those available. The 2.3 are the neutral temperatures that come out of the mighty instrument. Level 2.4 comes from the FUV instrument. Its main data product is what's known as the oxygen to nitrogen ratio, or the O to N2 ratio. This gives us information about the dynamics that are happening within the atmosphere based on how those 2 species of those chemical species are interplaying. We also have 2.5, which is also an FUV product. This gives us the nighttime O+ profiles. It gives us the HMF2 and NMF2. These are the height of the F2 layer and the number density of the F2 layer at night. The 2.6 data product comes out of our EUV instrument. This gives us similar things to the 2.5, however, this gives us them during the day. So this allows us to have composition both day and night throughout the mission. And then level 2.7 is the ionospheric composition coming out of the IVM. These are the in situ plasma parameters as ICON flies at 600 kilometers. And each of these allows us to get a larger picture of what's happening dynamically as ICON flies. So now I'll be showing you some actual data. So this is actual wind data that has come out of ICON. This is courtesy of Brian Harding. So what you see on the left here is just basically a day's worth of data, individual orbits going in solar local time, which is something that we normally work in because it's an easier way to see how things are reacting as related to the sun. And we can basically just see variation or changes in the winds throughout the orbit. These are a combination of 2 different mighty products. But basically, you can just see that as ICON's flying, we have this ability to look at these different points and to actually measure the winds as they go through. So the right side is showing the tangent point location on the planet, and the black bar is telling you where that right plot is showing. And if we go to the next slide, this is just some sort of example data from the temperatures. So this is just daytime temperature data from a particular day that we have, just showing how the temperature is changing with height during the daytime for these data. So just you see some scale, you can see some different scale changes. You can see how things are just changing throughout the day. And just sort of the variations that we can see even on the smaller time scales that ICON can see, as opposed to the larger time scales that we can also see as we fly. This is that FUV OTA N2 product just an example of a vacancy on a different day. Right now, what the OTA N2 can give us is what we're calling the disk column OTA N2. So as opposed to looking out on the limb, the FUV instrument can also look on the disk below icon. And these are those OTA N2 values that it can see over the disk throughout a day. And then I think and this is an example for just IVM temperature data for the ions throughout a single day. I believe this is the same day as the temperature data that I showed earlier for the MIGHTY instrument. And you can just see how it changes throughout the day, large scale changes, small scale changes, and the like. So what icon data allows us to do is take all these different things and be able to piece together a larger picture of what's happening, not only in the ionosphere itself, but also below the ionosphere, to see what dynamics of the neutral atmosphere are affecting the ionosphere itself at the same time. So, most important question, more information and where you can find the data. There are some publications that we have, papers that talk about the nitty-gritty details about how the data is processed, what assumptions go into the data, things along those lines. You can find that at the website above as publications papers. And also, one of the locations you can get the data is directly from the ICON website. As you can see here, the icon.ssl.berkeley.edu/data. This is our public-facing website, so this is where the latest and greatest data will exist. And currently there are some data products there that will slowly again be rolling out this week and in the coming weeks. If you have more questions, or if you want more information about the data products themselves on a slightly deeper level than what we were able to give today, there's a session on Wednesday that will go over the do's and don'ts of the data and sort of how to play with the data at 1 p.m. Mountain Time, and you can find that on the CEDAR schedules. And I believe that's the last of it.
Okay, thank you, Scott and Colin, for your excellent summary of ICON and the data that is currently or will be available soon. So we have a few minutes for Q&A, the final Q&A of the day. So I'll go ahead and jump right into the most popular questions. Our most popular question reads, several talks today have used the term electric field mapping. Can you elaborate on what this is? Is it an approximation?
Perhaps I could talk to this. It is an approximation. It's a relatively good approximation. I guess we shorthand it in terming it electric field mapping. What it really is saying is that the magnetic fields at higher altitudes are effectively equipotentials. And once you get up to the F region altitudes, that is a pretty good approximation. So it is saying that if we measure either the electric field or the E cross B drift that results from it on a field line up at, let's say, 600 kilometers, that you can relate that to the electric field that is at 500, 400, 300, 200, and so on. You have to scale this with effectively the magnetic field strength, which is known, extremely well at the altitudes we're looking at the low latitudes. It is an approximation, and it starts to break down as you get to very low altitude. But what it basically means is if you're really trying to see the electric fields, the E cross B motion at, say, 300, 350 kilometers, extending it from there to 600, that is a very good approximation.
Okay, thank you. I think we have time for one more question. Our next question reads, will uncertainties for all of these data be provided as well, specifically for the level 2 data?
Yes.
Easy.
Yeah, absolutely. Every part of the level 2 data comes with a wealth of metadata, including uncertainties, and in some cases, those uncertainties are subdivided into sources of uncertainty. But yes, there's... everything you would want.
All right, I think we're just now turning to the final minute of the day. So with the conclusion of that talk, I wanted to say that it has been a long day. Thanks everyone for joining, and we hope that you enjoyed today's workshop. We also thank all of our speakers for their excellent informative talks. Before we conclude the day, Kamal would like to remind everyone of a few things from this morning. So Kamal, whenever you are ready, you can go ahead and take over.
All right. All right. Thank you, Matthew. Sorry, I had a little glitch. Thank you again, CEDAR attendees, for attending today throughout the whole day. Although it was a long day, but there were 8 wonderful talks. So as I had also announced at the beginning that we will be publishing CEDAR Student newsletter this year. And we will be publishing summaries of each of these talks, which would be written by our student volunteers. We'll also be publishing student feedback. So please give the feedback. Please fill out the feedback form we're gonna send you out at the end of this week, the feedback form. So it's important that you guys fill the feedback form, and please be candid. And please expect this newsletter to be released sometime in July. We will also publish the answer of the rest of the questions that could not be asked in Q&A sessions. At the last, we really we give special thanks to our student volunteers for helping us with this newsletter. We thank again to Deepti Ayagri from Indian Institute of Technology, Indore from India. We have Edith Makatala from University of Oulu, Finland. We have Megan Leme from Boston University in United States. We have Robert Ryan from University of Illinois from United States. We have Aiden Montier from Case Western Reserve University from United States. So thank you. And with that, I also want to add that if anyone in the audience also wants to contribute to the student newsletter, please reach out to Matthew or myself via email that you can see on the top right of the slide. You can also reach us via Slack workspace, CEDAR Slack workspace. So I am not okay. Yes. This CEDAR Science Slack workspace has been newly created, as Matthew had talked about that in the beginning of the today. So this Slack workspace has been created in order to have sustained interactions within the community during the virtual workshop and even afterwards. We also strongly encourage workshop session conveners and other community leaders to join and utilize this workspace. You can create channels for sub communities. So for example, we have a channel for data science. We also could have a channel for modelers. So that was just to give an example, but we strongly encourage the workshop session conveners to go use this QR code at the top right of this slide to invite themselves to this Slack workspace. Then we also invite students to join this Slack workspace and play a leadership role in making this a beneficial resource in terms of communication within communities. Students, for example, students can come up with a journal club and you can make a channel for journal club, and students can meet regularly and talk about a paper or new data or new missions, or even about the conference updates. Um, at the end, Professor Dolores Snip would like to ask questions to the, especially to the student participants. What topic instrument not addressed today would you like to know more about next year? So please let us know answer of this in CEDAR Slack workspace. You might have very interesting comments from different professors in our community. So other relevant information, for the CEDAR attendees who especially who are attending the CEDAR first time, if you are not subscribed to the CEDAR mailing list, please do so by using this QR code. If you are if you're subscribed to the CEDAR mailing list, you will get the emails about the job opportunities, conference updates, new missions, new data through this email list. So if you're not part of this list, please do so by this QR code. And then an important announcement: Matthew is an outgoing student representative this year. He has completed his 2-year term of student representative. So we would like to replace Matthew with a new incoming student representative. So if you would be interested to organize the student workshop next year with me, please nominate yourself or or someone you know. We'll be happy to answer any questions you may have. You can contact us via email and preferably from CEDAR Slack workspace. At the last but very important, we will be sending out you a feedback form for the student workshop. Please fill this out. Please be candid. Let us know what you think about the future directions of space physics and aeronomy. Let us know about any specific comment or anything that you think we missed, which fits in the theme of the workshop. Also, if you want to suggest any future theme for the next year workshop, please fill out this feedback form and let us know. What do you think? So with that, thank you again for your attendance from all around the globe. We encourage you to look into the full workshop CEDAR schedule using this QR code, and there are many interesting individual sessions from tomorrow onwards until Friday. And these sessions can spark new ideas, new interest. You might want to talk with some of the presenters. So it's a great way to even make connections. So I urge the students to please go ahead and explore the CEDAR workshop schedule and also the CEDAR Slack workspace. Thank you again. And now Matthew and I would like to end the student workshop for today. Thank you.